Welcome. Today we begin a chapter on designing resilient distributed systems. We'll explore how systems survive unpredictable failures, and why consensus is a central building block. Keep this title in mind as the theme for everything we cover. Start with this provocative quote from J. Krebs. It captures an engineering trade-off. Often it's better for a system to stay available, even if imperfect, than to stop working to preserve absolute correctness. We'll return to that tension many times. Distributed systems fail in many ways. Nodes can crash or pause unexpectedly. Garbage collection can freeze a process for seconds. Networks can lose, reorder, duplicate, or very slowly deliver packets. Clocks are never perfect, they are approximate. These failure modes are the threats your design must tolerate. Here's the threat model we use throughout. Assume the network is unreliable, clocks are only loosely synchronized, and nodes may crash or pause without notice. Designing under this model is hard but realistic and keeps our solutions practical. A practical approach is to provide a few powerful abstractions that hide failure complexity from application code. Instead of each app handling every failure mode, we implement correct, well-tested components once and let everyone use them. This is how systems scale safely. You saw this pattern in transactions. Atomicity, isolation, and durability give applications the illusion that crashes and concurrency don't happen. Consensus plays a similar role for coordination problems. Consensus is the problem of getting a collection of unreliable nodes to agree on a single value even when some fail or messages are lost. It's the foundation for many higher-level services like leader election, configuration storage, distributed locks, and replicated logs. Consider leader election for a single leader replicated database. If the leader crashes, remaining nodes must agree on a new leader. If two nodes both act as leader, a split brain, they can accept conflicting rights and corrupt the system. A correct consensus mechanism ensures all nodes converge on the same leader and the same committed state. Think of the runtime flow as a simple pipeline. The client talks to a leader, the leader replicates to followers. If the leader crashes, the system must run consensus to agree on a new leader so clients can continue. The bad path is lack of agreement, which can lead to split brain and conflicting rights, exactly what we want to avoid. Not all guarantees are possible. In some situations, systems can make progress despite failures, but classic results show that certain strong guarantees are impossible under realistic assumptions. For example, deterministic consensus in a fully asynchronous system can be impossible with even one crash in some models. Practical design boils down to understanding trade-offs such as those captured by the CAP theorem. This chapter emphasizes intuitions and practical patterns that engineers can use. We won't prove every theorem here, instead we'll highlight the most relevant ideas and point you to references for rigorous proofs if you want them. By the end of this chapter you should understand 4 core things: what consensus provides and why it's challenging, how to safely use consensus in production systems, the common failure modes consensus protocols must handle, and the fundamental trade-offs and impossibility results that constrain our designs. In summary, expect failures and design for them. Use abstractions like consensus to simplify application logic. Be aware of fundamental limits and trade-offs, and choose the right balance for your system between correctness, availability, and complexity. Today we'll unpack what consistency means in distributed databases, how replicas can disagree, why that happens, and the trade-offs involved in making them agree. We'll move from the simple idea of eventual convergence to stronger models like linearizability and consensus. First, remember that when you look at 2 replicas at the exact same time, they may hold different values. This is not a bug, it's a fundamental result of replication. Writes reach replicas at different times because nodes communicate over networks that introduce latency and unreliability. The root causes are network latency and asynchrony. Regardless of whether a system uses a single leader, multiple leaders, or leaderless replication, messages carrying updates take time and can be delayed or reordered. That means global instantaneous state doesn't exist in practice. Many systems provide eventual consistency. In plain words, if you stop making writes and wait long enough, all replicas will converge to the same value. A clearer term for this is convergence, because the guarantee is only that replicas will agree eventually, not how fast. Crucially, eventual consistency says nothing about how long replicas may disagree. During that window, reads can return stale data or even no data. The system makes no timing promise beyond eventually, and it typically assumes network problems will heal. These differences matter in real systems. For example, you might post a comment on your phone and not see it immediately on your laptop because the read hit a lagging replica. Or two buyers might both see an item as available and complete purchases, causing overselling. Developers often expect DBs to behave like local variables, write a value and read it back immediately. Distributed systems break that intuition. Bugs from this mismatch are subtle and intermittent, often only visible under network faults or high concurrency, and are hard to reproduce. Because stronger guarantees are easier to reason about, many systems sacrifice latency, throughput, or availability to provide them. Enforcing a strict global order of updates can raise write latency or reduce availability during network partitions. Choosing consistency is an engineering trade-off. Consistency in a distributed sense differs from transaction isolation. Isolation deals with anomalies from concurrent transactions, race conditions within or across nodes, while distributed consistency asks how replicas reconcile state under delays and failures. They overlap, but they answer different questions. This chapter is in 3 parts. First, we'll study linearizability, a strong, intuitive model, along with its benefits and costs. Next, we'll explore ordering guarantees, causality, and partial versus total orders. Finally, we'll examine distributed transactions and consensus protocols that coordinate updates across nodes. As you learn these models, keep the engineering trade-off in mind. Stronger consistency simplifies reasoning and reduces classes of bugs, but can hurt latency and resilience. The goal is to pick the right consistency level for your application's correctness needs and operational constraints. Think of the topic as a simple flow. Replication leads to possible inconsistency because of network delays. Systems then offer guarantees, like convergence/eventual consistency or stronger models. Each guarantee has trade-offs in latency and availability. Finally, techniques ordering rules, transactions, and consensus protocols address those trade-offs at different costs. We'll unpack each step in the chapter. Today we will demystify linearizability, often called the illusion of a single authoritative copy. We'll see what it guarantees, why it matters, and the trade-offs when systems try to provide it. Linearizability means each operation looks as if it happened at one instant in time between when it was called and when it returned. In practice, the system should behave like there's only one copy of the data and all operations happened in a single order consistent with real time. You may see different names in papers and documentation: atomic consistency, strong consistency, or external consistency, but they all point to the same real-time ordering idea. The crucial part is real-time precedence. If operation A finishes and later operation B begins, then every client must observe a before B. That is how the system enforces a single, real-time consistent order. Linearizability is fundamentally a recency guarantee. Reads should reflect the latest completed writes. When operations overlap in time, the system can choose an order, but once chosen it must present that same ordering to everyone. A handy way to remember it: once you observe a result, any later read should see at least that result. This makes reasoning about programs much simpler and avoids time of check/time of use surprises. Imagine a live sports app where the referee records the final score. Alice refreshes and immediately sees the updated score. Bob, who refreshes after Alice and after the write completed, should also see the final score. If Bob's read goes to a replica that hasn't received the update yet and shows an earlier state, that's a violation of linearizability because his read started after the write completed. If the reads truly overlap in time, it's okay for the system to order them one way or another. The key is that whatever ordering the system picks, all clients must observe that same ordering for consistency. Linearizability gives developers an intuitive model. You don't need to worry about chasing distributed replica states. That simplicity reduces subtle bugs and makes correctness arguments straightforward. Providing linearizability typically requires coordination, for example, leader election, consensus, or synchronous replication, which can increase latency and reduce availability under failures. System designers must balance the need for strict correctness against performance and fault tolerance goals. Here's a simple flow. The client sends a read or write to replicas. Replicas may forward writes to a coordinator, a leader, or consensus group, which decides the order and ensures replication. Once the write is acknowledged, all subsequent reads must reflect it. If a read reaches a replica that is still lagging behind the acknowledged write, that read can return stale data and break linearizability. When choosing a consistency model, ask whether you need the strong, intuitive guarantees of linearizability. If yes, accept the coordination cost. If low latency and high availability are more important, choose a weaker model but test carefully. In either case, include tests that exercise real-time precedence and overlapping operations so you can catch violations. Linearizability is the idea that a distributed object behaves as if there were one canonical copy. Informally, whenever a client performs an operation, it appears to happen instantaneously at some moment between when the client sent the request and when it got the response. That simple mental model, the single copy illusion, lets clients reason about shared data as if there were no replicated copies or network delays. To reason about timing, we model each operation as a horizontal bar from the time the client sent the request to the time it received the response. Because of network and server delays, the true moment the system applied the operation lies somewhere inside that bar. We don't know exactly where, only that it must be between send and receive. Let's make this concrete. Suppose we have a single key X starting at 0. Background job C issues write X1, while two clients, A and B, are repeatedly reading X. From the client's perspective, we can only observe when each read or write was sent and when it completed. From linearizability's standpoint, any read that completed before the write even began must see the old value 0. Any read That overlapping case allowance creates a potential problem. Different overlapping readers might see values that flip back and forth. If the system truly presented a single copy, once the new value becomes visible, it should never revert for later readers. Linearizability enforces this monotonic visibility. Once a read returns 1, any read that starts later must also return 1. Formally, linearizability assigns to every operation a linearization point, one instant inside its request interval when the operation took effect. Reads return the value of the most recent write according to these points. And crucially, the chosen points must respect real time. If operation O1 completed before O2 began, O1's linearization point must be earlier than O2's. A helpful way to picture this is to draw each request as a bar on a timeline and place a single dot inside each bar where it took effect. If you then read the dots from left to right, you get a sequential ordering. That order must make sense. Reads must see the most recent preceding right. Compare and set operations must succeed or fail according to the value at their dot. Now add compare and set, CAS. A CAS succeeds only if the register's value at the CAS's linearization point equals the expected value. When many operations overlap reads, writes, CAS, the system may choose any ordering of their linearization points consistent with real time. That chosen ordering determines which CAS succeed and which fail, modeling interference between clients. A few practical corollaries: the system can reorder only operations that overlap. Operations that are not concurrent must keep their real-time order. Also, because the linearization point can occur before the client receives acknowledgement, other clients may observe an effect before the originator's client sees its OK response. Finally, CAS is useful because it exposes concurrent interference. Some CAS calls will fail if another operation linearized earlier changed the value. How do we check linearizability? Tools record the exact send and receive times for every operation and attempt to place linearization points inside those intervals to form a valid sequential history. Searching for such an arrangement can be expensive. Many overlapping operations produce many possible orders, so practical tools use heuristics and pruning to manage the search. To summarize, linearizability gives us a reliable and intuitive mental model, the single copy illusion, by treating every operation as atomic at some point between send and receive. This ensures that once a new value is observed, later reads cannot see an older value, and it accommodates real network delays and concurrency while preserving a simple sequential reasoning model. Today we compare two related but distinct consistency guarantees you will see in distributed systems: linearizability and serializability. They both talk about ordering concurrent operations, but they mean different things and have different practical consequences. I'll walk you through definitions, examples, differences, and guidance for choosing between them. At a glance, both terms suggest arranging concurrent operations in some sequential order. The important point is that sequential order can be constrained in different ways. Linearizability ties the order to real time for single operations. Serializability only requires the final results look as if transactions ran one after another, but not necessarily in real-time order. Linearizability is a property of individual operations on shared objects. It guarantees each operation appears to take effect at a single instant between when it was invoked and when it returned. Crucially, that ordering must respect real time. If operation A completes before operation B starts, any linearizable system must order A before B. Write that phrase on the board and keep it in mind as the defining characteristic. For example, client 1 sets feature flag F equals true and receives an acknowledgement. If client 2 reads F after that acknowledgement, linearizability requires that client 2 sees true. If it reads false, the store is not linearizable. Use linearizability when immediate recency and predictability of single operations matter. Typical use cases include leader election, coordination services, feature flags, and primary metadata stores, places where clients expect a single write to be visible immediately to subsequent reads. Serializability is a transactional property that applies to sequences of operations grouped as transactions touching multiple objects. It requires that the outcome of concurrent transactions be equivalent to some serial execution of those transactions. The key is that the equivalent serial order need not respect the real-time order of events. Write that short note. To illustrate, in an e-commerce checkout, T1 reserves inventory and decrements stock while T2 reads stock to display availability. If the interleaved execution can be reinterpreted as some one-by-one ordering that produces the same observable results, the system is serializable, even if that serial ordering places T2 before T1 in time. Summarize the main contrasts. Scope: linearizability applies to single operations, serializability applies to multi-operation transactions. Real-time constraint: linearizability enforces it, serializability does not. Strength: because of the real-time requirement, linearizability is stronger for single operation recency, while serializability focuses on transactional correctness across multiple objects. A concrete divergence: client A writes X equals 1 and receives an acknowledgement, then client B reads X, linearizability requires B sees 1. Serializability alone does not guarantee that B sees 1, serializability only guarantees there exists a serial ordering of transactions that explains results, which might place transactions in a different order than wall clock time. This can produce surprising anomalies if you expect recency. There is a stronger transactional guarantee called strict serializability, or external consistency. It's simply serializability plus the real-time requirement. In other words, the equivalent serial order must respect wall clock order of transaction completion. This is essentially the transactional analog of linearizability and gives both isolation and recency guarantees. How to choose: pick linearizability when single operation recency and predictable read after write behavior matter. Pick serializability when correctness across multi-object transactions is the priority and you can tolerate a serial order that doesn't match real time. Pick strict serializability when you need both transactional correctness and real-time intuition, but accept the additional coordination, latency, and availability costs. Both linearizability and strict serializability generally require tighter coordination, which increases latency and reduces availability under network partitions, compared to weaker models. Systems offering just serializability can sometimes be faster by allowing more flexible ordering, but that flexibility can cause confusing anomalies for users hoping for immediate recency. Linearizability: each operation looks instantaneous and respects real time. Serializability: transactions behave as if run in some serial order, not necessarily respecting real time. If you need both, look for strict serializability or external consistency, and weigh the performance trade-offs. I'll read the decision flowchart you can copy to the board. Start dash do you need single operation recency and real-time reads? Dash yes dash use linearizability. Dash no dash do you need multi-object transactional correctness? Dash yes dash use serializability. If you also need real-time order for transactions dash use strict serializability, external consistency. Dash if you can tolerate weaker recency and want better performance dash consider weaker consistency models. This simple path helps you pick the right guarantee for your use case. Today we'll study serializability, the core isolation property that makes concurrent transactions behave as if they ran one after another. We'll see what it means, why it's useful, and how systems preserve correctness while allowing concurrency. Serializability means, even if transactions actually interleave their reads and writes, the final result must be indistinguishable from some sequential execution where each transaction ran to completion before the next started. Transactions can touch many objects, rows, documents, keys, but the system must ensure the combined effect equals one valid serial order. Think of serializability as a promise about what applications observe. The database may pick any serial order that preserves correctness. It doesn't have to reflect the exact real-time ordering. That freedom lets concurrency control mechanisms optimize throughput while still offering a simple correctness model developers can rely on. Imagine an online store where T1 processes an order in decrements inventory, and T2 restocks an increments inventory. If T1 and T2 run concurrently, serializability ensures the final inventory equals either doing T1 then T2, or T2 then T1. It prevents weird outcomes, for example, a lost update or a partially applied change that would not correspond to any serial ordering. Here's a simple flow to picture how serializability works. Transactions start and their operations may interleave. The concurrency control layer observes accesses and records conflicts or dependencies. Based on that information, it selects a serial order that preserves correctness. When transactions commit, the system ensures the applied changes produce the same final state as that chosen serial order. Serializability matters because it simplifies reasoning about concurrent programs. Developers can reason as if transactions ran one at a time, which makes it much easier to maintain invariants such as account totals or inventory limits. At the same time, databases can optimize internally reordering or interleaving operations as long as the observable result matches some serial execution. Databases provide serializability using different techniques. Two-phase locking enforces order by holding locks. MBCC keeps multiple versions so readers don't block writers. Optimistic schemes let transactions run and validate at commit time. Each approach trades off performance, complexity, and contention behavior. A practical checklist: assume transactions behave as if serial, identify the invariance your app depends on, test your workload for concurrency anomalies, and pick a database or isolation level that gives you serializability if your application requires these guarantees. To summarize, serializability is the fundamental correctness guarantee for concurrent transactions. It requires that the outcome of any concurrent execution matches some serial order. That prevents anomalies, simplifies reasoning about invariance, and still permits the database to use concurrency internally to improve performance. Today we'll unpack two important correctness notions in distributed systems: linearizability and serializability. We'll see what each guarantees, where each can fail, and what developers must do to get the behavior they need. Linearizability is a per-object guarantee about recency. In plain terms, each read or write on a single object appears to take effect at one instantaneous point between when it was called and when it returned. That means once a write completes, any later read of the same key or register should see that write, or a later one. It's a strong and intuitive guarantee for single-object operations. A crucial limitation is scope. Linearizability applies per object. It does not magically bundle multiple operations across different objects into one atomic action. So it can't by itself enforce multi-object invariance. Imagine two microservices that each update a different key in the same customer profile. Each key is linearizable, so reads of each key see the latest write. But there's no guarantee the two related updates appear together in a single, consistent state. If both services read each other's keys and then write based on those reads, they might both act on stale information and produce an inconsistent combined state. This classic anomaly is called write skew. To prevent such multi-object anomalies, you must make potential conflicts explicit. That means changing the data model or protocol so concurrent operations can tend on the same object, which the system can then serialize. Examples include using a shared lock, a single coordinating key, or an explicit version check like compare and swap on a combined representation. These approaches turn implicit cross-object races into real conflicts the system resolves. Serializability is about transactions. It gives the illusion that transactions executed in some sequential order. That protects multi-object invariance because each transaction sees a consistent view and effects appear atomic. When a system provides serializability and also respects per-object real-time recency, linearizability, the combination is called strict. For example, classic two-phase locking in systems that run transactions one at a time typically enforce a single real-time consistent order. They therefore maintain recency per object while giving serial transaction semantics. But not every serializable approach is linearizable. Serializable snapshot isolation isolates readers by giving them a frozen snapshot. That snapshot can omit writes that completed after it was taken, so reads under SSI may not reflect the latest writes. Consider a long analytics scan running on a snapshot while checkouts occur. SSI lets the analytics query proceed without blocking checkouts, but that query might miss purchases that just finished. A linearizable read would see those recent purchases. If your application needs the strongest real-time visibility, for instance to enforce strict inventory constraints across services, you must choose protocols that guarantee linearizability or explicitly coordinate the operations that must be atomic. Stronger guarantees often cost you in latency, throughput, or implementation complexity. Making conflicts explicit or using stricter locking can reduce anomalies but may increase contention and slow the system. Here's a short checklist to guide design choices. 1. Identify invariants that span multiple keys. 2. If they exist, ensure conflicting ops contend on the same object or run inside serializable transactions. 3. Decide whether you need real-time recency, if so, require linearizability. 4. Accept the trade-offs or redesign the data model to avoid cross-object races. To summarize with a small flow, first ask, do I have invariants across multiple keys? If yes, make those updates transactional or make conflicts explicit. Next ask, do I need the latest writes visible immediately? If yes, require linearizable reads. If you need both, aim for strict serializability or design explicit coordination that provides both properties. Linearizability guarantees per-object recency but not multi-object transactional safety. Serializability guarantees transaction-level correctness but does not always give real-time recency. Strong correctness requires making trade-offs explicit, either change concurrency control, locks, says, single writer keys, or adjust the data model so conflicts are visible and can be serialized. Today we'll focus on linearizability, what it is, when you need it, and concrete modern examples where weaker consistency would cause harm. We'll walk through definitions, real-world cases, a simple textual flowchart of how linearizability works, trade-offs, and implementation pointers. Linearizability means every operation on a shared object appears to take effect instantaneously at some point between its invocation and its response, and those instantaneous effects respect real-time ordering. In plain words, if client A finishes an operation before client B starts another, then everyone must see A's result before B's. Emphasize the two parts. The operation has an atomic instant where it takes effect, and those instants are ordered by real time. That ordering must be visible to all observers. This gives a single global timeline of visible state changes. Eventual consistency allows temporary divergence. Different clients may see different states for a short time before they converge. Linearizability disallows that kind of transient inconsistency for operations that must be immediately visible. Many user-facing features tolerate small, transient staleness, like counters, newsfeeds, recommendation rankings, and live scores often do fine with eventual or bounded staleness models because slight delays don't break invariance or safety. Now we'll go through specific domains where even milliseconds of stale or out-of-order state can cause real problems: finance, inventory drops, reservations, coordination, trading, access control, and safety-critical systems. Why it matters: account balances, transfers, and settlements must not permit double spending or show inconsistent balances to different clients. Example: a mobile banking app and an ATM cannot both allow withdrawals that together exceed the balance because a transfer hasn't propagated yet. Legal and audit requirements often mandate strict consistency. Why it matters: to prevent oversells and preserve fairness, stock views must be immediately consistent. Example: during a limited edition sneaker drop, linearizability ensures the last pair cannot be sold twice because one server hasn't yet recorded the sale. Why it matters: seat assignments, hotel rooms, and ride bookings must remain unique and conflict-free. Example: airlines and ride-hailing platforms need to avoid double booking a seat or driver when many clients try to reserve the same resource concurrently. Why it matters: protocols that elect leaders or allocate exclusive access depend on a single agreed ordering to make progress safely. Example: a cluster manager uses linearizable locks so only one node performs a schema migration at a time. Why it matters: order matching, settlement, and regulatory reporting require deterministic ordering to avoid financial loss and legal exposure. Example: an exchange must present the same sequence of bids and trades to all participants to prevent arbitrage and disputes. Why it matters: permission changes or revocations must be recognized immediately to prevent unauthorized access. Example: when an admin revokes credentials, that revocation should be honored instantly across all services to avoid security breaches. Why it matters: sensor updates and actuator commands have real-world consequences. Stale or reordered commands can be dangerous. Example: in an automated factory line, an emergency stop must take effect globally and immediately to prevent injury. Linearizability typically requires coordination, consensus, or synchronous replication, which increases implementation complexity, raises latency, and can reduce availability under network partitions. Use it when invariance, laws, safety, or money demand strict ordering, otherwise consider weaker models for performance. Use linearizability if correctness or legal compliance depends on strict ordering, operations change scarce or financial resources, you need global agreement on operation success/failure, or stale reads would compromise security or safety. Common ways to get linearizability include consensus algorithms like Raft or Paxos, single leader replication with synchronous commits, and transactional systems that serialize conflicting operations. Each has different operational costs and failure modes. Text flowchart: client invokes operation-request reaches replicas/leader- a single linearization point is chosen, consensus or leader commit -effect becomes visible to all -client receives response. That linearization point is the instantaneous moment the operation takes effect for everyone. In short, pick linearizability when application invariance, business rules, or safety requirements demand that every client share a single immediate view of state. For many other features, weaker consistency models give better performance without sacrificing correctness. Today we're studying a critical idea for replicated systems: ensuring there is exactly one active leader at any time. I'll explain why that matters, how we implement it in practice, and the pitfalls to avoid. First, the fundamental correctness requirement: single leader replication depends on a simple guarantee: at any moment there must be exactly one active leader. If that guarantee fails, the system can accept conflicting updates and break safety. When multiple nodes simultaneously believe they are the leader, we call that a split brain. In a split brain scenario, two leaders can accept different updates for the same data, producing inconsistencies that are hard to recover from. A pragmatic way to enforce a single leader is to treat leadership like ownership of a distributed lock. Every node that starts up tries to acquire the lock, the node that wins becomes the leader and others remain followers. Not every lock implementation works here. We require linearizability: all clients must see lock acquisitions and releases as if they occurred in a single global order. Without linearizability, two nodes might both believe they hold the lock at once, defeating leader uniqueness. In production, teams usually rely on coordination services that provide linearizable primitives. Systems like Zookeeper and ECT are common because they implement consensus under the hood and expose operations that appear instantaneous and globally ordered. Because the details of correct usage are subtle, higher-level libraries exist. For example, Apache Curator offers recipes and helpers to simplify correct leader election and distributed locking, reducing the chance of developer mistakes. One important subtlety is fencing. When leadership changes, a previously failed leader might be slow to realize it lost leadership. Fencing attaches monotonically increasing tokens or sequence numbers to the lock. External resources respect those tokens so stale leaders cannot override the new leader's actions. Distributed locking also appears in shared disk databases. Oracle Real Application Clusters implements fine-grained, linearizable locks at the disk page level so multiple nodes can safely share storage. Because these locks are on the transaction-critical path, RAC often uses a dedicated low-latency interconnect to keep arbitration fast and predictable. Here's a simple flow to picture. When a node boots, it tries to get the lock. If it succeeds, it becomes leader and gets a fencing token before serving requests. If it fails, it remains a follower and watches the lock. When the leader fails or its lease expires, the lock becomes available. The next node that acquires it receives a higher fencing token, ensuring external resources can distinguish fresh leaders from stale ones. To summarize, electing a single leader by locking is straightforward in concept but requires a foundation that gives linearizable operations and careful failure handling. Coordination systems built on consensus provide that foundation, and fencing plus higher-level libraries make the overall solution robust and practical in real-world conditions. Today we explore why some uniqueness guarantees in distributed systems require linearizability. We'll look at examples, an intuitive analogy, the failure modes when you don't have it, and when you can get away with weaker guarantees. Many systems must keep certain values unique. Think of a username on a social app, the email tied to an account, or a file path in cloud storage. These values serve as identifiers, and duplicates create serious problems for correctness and user experience. If two clients try to create the same identifier at the same time, the system must make sure only one succeeds. That requires a deterministic, real-time resolution so the outcome is consistent no matter which node processes the requests. Linearizability gives us that single truth. It makes each operation appear to happen at a single instant, and every operation is ordered globally. Because of that ordering, if two claims race, one will be seen as happening first and the other will see the updated state and fail. A helpful analogy is compare and set or acquiring a lock on the name. The operation is, set this username to user X if it's not already taken. That atomic check and set is exactly what you need to prevent two winners when requests race. If two requests race in a linearizable system, linearizability ensures one appears first in the global order and succeeds. The later one, seeing the name already taken, fails. This is what prevents duplicate claims in real time. Without linearizability, you can lose that up-to-date truth. Two nodes might both think the name is free and both accept a claim, producing duplicates. The same problem breaks invariants like non-negative balances or accurate inventory counts. This requirement shows up in many domains. To keep an account balance non-negative, prevent selling more items than exist, or avoid double booking a seat, you need a single authoritative value that every node agrees on at the moment of update. Linearizability gives you that. However, some applications tolerate a looser approach. Airlines overbook and then reaccommodate passengers. Shops may temporarily oversell and later refund or discount. If you can accept corrective actions and customer remediation, strict linearizability may be unnecessary. Note that many database constraints don't require linearizability. Structural rules like foreign keys or attribute validations can often be enforced with weaker consistency or at the application level. The key distinction is whether violations are tolerable and correctable. Here's a simple flow to visualize it. First, two clients submit claims. The system orders those operations globally. The operation placed first in that order succeeds and updates the authoritative state. The later operation sees the updated state and fails. This ordering is what prevents duplicates. In practice, you must weigh strictness against availability and performance. Choose linearizability when uniqueness violations are unacceptable and must never happen. If you can tolerate corrective measures or compensation, weaker consistency models can offer better availability. In short, linearizability enforces a single, instantaneous truth. Use it for hard uniqueness guarantees, otherwise consider the trade-offs. Today we will study a subtle but important class of bugs that show up when related state moves across two different channels. I'll use a simple human analogy and then map it to a common modern web pipeline so you can recognize the problem and learn practical fixes. Imagine two people editing a shared scoreboard during a video call. One person updates the scoreboard system, but before the system finishes, they shout the new score over chat. The listener now has two different signals, the spoken score and what the shared scoreboard shows. If those disagree, the listener detects an inconsistency that the system alone would never reveal. That extra, uncontrolled communication channel, voice or chat, surfaces the violation. A concrete example is a photo upload pipeline. The user uploads a large image. The web server writes the image into durable file storage and then sends a small resize instruction to a message queue. A separate resizer service consumes that instruction, retrieves the big image from storage, creates a thumbnail, and writes the derived thumbnail back to storage or a CDN. This split keeps the message queue small and efficient while the file store holds the large binary. We split responsibilities because message brokers are optimized for tiny control messages, not multi-megabyte blobs. The web server therefore writes the heavy object into the file store and queues only a pointer. This pattern is common and sensible from a performance and cost perspective. A race appears when the message queue and the file store do not present a single, consistent view of recent operations. The queue might deliver the resize instruction immediately, and the resizer might fetch the object straight away. If the storage hasn't yet made the latest write visible to reads, because of replication lag or eventual consistency, the resizer can see an older version or no object at all. That creates a mismatch between the full-size object and the derived thumbnail. Linearizability is a strong consistency guarantee. Once a write completes, any subsequent read must see that write as if the operation happened at a single instant. If your file store is linearizable, the resizer will always observe the up-to-date object after the web server's write completes. Without linearizability, replicas or caches can lag and produce stale reads. When the resizer reads a stale or missing object, it can produce a thumbnail that doesn't match the final stored image, or it can fail because the object is missing or incomplete. Unlike a transient glitch, this can cause permanent inconsistency. Thumbnails derived from the wrong data remain published, and debugging this is hard because the message queue and storage each looked fine in isolation. Walk through the flow. The web server writes the object to file storage and then enqueues a resize message. The queue delivers the message to the resizer, which fetches the object from file storage and creates a thumbnail. The critical timing window is between the storage write becoming durable and visible, and the queue delivering the message. If the queue arrives earlier than the storage replicas converging, the resizer can read stale data. This is the cross-channel race. There are practical mitigations you can choose from depending on how much complexity and latency you can tolerate. I'll list and explain them one by one. The simplest reasoning model is to use a storage layer that guarantees linearizability. If the file store is linearizable, then once the web server's write completes and returns, any subsequent read by the resizer will see that write. This avoids the need for extra coordination, but linearizable services can be more expensive or higher latency depending on implementation. Include a version identifier or generation token with the resize message. The resizer fetches the object and checks the token to confirm it has the expected version. If it doesn't match, the resizer can retry or fail safely. This implements an explicit read-after-write check on the consumer side and makes stale reads detectable rather than silent. Delay sending the resize instruction until you receive explicit confirmation that the storage write reached the required durability or replication level. In other words, only enqueue the work when you know the object is visible to readers. This increases end-to-end latency but prevents the race at the source. If the objects are small enough, put the image payload directly into the queue rather than storing it separately. That removes the two-channel gap entirely because the control and the data travel together. This is only feasible for small images or thumbnails due to queue size and cost constraints. Use a strongly consistent metadata service or a single authoritative store that both the web server and the resizer consult for object readiness. For example, write a metadata record saying Object X is ready in a strongly consistent database and have the resizer check that record before fetching the file. This centralizes readiness information and avoids divergent views. For the strongest semantics, you can employ distributed transactional techniques, two-phase commit or a transaction coordinator, to atomically publish both the object and the work item. This eliminates the window for inconsistency, but at the cost of significantly more complexity, operational burden, and latency. Each mitigation trades off complexity, latency, and cost against the guarantee you obtain. Linearizability is easiest to reason about if you can afford it. If you cannot, add explicit coordination like version checks or confirmations so downstream workers can deterministically detect and handle stale reads. The bottom line, whenever a workflow is split across two channels, one for heavy state and one for control messages, be deliberate about recency guarantees. If your storage doesn't provide linearizability, you must add coordination so that downstream workers do not act on stale or missing data. With those precautions, you can avoid cross-channel races and the confusing, hard-to-find bugs they produce. Today we'll study linearizability and how systems go from a single atomic copy to replicated designs that try to preserve that atomic illusion. We'll explore why the single copy idea is simple but fragile, and how replication adds complexity and trade-offs when we try to keep operations appearing instantaneous. Linearizability means every read or write behaves as if it happened at one exact instant. Even if state is stored on many machines, clients should be able to imagine a single atomic copy and reason about operations as instantaneous. The simplest way to guarantee linearizability is to have exactly one copy of the data and execute each operation on it. That makes correctness straightforward. There's a single place to serialize all operations. But a single authoritative node is fragile. If it crashes or becomes unreachable, the whole service can be down or data can be lost until the node is restored. For modern applications, that fragility is unacceptable. To survive failures, systems replicate data across machines. Replication ensures the service can continue even when some nodes fail, improving availability and fault tolerance. There are many replication approaches. Leader-based systems centralize updates through one leader. Quorum systems require overlapping sets of nodes for reads and writes. Primary backup is a simple active/passive pair. Chain replication orders updates along a chain. An asynchronous multi-master allows concurrent updates on many nodes. Each replication method makes trade-offs. Strong consistency often requires coordination that hurts availability or increases latency. Some designs tolerate more failures but add complexity, like conflict handling in multi-master setups. Replication can preserve linearizability, but it usually costs performance or availability. Leader-based synchronous replication and properly configured quorum systems can give linearizable semantics. Approaches that allow concurrent, asynchronous updates need additional coordination or conflict resolution to achieve the same guarantee. Think of the design path as a flowchart. Start with the single copy idea. If fragility is a problem, replicate. Choose a replication strategy, then evaluate the trade-offs for consistency, availability, latency, and tolerated faults. If you require linearizability, lean towards synchronous leader replication or majority quorums with stricter coordination. If you can relax consistency, you may opt for techniques that favor availability. To summarize, linearizability gives a strong, intuitive correctness model. A single copy is the easiest way to get it, but it's not resilient. Replication brings resilience but makes preserving the linearizable illusion harder. You can achieve linearizability with certain replication choices, but expect costs in coordination, latency, or availability. Today we will examine how single-leader replication can fail to provide the strong consistency guarantees many engineers expect, and what causes those failures. First, recall the basic architecture. One node acts as the leader and receives all client writes. Other nodes, called followers, keep copies of the leader's data by replicating its updates. This centralizes write coordination and simplifies some aspects of replication. If clients always read from the leader or from followers that are synchronously updated, the system can present a strong form of consistency to clients, namely linearizability, because reads observe the latest committed state. Linearizability means every operation looks as if it took effect at a single instance somewhere between when the client called it and when it returned. If that holds, all operations can be placed in a single global order that respects real time. Important caveat: having a single leader doesn't guarantee linearizability. Some systems choose different isolation or ordering semantics, like snapshot isolation, to improve throughput. Under those semantics, reads may return a consistent snapshot that is not the absolute latest write, and some interleavings of transactions that violate linearizability are allowed. Also, implementation bugs or improper concurrency control can break linearizability even when the architecture should support it. A second caveat is leader identity. Distributed systems face network partitions, message delays, and crashes. These can cause multiple nodes to think they are the leader, a split brain. If a delusional leader continues to accept requests, it can introduce conflicting writes. Asynchronous replication can make this worse. A leader might acknowledge a write before followers have it, then fail, and a promoted follower may not have that write, causing lost commits and breaking linearizability from clients' viewpoints. Let me walk you through a simple flow. The leader receives a write and applies it, then often acknowledges the client. That write is sent to followers asynchronously. If the network delays or drops those replication messages, followers may lag. If the network partitions and another node becomes delusional leader, it can accept different writes. The outcome can be two divergent histories, or, if the original leader's acknowledged write never reached a majority, an acknowledged write that later disappears when a follower is promoted. A concrete example: a payment system with two nodes that each think they are leader during a partition. Each accepts a withdrawal for the same account. Without majority elections or fencing, clients can see inconsistent balances or transactions applied twice, a clear violation of linearizability and correctness. Another example is a global configuration store. An operator updates a configuration on the leader and immediately queries a follower in another availability zone that is updated asynchronously. The follower may return stale data, surprising components that expected the update to be immediately visible. Operators and engineers use several practical mitigations. Enforcing majority quorum or using consensus for leader election prevents split brain. Synchronous replication for critical replicas ensures followers reflect committed writes before the leader acknowledges. Leader leases or fencing tokens stop old leaders from accepting requests after they've lost authority. And you must deliberately choose isolation levels, knowing their consistency trade-offs. To summarize the conditions under which single leader replication actually gives you linearizability, the system's isolation and concurrency controls must permit real-time ordering, clients must read from nodes that reflect the latest committed state, and the system must reliably know and enforce who the leader is. If any of these fail, you can get stale reads, lost writes, or split-brain anomalies. Final takeaways: don't assume single leader equals strong consistency. Understand your database's isolation model, design your read paths with freshness guarantees in mind, and make leader election and fencing robust. These steps will reduce the risk of the leader lying to clients and causing hard-to-find consistency bugs. Today we'll explore why consensus protocols, while they can look like simple single-leader replication, actually include extra safety rules that prevent split brain and stale reads, and so enable linearizable storage across a distributed system. At first glance, consensus systems resemble single-leader replication. A designated leader accepts client rights and replicates them to followers. That image helps intuition, but it doesn't capture the safety machinery under the hood. Two core problems threaten correctness: split brain, where more than one node can mistakenly think it's leader after partitions or timing issues, and stale replicas, where lagging followers could serve out-of-date reads. Consensus protocols are explicitly designed to stop both. Leader election in consensus is guarded by majority quorums. Requiring a majority to elect or confirm a leader means any two quorums overlap, so you can't have two disjoint majorities simultaneously believing in different leaders. This rules out concurrent authoritative leaders. Consensus algorithms attach monotonically increasing terms or epochs to elections and log entries. A higher term denotes a more recent leadership era. Nodes will reject actions from lower terms. This prevents an older, partitioned node from resuming leadership or applying stale operations. Rights are tracked in a durable, ordered log. An operation isn't considered committed until it's durably recorded and replicated to a majority. Tying reads and writes to the committed log ensures everyone agrees on the order and that followers can't return obsolete data. Leader fencing mechanisms stop old leaders from serving requests after they've been superseded. Examples include lease checks, commit index comparisons, or requiring leaders to hold a current term. Fencing verifies that only the genuine, current leader can make progress. These mechanisms work together. Majority quorums ensure uniqueness, terms provide recency, durable logs ensure a consistent committed order, and fencing blocks obsolete actors. Together they prevent split brain and stop stale state from leaking into client responses. Because of these safeguards, consensus protocols can provide linearizability. Every operation appears to take effect at one instant between its invocation and response, and all nodes agree on the operation order. That gives the strong consistency semantics many services require. You see these ideas in production. Raft is used for Kubernetes configuration, Zookeeper, Zab, coordinates services, and systems like CockroachDB and Consul rely on consensus to keep metadata and configuration consistent. Here's a simple write path you can picture. Client leader. Submit write leader appends to its log leader replicates entry to followers majority acknowledge leader marks entry committed leader applies to state machine and response to client. The commit only happens after the majority step. And a simple election flow. Detect failure or timeout start election with higher term send vote requests to peers grant vote if candidate is up to date in term as current candidate wins if it gets majority new leader begins serving. The term and majority checks prevent split brain. In short, consensus may look like single leader replication, but the additional rules, majority quorums, increasing terms, durable commits, and fencing are what prevents split brain and stale replicas. Those rules are precisely what let production systems provide safe, linearizable storage. Today we're going to unpack why running multiple writable leaders in a distributed system undermines linearizability. We'll define linearizability, show how multi-leader replication works, walk through a concrete example, examine conflict resolution strategies, and end with guidance on when this trade-off makes sense. Linearizability is the strong guarantee that every operation appears to take effect atomically at one instant on one authoritative copy of the data. In practice, this means every client sees results as if there were a single, perfectly ordered timeline of operations. Multi-leader replication lets several nodes accept writes at the same time and replicate changes to each other asynchronously. This design improves write availability and can reduce latency for geographically distributed clients, because writes can be handled locally. When more than one node accepts writes, there is no single chronological order that all participants immediately agree on. Two clients can update the same key on different leaders around the same time, and because replication is asynchronous, each leader can observe a different sequence of events for a while. That temporal ambiguity creates divergent versions of the same data and therefore violates linearizability. Imagine an online store with two active writable regions, North America and Europe. A customer in North America places an order in decrements inventory via the North America leader. Milliseconds later, another customer in Europe purchases the same SKU in decrements via the Europe leader. Each leader applies its write locally and then sends updates to the other region afterward. Until replication completes and any conflict resolution logic runs, NA and EU have different inventory counts. There was no single instant when both regions agreed on the inventory, so the system is not linearizable during that window. Conflicts are the inevitable result of having no single authoritative copy. Systems that accept concurrent writes must detect and reconcile divergent updates. Common approaches include last write wins, which is simple but can lose data, application-level merge functions, which are precise but add complexity, versioning schemes like vector clocks to detect causality, and convergent replicated data types or CRDTs, which give deterministic merging for certain data models. Multi-leader replication is a deliberate engineering trade-off. It boosts write availability and lowers latency for geo-distributed or offline scenarios, but it increases operational burden and pushes complexity onto application logic for conflict handling. Choosing it means accepting eventual consistency and extra reconciliation work. Here's a simple flow you can picture. Client writes to leader A dash leader A applies change locally dash leader A replicates asynchronously to leader B dash meanwhile client 2 writes a different change to leader B dash leader B applies change locally dash replication completes dash system detects divergent versions dash run reconciliation strategy to converge. This sequence shows where the temporal ambiguity and conflicts arise. Choose multi-leader when low latency for local writes, high write availability across regions, or offline/partition tolerant operation are more important than having a single instantaneous global order. If strict linearizability is required, prefer single leader or consensus protocols like Paxos or Raft. Remember 4 core points. Multi-leader systems can accept concurrent conflicting writes. Asynchronous replication creates windows where nodes disagree. That disagreement breaks linearizability, and you must decide whether the benefits in latency and availability justify the added complexity of conflict detection and resolution. Today we'll examine a common claim that overlapping read and write quorums, W plus or greater than n, give you strong consistency. I'll show why that intuition is useful but incomplete, and how real systems can still violate linearizability despite quorum overlap. First, recall what quorum overlap means. If the number of replicas is n, and a write waits for W replicas while a read waits for R replicas, then W plus or greater than n ensures that at least one replica is in both the read and the write. That guarantees the read can see some replica that observed the write. Linearizability is stronger. Every operation must appear to take effect at a single instant, and those instants must respect real time. That means if client A's operation completed before client B started, every observer must see A as happening before B. It's about preserving actual event order, not just replica overlap. An overlapping replica only guarantees shared state, not that all observers will agree on the order events occurred in real time. Network delays, clock skew, and the way replicas resolve conflicts can create behaviors that cannot be mapped to any single global real-time ordering. A practical culprit is last write wins implemented with wall clock timestamps. Timestamps are compact and fast to compare, but they rely on clocks. If clocks disagree, two operations that happen in one real-time order can acquire timestamps that imply the opposite order. That breaks linearizability because the system's chosen ordering no longer matches real time. Let me walk you through a concrete scenario you can put on the board. Suppose 3 replicas, and both writes and reads require 2 responses. Client A writes V1 and reaches R1 and R2. R2 stores V1 with a timestamp of 100. Later in real-time client B writes V2 and reaches R2 and R3. But due to clock skew, V2 gets timestamp 90, which is earlier than 100. A read that queries R1 and R3 will see V1 on R1 and V2 on R3. If the conflict resolution rule is last write wins by timestamp, the system will choose the entry with the newer timestamp. Because clocks disagreed, that choice can contradict the true real-time order, and no single linearization point can reconcile what clients observed with real-time ordering. Here's that flow in a linear, textual flowchart. The key takeaway is that writes and reads touch overlapping replicas, but because timestamps can be inconsistent, the conflict resolution can pick an ordering that doesn't reflect the real execution order. That violates linearizability even though W plus R is greater than N. Another practical problem is sloppy quorums and hinted handoff, used to maintain availability during partitions. Writes may be stored temporarily on alternate nodes and replayed later to the intended replicas. That replay can reorder how replicas converge compared to the original client-perceived order. A reader can see a state that cannot be placed at a single instant respecting real-time. Even with strict quorums, many small implementation details decide whether the system is linearizable. How conflicts are resolved, how retries are performed, whether metadata like timestamps or vector clocks are compressed or truncated, all of these choices can destroy the mapping from overlapping quorums to linearizability. In short, quorum overlap is a useful safety property, but it is not equivalent to strong consistency in the linearizable sense. If you need linearizability, you must enforce a real-time respecting ordering mechanism, use a single linearizable leader or consensus protocols, avoid relying solely on unsynchronized clocks for ordering, and be careful with techniques like hinted handoff and metadata compression. Otherwise, expect surprising behaviors in the field. Today we'll examine why the simple quorum rule or plus W greater than N doesn't always guarantee linearizability in leaderless replication systems, and what practical trade-offs exist when you try to fix that. Start with the standard dynamo-style rule, R plus W greater than N. The intuition is that a read quorum intersects a write quorum, so a reader should always contact at least one replica that saw the latest write. Here's a small concrete setup we'll use. There are 3 replicas. The writer sends the update to all 3 replicas, W equals 3. Clients read by asking 2 replicas each, so R equals 2. Follow the events in time. The writer issues the update and sends it to every replica, but network delays mean replica 1 applies it first while replicas 2 and 3 are still old. Client A reads replicas 1 and 2, sees a 1 from replica 1 and returns 1. Shortly after A completes, client B reads replicas 2 and 3, both still have 0, so B returns 0. Notice that even though the quorum inequality is satisfied, the execution is not linearizable. A's read finished before B's read began, yet B observed the older state. The underlying cause is simply timing. Writes didn't reach all replicas before different overlapping quorums were queried. You can reduce or eliminate these stale read windows, but only at a performance cost. One option is synchronous read repair, when a reader finds divergence at updates lagging replicas before responding. Another is read before write. Writers first read a quorum to learn the latest state, then write a new value. Both force extra blocking work and so increase latency and reduce throughput. Important caveat: while synchronous techniques can make ordinary reads and writes linearizable, they don't give you a correct, linearizable comparen set in a leaderless setup. CIS must serialize competing updates cluster-wide. To do that reliably, you need a consensus protocol like Paxos or Raft, or a single leader to sequence operations. So what's the practical takeaway? If you truly need linearizability under concurrent operations, design with a leader or with consensus. If you choose a leaderless approach for availability or performance, be explicit in your design and documentation about the weaker guarantees so application logic can tolerate or avoid surprising stale reads. Here's a simple text flowchart to visualize delivery and reads. The writer pushes the update to all three replicas, but replica 1 applies it early while replicas 2 and 3 lag. Client A reads replicas 1 and 2 and therefore observes the updated value. Later, Client B reads replicas 2 and 3 and sees the old value. The sequence of results: A returns the new value, then B returns the old value, is exactly how linearizability is violated in practice. Today we'll explore a fundamental trade-off in distributed systems, linearizability versus availability, and how that trade-off becomes obvious during a data center network partition. I'll walk you through a simple two-region deployment and show how two common replication strategies behave when the link between regions breaks. Imagine two cloud regions, each running application servers and a copy of the database. Those regions normally send updates across a replication link so each copy stays in sync. Now picture the inside networks of both regions working fine, and clients still reaching their nearest region, but the link between regions is severed. Specifically, the partition we care about is when the inter-region link fails. Local clients can still connect to servers in their region with low latency, but the two database replicas cannot exchange updates. That simple change causes different replication designs to behave very differently. First, consider multi-leader replication. In this model, each region is a writable leader. Local clients read and write to their nearby leader. Replication to the other region happens asynchronously, so updates are queued and sent when the network returns. During the partition, multi-leader maximizes local availability and responsiveness. Users keep working as if nothing happened. The downside is you no longer have global linearizability. Clients in different regions can see updates in different orders, or even conflicting updates. Those conflicts need resolution later. To handle conflicts, you can use application-specific merge logic, adopt conflict-free replicated data types (CRDTs) that converge automatically, or use deterministic tiebreakers like last writer wins. Each approach has trade-offs in correctness and semantics, so pick one that matches your application's needs. Now consider single leader replication. A single region hosts the canonical leader that enforces linearizability. All linearizable reads and writes must be handled by that leader, so other regions forward operations to it. If the inter-region link fails, clients in the follower region cannot reach the leader, so they cannot perform linearizable operations. They might still read from the local replica, but those reads may be stale. In short, single leader preserves strong consistency but sacrifices availability for disconnected regions. Which model is right depends on your application. Multi-leader fits scenarios that prioritize responsiveness and can tolerate temporary divergence, think collaborative editing or social feeds. Single leader suits workloads that require immediate, global correctness, like bank balances or payments, where you'd rather be unavailable than risk anomalies. There are operational choices to reduce the pain of either model. For single leader systems, you can route clients to the leader region using DNS, a control plane, or client-side topology awareness to preserve availability for some clients. For multi-leader systems, you need robust conflict resolution, monitoring of replication backlogs, and testing of merge behavior. Hybrids are possible too. Place consensus groups across regions, accept higher latency, or shard data and assign leaders by partition to balance consistency and availability. Here's a simple flow. A client talks to its nearest region. With multi-leader, the local write succeeds immediately and is queued for cross-region replication. After the link is restored, updates merge and the system converges. With single leader, the follower must forward operations to the leader. If the leader is reachable, the operation is linearizable. If not, the operation cannot complete, or the client may accept a stale local read depending on the design. To sum up, multi-leader emphasizes availability and responsiveness at the cost of immediate global ordering and potential conflicts. Single leader enforces global linearizability but can become unavailable for any region that loses contact with the leader. Your choice should reflect whether your application can tolerate temporary divergence or must guarantee strict ordering and correctness. Today we'll talk about a fundamental tension in distributed systems. When the network becomes unreliable, you cannot simultaneously guarantee immediate consistency and continuous availability. This is not about a particular database design or deployment detail, it applies to any system that aims to be linearizable, whether it uses leaders, leaderless replication, shared storage, or shared nothing architectures. Put simply, a network failure forces a choice. You cannot have both perfect, immediate consistency and uninterrupted service when messages can be lost, delayed, or partitions occur. We must decide which guarantee to preserve in the face of such faults. Linearizability means every operation looks as if it happened at a single, globally agreed instant. If your application requires this guarantee, disconnected replicas cannot safely accept new requests while partitioned. Accepting requests could break the global single instant view of operations. When we insist on linearizability, replicas that lose contact with others must either stop processing new operations until connectivity is restored or return errors to clients. In practice, this is a sacrifice of availability. The system becomes unavailable for some operations during network faults. If the application can tolerate weaker guarantees than linearizability, replicas can continue to accept and process requests independently during a partition. This keeps the system available but means the global order seen by different replicas might diverge and require reconciliation later. Common approaches that preserve availability include multi-leader replication and leaderless designs where updates are accepted at multiple nodes and converge eventually. Techniques such as eventual consistency, causal consistency, and CRDTs are often used to reconcile changes after partitions heal. Partitions are not only a multi-data center problem. Network faults can occur anywhere, between data centers, across regions, or even inside a single data center because of bad switches, overloaded links, or flaky virtual networks. Any place with unreliable communication can surface the CAP trade-off. The CAP label, coined by Eric Brewer around 2000, summarizes this trade-off: you cannot simultaneously guarantee consistency, availability, and partition tolerance. CAP began as a rule of thumb rather than a formal proof, but its purpose is conceptual, to force architects to be explicit about which guarantees they value and how systems behave when the network misbehaves. CAP influenced the move away from shared storage cluster thinking toward shared nothing, highly distributed designs, and helped spur the NoSQL movement. In practice, engineers choose the model that fits their domain: strong linearizability for critical correctness, like banking or inventory, eventual or causal consistency for low latency, highly available services, like user timelines or feature flags, and hybrid methods where appropriate. Here's a simple decision flow. When a client request arrives, ask whether strict linearizability is required. If yes, the system must either block the request or return an error until nodes can coordinate that preserves consistency but reduces availability. If no, the system can accept the request locally during the partition and reconcile divergent states later. That preserves availability but gives up global linearizability. Designers use many tools to balance consistency and availability: quorum-based protocols that require a majority for some operations, conflict resolution rules, CRDTs for automatic convergence, or hybrid approaches that only require strict guarantees for a subset of operations. The right choice depends on which correctness properties your application cannot compromise. To summarize, network unreliability forces an unavoidable choice between strict consistency and continuous availability. CAP captures that core insight and encourages explicit design decisions. Use strong consistency where correctness is paramount, weaker models where availability and latency matter more, and hybrid techniques when you need a mix. The trade-off is fundamental, not an accident of implementation. Today we'll look beyond the catchy slogan "Pick 2" and understand what CAP really tells us and what it doesn't. We'll see why treating partitions as an optional choice is misleading, and learn the practical way to think about consistency and availability when networks fail. You have probably heard the one-line summary: consistency, availability, partition tolerance, pick 2. It's memorable, but it's also dangerously short. It suggests we can freely choose any two of the three properties, as if partitions were an optional feature we could turn off. In real systems, network partitions are not a feature, they're a fault. Links break, routers fail, regions get isolated. Any distributed system that's deployed in the real world must expect partitions at some point. So the real question is, what do we do when a partition happens? A clearer way to state the trade-off is this: a system can be either consistent or available when partitioned. That means once replicas or services are separated by a network fault, you must choose between preserving a single global order of operations, linearizability, or continuing to serve requests locally and possibly returning stale or divergent results. When we say consistent here, we mean linearizability. Operations appear to take effect instantaneously at some point between their invocation and availability, in the everyday engineering sense, means serving requests and staying responsive. If you favor availability during a partition, local nodes continue to accept and answer requests even without full coordination. That keeps the service running, but results may be stale, conflicting, or require later reconciliation. Important confusion comes from definitions. The formal CAP proof uses a strict definition of availability. Every request to a non-failed node must eventually get a response. Many systems marketed as highly available don't satisfy that strict property under partitions, but engineers still use the term. This mismatch leads to miscommunication and poor design choices if left unaddressed. The theorem itself assumes one consistency model, linearizability, and a particular fault model: nodes stay alive but become disconnected. It doesn't explicitly cover other realities like unbounded network delays, crash nodes, transient errors, or hybrid strategies. so CAP is precise but narrow in scope. In practice, you make choices based on the application's needs. For example, a globally distributed shopping cart may accept local rights during a region partition and reconcile conflicts later, prioritizing availability to keep shoppers buying. A financial ledger typically refuses rights when it can't guarantee a global ordering, prioritizing consistency to avoid lost or duplicated money. Both are reasonable choices for different requirements. Designers also care about other trade-offs: latency, how durable rights are, how reconciliation is performed, and how often partitions occur. Modern frameworks and impossibility results extend CAP by reasoning about latency, consistency trade-offs, and more refined fault models. These give more actionable guidance than the three-word mantra. Let's walk a simple decision flow. Start: the system is running. If no partition is detected, you can often provide both consistency and availability. If a partition is detected, you must choose. Option 1: favor consistency, reject or stall requests and wait for coordination, so everyone keeps a single correct view. Option 2: favor availability, accept local requests, which may create divergence that must be reconciled later. Each branch has costs and operational implications. To design robust systems, be explicit. First, define the consistency guarantees your application actually needs. Is eventual consistency acceptable, or do you require linearizability? Second, build a realistic fault model for your deployment. How often do partitions occur and what other failures matter? Third, choose trade-offs that include latency, durability, and reconciliation plans, and document them. Avoid leaning on pick 2 as a substitute for precise requirements and models. The final takeaway: CAP is historically important and highlights a real impossibility, but its popular summary is misleading. Treat partitions as inevitable faults, use the clearer phrasing, consistent or available when partitioned, and prefer precise definitions and fault models when making design decisions. Today we'll explore why linearizability, though a clean and intuitive correctness guarantee for concurrent systems, is often avoided in real systems, not because it's wrong, but because it costs time. I'll explain the hardware and theoretical reasons behind that cost and what engineers do instead. Linearizability means every concurrent operation looks like it happened instantaneously at some point between its invocation and its response, and if one operation completed before another started in real time, the real-time order is respected. That strong guarantee makes reasoning simple. You can think in sequential terms even when things run concurrently. Surprisingly few production systems give full linearizable behavior. The dominant reason is performance. Achieving linearizability often forces extra weighting or coordination, which raises latency and reduces throughput. We'll see where that weighting comes from. On modern multi-core machines, each core keeps its own caches and a store buffer. When a core writes a memory location, the update usually stays in that core's cache or buffer first. Other cores might still have older versions in their caches. Until the update is propagated and made globally visible, reads on other cores can return stale data. Imagine core A writes x equals 1, that write sits in A's cache or store buffer. If core B immediately reads x, B may observe the old value because its cache hasn't seen the update. This isn't a bug in hardware, it's a performance optimization. You only get immediate visibility if you use synchronization primitives like memory fences that force propagation. Caches and asynchronous writebacks are deliberate. They avoid slow trips to main memory, improving throughput and reducing latency in the common case. The trade-off is that multiple copies of data exist temporarily, which means the system doesn't present a single, instantaneous global view, hence loss of linearizability unless you pay extra coordination cost. It's tempting to call this a CAP-style trade-off, but that's misleading. CAP addresses availability versus partition tolerance in distributed networks. Inside a single machine, the issue is not partitions but intentional weakening of consistency to gain latency and throughput benefits. Distributed databases make similar trade-offs. They often choose weaker consistency to keep latency low, not just to tolerate partitions. There's a deeper, formal reason you can't get linearizability for free. Atiyah and Welch proved a lower bound showing linearizable operations need to incur weighting proportional to uncertainty in message delays. Intuitively, to make an operation appear instantaneous and globally ordered, implementations must wait long enough to rule out that some earlier operation is still in flight. When delays are variable or unpredictable, that weighting makes linearizable operations inherently slow, and no clever algorithm can avoid that. Think of it as a simple decision flow. When an operation occurs, you can either wait for global visibility, which enforces linearizability but adds latency due to coordination and fence costs, or you can return quickly, accepting weaker consistency and the risk of stale reads. If you return quickly, you typically need synchronization, compensation, or application-level strategies to preserve correctness in practice. Practically, engineers face a clear trade-off. If you demand linearizability, you must accept the latency tax, operations will be slower. If you relax consistency, you can get much better latency but must compensate with synchronization, conflict resolution, or application-level correctness strategies. For latency-sensitive systems, many choose the latter and design around weaker guarantees. In summary, linearizability gives simple, strong semantics but costs latency because of hardware design and fundamental lower bounds. Systems intentionally weaken consistency for better performance. The right choice depends on your application's latency requirements. If you relax consistency, plan to use synchronization, compensation, or application-specific techniques to maintain correctness. Later material will explore concrete strategies for doing that. Today we'll explore how ordering of events underlies many correctness properties in distributed systems. We'll connect linearizability, replication, transactions, clocks, and consensus and see why getting the order right matters. Linearizability means a shared object behaves like a single, real copy. Every operation appears to take effect instantaneously at one point in time. That simple seeming rule implies a powerful constraint: every operation must be placed in one global order. Because each operation has an instantaneous effect, we must be able to fit all operations into a single, well-defined sequence. If two operations overlap in time, the linearizable history still chooses a consistent order that respects real-time precedence. If A completed before B started, A must come before B in the sequence. In single-leader replication, the leader's main job is to establish a single order for writes. The leader turns incoming updates into a serialized replication log. Followers apply that same sequence so they end up consistent. This is why having one leader makes providing consistency simpler. If you don't have a single leader, for example with multiple masters or leaderless designs, different replicas can see concurrent writes in different orders. That can produce divergent states and requires conflict resolution or stronger algorithms to restore a single consistent ordering. Serializability for transactions means the outcome of concurrent transactions must look like some sequential ordering of those transactions. Systems achieve this by running transactions one after another, or by allowing concurrency with mechanisms that prevent conflicting interleavings, locks, optimistic checks that abort and retry, and other concurrency control techniques. Clocks and timestamps are another tool to impose order. Physical clocks rely on clock synchronization protocols or bounded uncertainty services like TrueTime to compare event times. Logical clocks, like Lamport timestamps and vector clocks, capture causality without needing physical time. Each approach trades off assumptions and the kinds of ordering guarantees you can provide. Think of ordering as a flow. A client issues an operation, the system assigns it a place in an order. This might be by a leader writing to a log, by attaching a timestamp, or by running a consensus protocol. The system replicates and applies operations in that agreed order, and finally clients observe the resulting state. Each stage is where correctness or failure modes can appear. Ordering, linearizability, and consensus are deeply connected. Linearizability demands a single global ordering that respects real-time precedence. Consensus protocols are the mechanisms that enable distributed processes to agree on one order or value. Understanding this link clarifies what distributed systems can guarantee and what they cannot without extra assumptions. In the next sections, we'll unpack these connections more formally and demonstrate how ordering underpins many core guarantees. We'll look at the algorithms that implement ordering, the limits imposed by asynchrony and failures, and the trade-offs system designers make when they choose leaders, clocks, or consensus. Today we'll study why ordering in distributed systems is not optional. It preserves causality. When ordering is violated, cause and effect breaks down and users or services see impossible states. I will walk you through concrete examples and the mechanisms we use to preserve causal order. The simple rule to remember is cause before effect. If an operation B depends on A, any view that shows B must also show A. Violating this leads to confusing and unsafe behaviors. Imagine a social feed where a reply appears but the original post is missing. The reply implicitly depends on the post. Systems that provide consistent prefix reads guarantee that you never see a reply without the post it references. The read view is a prefix of the ordered history, so causal dependencies are preserved. In multi-region replication, a create on one leader and an update on another can arrive out of order. The result can look like an update to a non-existent row. This happens when replication is asynchronous and messages overtake each other. Correct systems enforce that creates are delivered before dependent updates. There are three relationships between two events A and B: A happened before B happened before A, or A and B are concurrent. Happened before is a causal relation, later events may observe earlier ones. If A and B are concurrent, neither influence the other. Tools like vector clocks let us detect these relationships in practice. Here's a simple flowchart in text: A leads to B, and B leads to C. That chain means C depends on B and indirectly on A. If another event D exists with no arrows to or from A, then A and D are concurrent, they don't causally affect each other. These diagrams help reason about which events must be visible together. When a transaction reads a snapshot of the database, that snapshot should be causally coherent. If the snapshot exposes an effect, it must include the cause. Snapshot isolation gives a single consistent view corresponding to a point in time. All causal predecessors up to that point are visible, later effects are not. Violations like read skew show up when snapshots don't preserve causality. A classic write skew example: two engineers each check whether someone else is on call and, seeing they are, both remove themselves. If both transactions read the same snapshot that says the other is on call, they can both leave, violating safety. Serializable snapshot isolation detects the conflicting causal dependencies and prevents this anomaly. Think of a live score update pushed to an app while somebody in the room shouts the score. If the app later returns an older score to someone who already heard the shout, that's a causal violation. The shout depended on the announced score, so anyone who observed the shout should see that same announced score. Similar problems occur in multi-step pipelines where later stages lag behind. Causal order simply means cause comes before effect. Messages are sent before they can be observed. A read that influences a write must precede that write in any consistent view. Chains of dependent operations across nodes form the causal order of the system. A causally consistent system guarantees that when you see an effect, you also see everything that led to it. That avoids the confusing states we discussed. Snapshot isolation is one practical way to give clients a causally coherent view. Maintaining causal order matters because violating it breaks users' mental models, leads to incorrect decisions, safety violations, and subtle bugs. In safety-critical applications, on-call schedules, financial transactions, or coordinated state machines, preserving causality is essential. In practice, systems track causal metadata such as vector clocks or dependency lists, provide read guarantees like consistent prefix or causal snapshots, and use stronger isolation like serializable SI when anomalies are unacceptable. These choices trade extra metadata and possible latency for correctness and simpler reasoning. Before designing or debugging a distributed system, run this quick checklist. If an effect is visible, can its cause be seen? Could replication reorder dependent operations? Are concurrent writes detected and resolved? Is the snapshot view presented to clients causally coherent? Answering these will guide correct choices for consistency. Today we'll connect a simple mathematical idea, orders, to practical database consistency models. I'll explain total and partial orders, give concrete examples, and show how those ideas map to choices engineers make about consistency, availability, and performance. and order is simply a way to compare elements. It answers the question, for a pair of items, which one comes before the other? That basic idea is what we'll use to reason about how systems decide the order of operations. A total order means every two items are comparable. Given any pair, you can always say which one is earlier or larger. This produces a single global ranking of all items, which makes reasoning straightforward because there's one agreed sequence. For example, timestamps form a total order. If I give you February 1st, 2024 t 10 hours Z and February 1st, 2024 t 10 hours and 5 seconds Z, you can immediately tell which event happened first. That single timeline is what total ordering gives us. A partial order relaxes that requirement. Some pairs are comparable, others are not. You can say one precedes another only when there is a clear relation, like inclusion or causality. When no relation exists, the items are incomparable. Consider feature sets A equals, login, search, and B equals, search, analytics. Neither contains the other, so neither is greater or before the other. They are simply incomparable in that partial order. This distinction maps directly to database consistency models. Systems that impose a total order correspond to strong consistency guarantees. Systems that accept partial orders correspond to weaker, more available models where only some relationships must be preserved. When a system enforces a total order of operations, for example linearizability or strict serializability, all nodes observe the same single sequence of events. That simplifies correctness reasoning because the system behaves like a single atomic machine, but it requires coordination, locks, synchronization, or consensus, which increases latency and reduces availability under partitions. Weaker models, like causal consistency or eventual consistency, reflect partial orders. Only causally related operations must appear in the same order everywhere. Concurrent or independent operations can be seen in different orders by different replicas and reconciled later, which improves availability and performance. Practical example: two people edit different paragraphs of a document while offline. Their edits are concurrent, neither edit causally precedes the other, so a system with partial ordering can accept both and merge them later instead of forcing a single global order immediately. A simple decision flow. Start: do you need a single, system-wide order for correctness? If yes, choose strong consistency, total order, accept coordination cost. If no, and only causal relationships need order, choose weaker consistency, partial order, gain availability and lower latency. This helps translate requirements into design choices. In short, total orders make reasoning and correctness easier but cost coordination and availability. Partial orders boost availability and performance but require reconciliation logic and can complicate reasoning. When correctness demands a single global order, for example a bank transfer where sequence matters, use total ordering. When availability and low latency matter more and operations are often independent, prefer partial order models like causal or eventual consistency. Today we will study linearizability, the strongest intuitive correctness property for concurrent and distributed systems. We'll see what it guarantees, why it matters, common examples where it's required, and some practical trade-offs. At the core, linearizability says the system looks like a single, authoritative copy of data. Every operation reads, writes, updates appears to happen at one instantaneous moment in time. We call that moment the linearization point. Even though operations may run concurrently in the real system, their effects can be mapped to those single instance. More concretely, linearizability imposes a total order on all operations. That means we can list every operation one after another. Importantly, this order respects real time. If one operation finishes before another begins, the earlier one must appear earlier in the sequence. This requirement ties the abstract order to actual time, which is what makes the guarantee strong and intuitive. This gives a single timeline illusion. Clients can think sequentially, one operation after another, with no overlapping effects. Even though under the hood operations were concurrent, the client-facing story is simple and sequential. That makes reasoning about correctness much easier for developers. Why does this matter in practice? Because developers can use simple mental models, the kind they use for single-threaded code even when many clients interact concurrently. For example, imagine an online store inventory. If two checkout requests concurrently try to decrement the same item count, linearizability ensures the key value store presents a single serial sequence of updates. That prevents overselling when the sequential view would forbid both decrements. Many real systems need this guarantee. Distributed configuration stores like ect and console rely on it so that configuration changes are seen in a single consistent order. Payment systems and bank accounts need linearizability to avoid double spend or inconsistent balances. Coordination services, for example distributed locking and leader election in Zookeeper, rely on it so that locks behave as if there is a single global lock. There are trade-offs. Linearizability simplifies reasoning and gives strong safety guarantees, but it can be more expensive in latency and can reduce availability during network partitions. As a result, many systems accept weaker consistency models, such as eventual consistency, to favor low latency and partition tolerance. Still, for safety-critical operations like financial transactions or metadata coordination, linearizability is often the right choice. Let me draw a simple timeline to visualize linearization. Imagine client A starts an operation, we mark its linearization point, and then it completes. Client B starts later, its linearization point appears later on the timeline. If A finished before B started, A's linearization must be earlier. The key idea is that each operation has a single representative instant on the timeline, and the sequence of those instants forms the total order. To summarize, linearizability gives you a single total order of atomic operations that matches real time, turning complex concurrency into a simple sequential story for clients. It's invaluable for coordination and safety critical systems, but comes with practical costs that influence system design choices. Today we'll explore how causality, concurrency, and linearizability relate. The core idea is simple: causal relationships induce a partial order of events, while linearizability forces a single, total timeline. We'll work through definitions, contrasts, and real-world analogies so you can picture what concurrency looks like versus what a linearizable system guarantees. Start with the happens before relation. When one event causes or precedes another, we say there is a happens before link, a B. If a B, they are ordered by causality. This relation captures direct or transitive causal chains in a system. Two operations are concurrent precisely when neither one happened before the other. In other words, if there's no causal path from A to B or from B to A, then A and B are incomparable, they are concurrent. The happens before relation forms a partial order. That means some pairs of events are comparable because of causality, but many pairs are not, they remain unordered. So the history of events can look like a graph with edges showing causal links, not necessarily a single line. A total order is stronger, every pair of operations is comparable. If a system presents a total order of operations, then for any two operations you can say which one happened first. Linearizability requires this property for externally observable effects. Linearizability enforces a much stronger constraint. In a linearizable data store, every operation appears to take effect at a single, indivisible instant on one timeline. Practically, this means the system behaves as if requests were executed one after another on a single copy of the data, no ambiguity about which operation took effect first. Contrast that with true concurrency. A concurrent execution looks like branching, multiple interleaved sequences of events that may later merge. Operations on different branches are incomparable because no causal path orders them. Only when branches are reconciled do you get a single sequence again. Think of Git. A straight-line commit history corresponds to serial work. When multiple developers work in parallel, you get branches. Commits on different branches are concurrent, they have no causal ordering relative to each other until you merge. The commit graph mirrors causal dependencies. Parent links indicate ordering, separate branches indicate concurrency. Another example is collaborative editing. If two users type in different parts at the same time, those edits are concurrent because neither causally follows the other. A linearizable system would serialize those edits and decide in order. Other systems, like CRDTs or operational transforms, accept concurrency and reconcile changes without forcing a single global timeline. Draw a simple flow. Start splits into two branches A and B, which represent concurrent operations. They run independently and then they merge back together at reconciliation. On the board you can see that between start and merge there is not a single straight line. A and B are incomparable until the merge reconciles them. If we forced a linearizable order, we would instead choose either start AB merge or start BA merge as the single timeline. Remember the diagram from Chapter 5, it showed overlapping operations with arrows denoting causal dependencies. Those arrows define a partial order. Some operations are linked by causality, arrowed paths, while others sit on different branches and are therefore concurrent. It did not form a straight line total order. In short, causality induces a partial order of events. Linearizability demands a total order, a single timeline where each operation takes effect at one atomic instant. When a system guarantees linearizability, it eliminates observable concurrency by presenting one consistent sequence of operations. When a system permits concurrency, its history looks like a graph with branches and merges, and some events remain incomparable until reconciliation. Today we'll explore how linearizability and causal consistency relate, and why we might prefer one over the other in distributed systems. We'll look at definitions, an example with microservices, the costs of linearizability, and a practical middle ground, causal consistency. Start with linearizability. It means every operation looks as if it happened instantaneously at some point between when a client called it and when the client got a response. That gives a very strong, intuitive guarantee. No matter how the system is implemented, clients can reason as if operations happen in a single global order consistent with real time. An important consequence of linearizability is that it automatically preserves causality. If one operation could have caused another, every observer will see them in that cause then effect order. You don't need extra timestamps or markers to ensure those cause and effect orderings across components when the system is linearizable. Imagine a user action triggers two independent subsystems, an event stream like Kafka and an object store like S3. If both systems are linearizable, a read that happens after a write will necessarily observe that write on both channels. There's no need for the services to exchange causal markers. Linearizability hides that coordination and makes reasoning simpler for developers. That hiding of complexity is the major benefit. With linearizability, developers can think in straightforward cause and effect terms even when multiple channels or services are involved, because the consistency model guarantees those intuitions hold. However, enforcing linearizability across a distributed, geo-replicated system is expensive. It typically requires synchronous coordination, remote acknowledgements, consensus protocols, or locking. Those coordination steps add extra network round trips and waiting, which translates to higher latency. In wide area deployments that span regions, those coordination delays become significant. Worse, linearizability often reduces availability during network partitions or faults, because nodes must wait for slow or unreachable peers to agree before proceeding. These are exactly the scenarios common in real-world deployments. Causal consistency offers a useful middle ground. It captures the cause and effect property we care about. If A caused B, everyone will observe A before B, but it doesn't demand the heavy global synchronization of linearizability. Crucially, it's the strongest consistency model that can remain available without being slowed by remote network delays in the same way. In practice, causal consistency means clients can proceed based on local information and still see a view of the data that respects causal order. They don't need to wait for a global commit or consensus. That translates to lower latency and higher availability for many applications that only need causality, not full linearizability. Systems that implement causal consistency use several techniques to maintain causal order without global sync. They track dependencies between updates, propagate small metadata that encodes causal relationships, and resolve conflicts locally when possible. These techniques let systems preserve causality while avoiding the performance cost of full coordination. I'll walk you through this flowchart. A single user action writes to two places, an event stream and an object store. If both are linearizable, any subsequent read will see those writes. The system guarantees that. Under causal consistency, reads will see the writes as long as the causal dependency has been tracked and propagated to the reader. The system preserves the cause-effect relationship without global weights. Under weaker models, reads might not see one or both writes, breaking our causal intuition. Causal consistency is promising, but it isn't a silver bullet. There are practical challenges. The metadata used to track dependencies can grow large, systems must bound and manage the dependency state efficiently, and conflict resolution semantics need to be simple enough for developers to use correctly. These challenges explain why production adoption is still limited. So when should you choose causal consistency? If your application requires cause-and-effect ordering but can tolerate weaker guarantees than full linearizability, causal consistency can give big wins in latency and availability. It's a good trade-off when developers want intuitive behavior without the cost of synchronous, global coordination, provided they handle the extra engineering work around metadata and conflict handling. In summary, linearizability gives straightforward, strong guarantees that make reasoning easy, but it comes with a latency and availability tax in distributed settings. Causal consistency preserves the important cause-and-effect behavior for many applications while avoiding heavy synchronization, offering a practical middle ground. The right choice depends on your application's correctness needs and the operational realities of your deployment. Today we'll explore how distributed systems preserve cause-and-effect without requiring a single global order. We'll focus on the intuition and practical mechanisms behind causal consistency, enough to understand how real data stores keep events in a sensible order even when they are not fully linearizable. Causal consistency ensures that if one operation causally depends on another, every replica sees them in that order. It does not force a single total ordering for all operations, instead it enforces a partial order that reflects actual cause-and-effect relationships. Think of events as having a happen before relation. Some operations clearly follow from earlier ones, they are causally related and must be seen in that sequence. Other operations are concurrent, neither cause the other, so replicas can apply them in any order without violating the causal rules. When a replica receives an update, it checks whether all operations that causally precede that update have already been applied locally. If any predecessor is missing, the replica delays applying the new update until those predecessors arrive and are processed. Imagine Alice posts a photo and later Bob comments on it. Bob's comment implicitly depends on Alice's post. Causal consistency guarantees Bob's comment will never be visible before Alice's post at any replica. That preserves the intuitive story the users expect to see. In an online store, creating an order causes an inventory decrement. The decrement depends on the order creation. If a replica applied the inventory change before seeing the order, the system's state would be confusing or incorrect. Causal mechanisms prevent that ordering mistake. To decide causality, we need to know what a node had seen when it issued an operation. If a node observed value x before generating write y, then x is a causal predecessor of y. This is like digital forensics, we need recorded evidence of what was observed, not just wall clock timestamps. Distributed systems commonly attach compact causal metadata to operations. Version vectors or vector clocks capture a node's causal history. When a client issues a write, it often sends the version metadata of the reads it performed. The system tags the write with that context so replicas can tell which prior updates must be present first. A typical sequence: a client reads some data and obtains a causal context, it then issues a write including that context, the coordinator tags the update with the context, replicas that receive the update compare the tag to their local history. If a replica lacks any referenced versions, it buffers the update or fetches the missing versions, and only applies the update once all causal predecessors are applied. This idea resembles conflict checks in serializable snapshot isolation. When a transaction commits under SSI, the system verifies the versions it read are still current. Similarly, causal systems record which versions were observed so dependencies are explicit and can be enforced before installing new updates. Let's walk a small flow by text. Client reads state A client generates write Y with context. A client sends write Y with context to coordinator coordinator forwards Y to replicas with metadata replica receives Y. Check if A applied if yes, apply Y, if no, buffer or fetch A, then apply Y. This shows the dependency check and wait pattern at the heart of causal consistency. In short, causal consistency is about conveying and enforcing had-seen relations. By attaching compact causal metadata to operations and having replicas respect those metadata, systems maintain intuitive cause-and-effect behavior without full global synchronization. Remember the practical pattern: record what was seen, tag writes with that context, and delay applying updates until all causal predecessors are present. Today we will look at how causality in distributed systems can be captured compactly using sequence numbers from logical clocks. We'll see the problem with tracking every dependency, the simpler clock-based approach, how it preserves important causal relationships, and the trade-offs involved. Causality tells us which operations are influenced by earlier actions. In a distributed system, knowing these dependencies is fundamental to reasoning about correctness. If A caused B, then B must reflect A's effects. In practice, recording every causal dependency becomes expensive. Imagine a client that reads many pieces of state, user profiles, permissions, feature flags, and then performs one write. Do we record that the write depends on all those reads? Storing every read as an explicit dependency quickly bloats metadata and complicates management. Think about a social app user who reads several posts and then writes a comment. Instead of remembering every post the user read, we want a cheaper representation of the fact that the comment came after those reads. Explicitly listing all prior reads is costly. A compact solution is to assign each operation a sequence number or timestamp from a logical clock. This timestamp is not wall clock time, it is a number produced by an algorithmic clock, like a monotonic counter. Each operation gets a small, fixed-size identifier. Logical clocks yield a total ordering. Every operation gets a unique number, and any two numbers are comparable to decide which operation came later. We can design these clocks so that if A causally precedes B, then A's number is smaller than B's. The key property we want is that the total order respects causality. When a causally precedes B, we ensure seq A is less than seq B. For events that are concurrent, with no causal link, the clock imposes some arbitrary order, which is acceptable for many systems. With sequence numbers, the system reasons about dependencies and conflicts by comparing short numbers rather than managing long dependency lists. This makes checks efficient and metadata small, a big win for scalability. A natural place for this technique is single leader replication. The leader assigns an increasing counter to each write and appends them to a replication log in that order. Followers apply entries in the same log order, even if they lag. Applying writes in sequence preserves causal consistency relative to the leader. This approach trades some precision for practicality. Total ordering may impose order between concurrent events that don't actually depend on each other. But in exchange you get much smaller metadata, simple comparisons, and straightforward implementation, a trade-off often worth making in production systems. Here is a simple flow to visualize the idea. Multiple reads get sequence numbers in increasing order. When the client writes, the write receives a higher sequence number. The system can infer that the write comes after those reads simply because its sequence is larger, so it doesn't need to remember each read explicitly. To summarize, sequence numbers from logical clocks are a compact and practical way to capture causality. They produce short metadata, allow fast comparisons, and are easy to implement in replication systems. The main caveat is that concurrent events get an arbitrary order, but for many real-world systems that loss of precision is acceptable given the gains in scalability and simplicity. Today we'll examine how systems generate sequence numbers without a single leader, why those approaches scale, and an important subtlety: locally generated IDs can mislead us about causal order. We'll look at 3 common strategies, concrete failure scenarios, and how to fix the problem when causality matters. Many distributed systems need unique, roughly increasing identifiers for operations, for replication, conflict resolution, or ordering events. The challenge is to do this without centralizing every request through one leader, which would limit throughput and availability. A single leader that serializes every operation becomes a throughput and availability bottleneck. Leaderless approaches let nodes assign IDs locally, so the system scales with parallelism and survives individual node failures more gracefully. First approach: each node keeps its own counter. Variants include simple schemes like odd/even numbers per node, or embedding a node identifier into reserved bits so all values are globally unique. In practice, database shards often tag writes with a counter that includes the shard ID and increment independently. The problem is different nodes progress at different rates. If node B issues many operations quickly, its numbers can outrun node A. A later event on A can receive a smaller numeric ID than an earlier event on B. So numeric comparison does not reliably reconstruct causal order. Second approach, stamp each operation with the node's wall clock time. If clocks are precise and synchronized, timestamps give a convenient total order and are often used for last right wins conflict resolution in geo-distributed stores. But physical clocks can disagree. NTP drift, misconfiguration, or resolution limits mean a later action on a node with a fast clock can get a timestamp after an earlier action on a slow clock node, or vice versa. That leads to incorrect conclusions about which event happened first when systems rely on timestamp order. Third approach, pre-allocate disjoint ranges of IDs to nodes. Node A might get 1 to 1000 and node B 1001 to 2000. Each node consumes IDs locally until its block is exhausted and then requests another block from an allocator. This reduces coordination during normal operation. Blocks can invert causal order too. Suppose node B used IDs 1 to 1000 earlier, then node A receives 1001 to 2000 later. If A performs an action that happened after B's earlier action but receives a higher numeric ID, numeric ordering might still imply the opposite relationship and other interleavings. The allocation timing and usage patterns determine whether numeric order matches happened before. Here are relatable examples. In collaborative editing, two authors may make edits that merge logic resolves by numeric order. A causality mismatch can choose the wrong edit. In shopping carts, adding an item on one device and removing it later on another can produce the wrong final state if sequence numbers don't preserve causality. In cache invalidation, a stale entry can persist if numeric comparisons prefer the wrong action. Think of the flow like this: each node assigns IDs locally, then messages are merged or replicated. The system resolves conflicts using numeric comparison. If numeric order doesn't match the true happened before relation, the resolution step can pick the wrong winner. To preserve causality, you need mechanisms that encode happen before explicitly. Lamport timestamps let you order events consistent with causality but don't capture concurrency fully. Vector clocks record per node counters and can detect concurrent updates precisely, at the cost of O(n) metadata. Hybrid logical clocks combine physical timestamps with a small logical counter to get many benefits of both approaches while remaining compact. All of these add metadata and some coordination compared to blind local ID assignment. In summary, per-node counters, physical timestamps, and pre-allocate blocks are practical and scalable, but they do not guarantee that numeric order reflects causal order. If your application relies on correct event ordering, design for causality explicitly, use logical or hybrid clocks or another causality-aware approach, because simplicity and throughput come at the cost of potential ordering errors. Today we're looking at Lamport timestamps, a simple logical clock that helps distributed systems order events in a way that respects causality, without relying on a shared physical clock. In distributed systems, we can't depend on one wall clock to order everything. Yet many protocols need a way to say which event came before another, at least in a way that doesn't violate cause and effect. That's the problem Lamport timestamps address. A Lamport timestamp is a simple pair, an integer counter plus a unique node identifier. Each event gets one of these pairs. The counter captures local logical time, the node ID breaks ties so each timestamp is unique. Every participant, server, process, or client keeps a local integer counter and knows its own unique node ID. The counter starts at 0 and advances as events occur or messages are received. To decide which of two timestamps is later, compare the counters first. If they're the same, use the node IDs as a tiebreaker. This gives a total ordering across all events. The trick that makes Lamport timestamps respect causality is propagation. Whenever you send something, include the biggest counter you've observed. When you receive a message with a larger counter, move your own counter up to that value before making your next timestamp. This ensures timestamps increase along causal chains. Here's the practical algorithm you implement. Start counters at 0. When you do a local event or send a message, increment and attach your timestamp. When you receive a message, take the max of your counter and the received counter, then increment as you generate the next event. And make sure requests and responses carry the max you've seen so others can advance. Imagine a global chat. Client A reads a message from server 2 that carries counter 5. When it sends a new message to server 1, A includes that 5. If server 1 was only at counter 1, it raises its counter to 5 and then increments to produce 6 for the new message. That guarantees the new message's timestamp is after the 1A read, preserving the read-send causal relationship. Here's the flow laid out step by step. A reads and gets 5 S2. A sends and includes 5. Server 1 takes max, its counter, 5, becomes 5, then increments to 6. The outgoing message gets timestamp 6 S1. This is how the causal order is carried forward through messages. It's useful to compare Lamport timestamps with version vectors. Lamport timestamps are compact and always give a total order. They always say which event is later, but they can't tell you if two events were concurrent. Version vectors keep a counter per node, let you detect concurrency and true causal relations, but require more metadata and complexity. Remember the limitations. Lamport timestamps are logical, not wall clock times, and they can't reveal true concurrency. Use them when you need a low overhead way to produce a total order that respects causality, but not when you must detect whether two operations are concurrent. To wrap up, Lamport timestamps are a simple counter node ID scheme. The propagation rule, always sharing and adopting the max counter scene, makes timestamps grow along causal chains. They give a total order consistent with causality, yet they won't tell you if events were concurrent. Their simplicity and compactness make them useful in many distributed systems. Today we examine why Lamport timestamps, though useful, are not enough to enforce uniqueness in a distributed system. On the board I want you to see the short statement: Lamport timestamps produce a total order that respects causality. I'll explain what that means and why it still leaves an important gap. Lamport timestamps are built from logical clocks. Each node increments its clock when it does something in timestamps events. By comparing timestamps and breaking ties with node identifiers, you get a deterministic total ordering of events. Crucially, that ordering respects causality. If A happened before B, A's timestamp is smaller than B's. Let's make this concrete. Imagine two data centers, each getting a registration request for the same username, @Alex, almost simultaneously. Both nodes will assign timestamps to their local registration operations. If you could collect every operation from every replica and then compare their Lamport timestamps, you could pick the earliest timestamp and declare that registration the winner. This retrospective approach is deterministic and valid once the whole history is known. But the problem isn't the retrospective resolution, it's what to do in the moment. A data center receiving a registration request has to reply right away. At that moment, it cannot know whether a concurrent registration is in flight elsewhere, or what timestamp another node will assign. Lamport timestamps don't tell you that no unseen operation exists that ought to come earlier. To be certain that the local request truly wins, you would need to consult other replicas to ensure none can claim the same handle with a lower timestamp. If any replica is unreachable due to failure or partition, you face two unattractive options: block until replies arrive, giving poor availability, or answer immediately and risk making the wrong decision, violating the uniqueness constraint. This reveals the root cause. Ordering alone isn't enough, you need finality. Finality means that once an operation is delivered or accepted, no other operation can later be inserted before it. Lamport timestamps give a way to order events conceptually, but that order is only definitive after you have collected all operations. Without finality, you can't safely treat a local ordering decision as permanent. What you need instead is a protocol that guarantees finality: total order broadcast, also called atomic or consensus-based broadcast. Protocols like Paxos or Raft ensure that when an operation is delivered, every correct replica will deliver it at the same position in the global sequence. Delivery therefore implies finality. No unseen operation can later be inserted ahead of it. Here's a simple text flowchart to visualize the choices. DC1 gets a request and assigns a timestamp 5, DC2 assigns 4 at the same time. If DC1 must decide immediately, it can either block and ask others or accept and risk being later reversed. In a retrospective system, you collect both ops and then pick the lower timestamp, but that may require rolling back an acceptance. In a consensus-based system, the replicas agree on the global order before delivering, so the winner is fixed when the client gets a response. To summarize, Lamport timestamps are useful for producing a consistent conceptual ordering, but they do not give the real-time finalization necessary for immediate, safe decisions like enforcing uniqueness. When you need a single, finalized global sequence across replicas, use a consensus or total order broadcast mechanism. That gives delivery implies finality, avoiding incorrect local decisions, though it comes with the usual trade-offs in complexity and latency. Today we'll look at how ordering works in distributed systems, why a single leader is a simple way to get a global order, and what limits that approach introduces. On a single CPU core, ordering is trivial. The processor executes instructions one after another, so every operation naturally gets a unique position in a total order. We don't need extra protocols to agree on order because the core itself imposes it. In a distributed system, many machines execute concurrently and communicate over unreliable networks. There is no single clock or thread that all machines see, so getting all nodes to agree on one sequence of operations is difficult. Messages can be delayed, lost, or reordered, and nodes can fail. You can try to order operations by timestamps or sequence numbers assigned independently, but this is weaker than having a single authoritative sequencer. For instance, using timestamps to enforce a uniqueness constraint can fail under node crashes or clock uncertainty. Two nodes might believe different orders and a failure can produce a violation. Single leader replication gives a clean solution. Appoint one node as the sequencer, route all client requests to it, let it serialize them on a single thread, and replicate the resulting ordered log to followers. Because one actor assigns positions, the system has a simple global order. Common implementations include primary replica databases where the primary serializes writes, Kafka partition leaders that sequence messages per partition, and consensus systems like Raft where the leader appends entries to a replicated log with safety guarantees. Think of the flow like this: clients send requests to the leader assigns each request a position and appends it to an ordered log, followers replicate that log from the leader. The leader is the single point that defines ordering for that stream of operations. That convenience has two main costs. First, throughput is limited by what the leader can process. If the write rate exceeds the host's capacity, the leader becomes a bottleneck. Second, availability depends on the leader. If it crashes or becomes unreachable, the system needs a safe leader election and recovery process to avoid losing or duplicating committed operations. In distributed systems literature, this problem is called total order broadcast or atomic broadcast. Every non-faulty process must deliver the same sequence of messages in the same order despite failures and message delays. Practical solutions trade latency, throughput, and complexity. You can't have all properties for free. Engineers choose among several approaches. Partitioning gives multiple leaders each handling a shard, which scales but complicates cross-shard consistency. Multi-leader or leaderless replication increases parallelism but requires conflict resolution logic. Consensus algorithms like Paxos or Raft provide a replicated log with strong safety but add coordination cost. Timestamp-based systems, such as those relying on tightly controlled clock uncertainty, can provide global ordering but demand careful engineering to handle faults and clock skew. Concrete examples make the trade-offs clear. A single partition database primary serializes writes and is straightforward, but it hits a performance ceiling. Kafka sequences messages per partition so you can scale by adding partitions, but cross-partition ordering is not free. Systems that require global uniqueness or cross-shard transactions either centralize sequencing and accept the bottleneck, or add distributed coordination like two-phase commit running on strong consensus-backed metadata. In short, appointing a leader gives a clean and strong way to achieve total order, but it forces you to confront the bottleneck and failover issues. Dealing with those problems is the heart of total order broadcast and consensus protocol design, and different systems make trade-offs based on their consistency, availability, latency, and throughput requirements. Today we'll examine why ordering within a single partition isn't enough for some distributed applications, and what a global ordering protocol, total order broadcast, actually gives us. I'll guide you through an example, the guarantees we need, and the trade-offs involved. Start with the common design. A partitioned or sharded database assigns a leader to each shard. That leader sequences operations for that shard, so operations that touch the same shard are ordered consistently. This design scales well for local requests because each shard can proceed independently. The benefit is clear: per partition ordering keeps local latency low and lets the system scale horizontally. The limitation, though, is that this per shard ordering does not create any global sequence across shards. That means operations that touch multiple shards may be observed in different orders by different parts of the system. Many important correctness properties require a global view. For example, to take a consistent snapshot across shards, or to ensure foreign key relationships that span shards stay valid, we need coordination beyond local ordering. Without it, invariants that span shards can be violated. A concrete, modern example is a globally distributed e-commerce system. The user's shopping cart may live on one shard, inventory counts on another, and payment records on a third. A single checkout touches multiple shards and needs a consistent view of each piece to be correct. If each shard orders its events independently, you can get anomalies. For instance, some replicas might see the inventory decrement before the payment record, while others see the payment first. That can lead to contradictions. The system may think stock is available when a payment has already been processed, or vice versa. To avoid these anomalies, you can enforce a single total order across all partitions. That means leaders cannot act completely independently for cross-shard events, they must coordinate to agree on a global sequence. That coordination introduces added latency and more complex protocols. Total order broadcast is the standard abstraction for implementing a global sequence. The idea is that nodes exchange messages and ensure that every correct node delivers the same set of messages in the same order, so they all maintain an identical event log. Formally, total order broadcast enforces two safety properties. Agreement ensures no node acts on an event while another correct node never learns about it. Total order ensures that the relative ordering of events is the same everywhere. Together, these avoid divergence and reorder anomalies that break cross-shard invariance. With these guarantees, all correct participants maintain the same log of events, which makes globally consistent snapshots and cross-shard constraints possible to enforce correctly. The trade-off is obvious. Achieving that global ordering requires consensus-style coordination or a sequencer, which increases latency and adds operational complexity compared with purely per-partition ordering. I'll draw a short flowchart on the board. First, show two independent timelines for shard A and shard B. Point out that without a global sequence, nodes can observe different interleavings. Then show how that leads to inconsistency between nodes X and Y. Finally, draw a single global timeline produced by total order broadcast. Explain that when every node applies operations in that agreed order, the interleaving ambiguity disappears and cross-shard invariants hold. In practice, total order can be implemented using consensus protocols like multi-paxos or raft across all participants, or using a dedicated sequencer that assigns global sequence numbers. A common design optimization is to apply global ordering only to cross-shard operations and keep local operations fast and partition local whenever possible. To wrap up, per-partition ordering scales and is efficient for local work, but it can't guarantee correctness for operations spanning partitions. Total order broadcast provides the strong guarantees we need: agreement and total order, so systems can maintain identical logs and enforce global invariance. But those guarantees come at the cost of added latency and complexity, so designers often apply global ordering only where it's needed. Today we'll study a strong guarantee in distributed systems, no message lost. In short, it means that if any correct node accepts and delivers a message, every other correct node will eventually deliver that same message. We'll unpack what this means, why it matters, how systems implement it, and the trade-offs involved. At its core, once a message is delivered by a correct node, the system ensures that all other correct nodes will also deliver that message, sometime later at the latest. That promise is about delivery, not about when or in what order. Formally, this guarantee is closely aligned with the notion of uniform reliable broadcast. It's also a required ingredient for stronger guarantees like atomic or total order broadcast, which add ordering constraints on top of delivery. Why do we care? Users expect consistent behavior across devices and services. If deliveries diverge, clients and services will see different state and produce confusing or incorrect results. Concrete examples make this clear. A chat message typed on your phone should appear on your web client and other devices. A configuration change must reach all replicas. Firmware updates should reach every targeted device. In blockchains, transactions broadcast to one node must propagate so all honest nodes record the same ledger entry. If delivery to one node doesn't imply delivery to all, system state can diverge. That leads to inconsistent responses, apparent data loss, and bugs that are difficult to reproduce and fix. One common pattern uses a leader and consensus. The leader accepts a message and replicates it to followers. Once a quorum acknowledges and the entry is durably stored, the message is considered committed and can be delivered by all replicas. Protocols like Raft or Multipaxos follow this approach. Quorum-based designs require writes to reach a quorum of replicas and reads to consult a quorum. This overlap ensures committed messages are visible cluster-wide without a single leader for every operation. Gossip or anti-entropy systems continuously exchange summaries and fetch missing data. Over time, all correct nodes converge on the same set of messages. This is useful at large scale, though propagation is probabilistic and eventual rather than immediate. Reliable multicast or explicit uniform broadcast protocols are designed so that if any process delivers a message, then every correct process will deliver it. They typically combine acknowledgements, retransmission, and failure detectors to guarantee delivery. Durable logs plus replication protect against node crashes. Systems write messages to stable storage and replicate them before acknowledging the client, ensuring a delivered message survives node restarts. Here's a step-by-step flow. The client sends a message to the leader appends it to a durable log, and replicates it to followers. After a quorum of followers acknowledge, the leader marks the entry committed and delivers it to connected clients. Lagging replicas then fetch the committed entry and deliver it to, satisfying the if one, then all guarantee. There are important limits. Delivery guarantees don't imply any particular order. Ordering requires extra coordination. Guarantees often imply at least once delivery, so handlers must be idempotent or deduplicate. Network partitions force trade-offs. Systems can favor availability or safety. Waiting for every node can increase latency and slow nodes can delay progress. And finally, guarantees depend on fault assumptions. Byzantine failures need stronger protocols. To make this promise practical, give each message a unique ID or sequence number so duplicates can be detected. Design handlers to be idempotent. Persist messages before acknowledging producers. Choose quorum or consensus when you need strong guarantees and use gossip or anti-entropy when you need scale. Monitor replication lag, use back pressure to protect slow nodes, and clearly document what your system guarantees. A brief chat example: Alice's message is written to a durable log on her server and forwarded to the cluster leader. The leader replicates it to a quorum and, when committed, delivers it to all connected clients. Lagging replicas fetch the committed entry later and deliver it as well. Pick this guarantee when consistent global state is critical: financial transactions, configuration pushes, critical alerts, or distributed coordination. For large-scale, best-effort workloads like some analytics or telemetry, eventual delivery without strict uniform guarantees may be an acceptable trade-off. In summary, the promise if a message is delivered to one node, it is delivered to all nodes captures a powerful consistency property. Achieving it requires replication and durability, often some form of consensus, and operational practices like idempotency, monitoring, and careful documentation to make the guarantee practical and robust. Today we will explore total order broadcast, what it guarantees, why it matters, and how real systems keep a single, consistent order of messages even when networks and nodes fail. I'll guide you through the correctness properties, common algorithmic patterns, how systems survive interruptions, practical examples, and the core trade-offs designers face. First, let's list the 4 core properties any correct total order broadcast must provide: validity, agreement, integrity, and total order. I'll explain each one so you clearly understand what correctness means in this context. Validity means, if a correct process broadcasts a message, then every correct process will eventually deliver it. In other words, the system must not lose messages from honest participants. Eventual delivery is required despite transient problems. Agreement means, if any correct process delivers a message, then every correct process eventually delivers that same message. This prevents split-brain situations where different nodes believe different sets of messages exist. Integrity guarantees 2 things: every delivered message was actually broadcast by some process, and each message is delivered at most once. This prevents invented messages and duplicate processing. Total order requires that all correct processes deliver the same messages in the same sequence. If 2 processes deliver M1 and M2, they must agree on which came first. This is critical for deterministic application state across replicas. Total order broadcast must hold under realistic failures. Packets can be dropped or reordered, nodes can crash, and networks can partition. We design algorithms that preserve safety in these conditions and provide liveness when the environment allows. To achieve correctness, we combine a few reliable mechanisms: durable logs to avoid loss, deterministic ordering rules to ensure identical sequences, and liveness tools like retries, elections, or consensus so progress resumes after outages. Leader-based systems designate a sequencer to assign increasing sequence numbers. Replicas append messages according. Total order can be achieved by consensus. Protocols like Paxos and Raft replicate a log. Each command is proposed and agreed upon by a quorum, then appended at the same log position everywhere. The quorum ensures agreement and integrity. Persistence and retries guarantee eventual delivery. Another pattern uses logical timestamps, Lamport or hybrid clocks, plus a deterministic tiebreaker like process ID. Timestamps give a candidate order. To be safe under partitions, you often need a coordinator or later consensus to finalize the ordering so no divergent orders persist. When the network or nodes fail, systems preserve safety using persistence, retries, quorum rules, and reconciliation. Let's unpack each of those ingredients and how they prevent order violations. Write messages and assign positions to stable storage or replicate them immediately. Durability ensures that when a node comes back after a crash or disconnection, it can resume from a consistent state and not lose its place in the global order. Senders and intermediaries keep retrying deliveries with backoff. Retries alone don't break order because each message is tied to a durable sequence position or a consensus decision. The ordering metadata keeps retries from creating conflicting orders. Many systems require a quorum, e.g., majority, to make progress. If partitions prevent forming a quorum, the system stalls accepting new globally ordered messages rather than risk divergent orders. This sacrifices liveness temporarily to protect safety. When connectivity returns, nodes exchange compact state, log indices, offsets, and fetch missing entries. Because ordering decisions are recorded as log positions or consensus rounds, catch-up just fills gaps, delivered order remains consistent across nodes. Here's a simple flow to visualize operation and recovery. Normal operation: a node broadcasts, the orderer assigns a position, replicas append to their logs, and then deliver. Under failure, the system may stop proposing new positions but preserves the log state. On recovery, nodes exchange offsets, fetch missing entries, and then deliver in the agreed order. This sequence keeps the total order intact. Real systems illustrate why total order matters. Event-sourced services rely on ordered events to build views. Financial ledgers require serialized transactions to avoid inconsistent balances. Multiplayer games need a consistent action order for authoritative state. Permissioned blockchains use quorum finality to prevent forks. Each uses sequencing, consensus, or leaders to ensure the same global order everywhere. Designers balance trade-offs. Many systems prioritize safety over liveness and stop under partition. Leader-based designs are simple and fast but can bottleneck. Consensus adds rounds in cost but increases decentralization and fault tolerance. Finally, making application operations idempotent is a good extra safeguard against retransmissions or rare duplicate deliveries. A correct total order broadcast couples deterministic ordering, sequencer, consensus, or coordinated timestamps with durability and liveness mechanisms. During interruptions, systems preserve safety by stalling or buffering. After repair, they use persistent ordering metadata and quorum-based reconciliation to ensure every correct node delivers exactly the same messages in the same global sequence. Today we're looking at total order broadcast and why it's central to consistent replication. Many consensus systems, you may know Zookeeper, implement this idea in practice. That connection between consensus and ordered message delivery is important, and we'll build on it later. First, we'll make clear what total order broadcast actually gives us and why we care. At its core, total order broadcast guarantees that every node receives the same set of messages in the same sequence. That simple property is extremely powerful. If every participant sees the exact same list of operations in the exact same order, they can stay in sync even when messages traverse different paths or nodes fail and recover. This is exactly what you need for robust database replication. Treat each message as a write operation. If every replica applies those writes in identical order, their states remain consistent aside from short replication lag. This idea is known as state machine replication. Feed the same deterministic operations into identical state machines in the same order and they converge on the same state. Total order broadcast also gives a straightforward path to serializable transactions. Imagine each transaction is packaged as a deterministic stored procedure or command message. If every participant executes those transactions in the globally agreed order, the system behaves as if transactions ran one after another on a single node. That removes anomalies and makes reasoning about correctness far easier. A crucial detail: ordering is final when a message is delivered. Once a message is placed at position n in the sequence, no node can later insert another message before n if later messages are already delivered. This finality is different from timestamp-based ordering. Clocks can drift and timestamps can be reassigned, creating ambiguity. Total order broadcast gives absolute ordering at delivery time and therefore stronger guarantees. You can also think of total order broadcast as building a globally consistent append-only log, a replication log, transaction log, or write-ahead log. Delivering a message is equivalent to appending an entry. Because every node appends the same entries in the same order, each node can read and replay the log to achieve identical state transitions. That log view is useful beyond replication for coordination too. For example, lock services use the log sequential indices as fencing tokens. Each lock acquisition becomes a log entry, the assigned sequence number is a monotonic token. A client holding the current token can prove its freshness, older tokens are stale and can be ignored. Zookeeper exposes this via ZXID, and ECT and similar systems use analogous sequence numbers for safe fencing. Here's a simple flow to hold in your head. A client sends a message. That message goes through total order broadcast, which decides a single global position. The message is appended to the global log at that position. Remember, every node uses the same positions. Finally, replicas apply the logged operations in sequence, producing identical state transitions across nodes. To summarize, total order broadcast ensures identical, final ordering of operations across nodes. That makes replication straightforward, enables serializable execution by ordering transactions, and provides a natural append-only log for coordination tasks like fencing. Behind the scenes, consensus algorithms implement or support this primitive, and we'll unpack that relationship in later chapters. Welcome. Today we'll explore how a single global ordering, a total order broadcast, can be used to build linearizable storage, and where this approach needs extra care. We'll walk through definitions, a concrete example, reserving a unique social handle, the log-based algorithm, why it works, the caveat about reads, and 3 ways to achieve linearizable reads. First, total order broadcast. It guarantees that every node delivers messages in the same global sequence. Delivery can be asynchronous. Different nodes may receive messages at different times, but the relative ordering of messages is identical everywhere. Now, linearizability. This is a real-time guarantee. Any completed read must reflect the most recent completed write, according to actual wall clock order. Linearizability ties operations to a single global timeline that respects real-time ordering of completed operations. Put simply, total order broadcast gives everyone the same global order of messages. Linearizability requires that operations appear to take effect at a single point in real time, so reads must reflect the most recent writes. These are related but not identical guarantees. To make this concrete, imagine reserving a unique handle on a decentralized social network. For each handle, we imagine a logical register initialized to null, meaning available. Claiming a handle is an atomic compare set. Write your account ID if and only if the register is currently null. With linearizable registers, concurrent attempts to claim the same handle resolve so that exactly one CAS succeeds, all other attempts observe the register is no longer null. We want that same property when building on a total order log. Here is the log-based algorithm in 3 steps. First, append a claim message for the desired handle to the replicated, append-only log. Second, wait until the log delivery mechanism returns your appended claim back to you. Since delivery is in total order, every node will eventually see the same sequence. Third, inspect the log, find the earliest claim for that handle. If the first claim is yours, you win and commit, otherwise you abort and report failure. Why this produces unanimous agreement. Total order delivery ensures everyone sees the same ordering of competing claims. By choosing the earliest claim on the log as the winner and aborting later ones, all nodes deterministically agree which claims committed. That yields linearizable write decisions. This pattern generalizes. For serializable multi-object transactions, record transaction intents in a single global log. Order the intents and decide commit or abort deterministically from that order. The global log becomes the canonical timeline that serializes conflicting transactions. Important caveat: while the log-based design orders and linearizes writes, it does not automatically make reads linearizable. Clients that read from replicas asynchronously updated from the log can observe stale state. The naive approach typically yields sequential consistency, a consistent timeline, but not necessarily respecting real-time recency for reads. If you need linearizable reads as well, you must force reads to observe a specific point in the same agreed timeline. There are 3 common strategies to do that, each with trade-offs in latency and complexity. First, sequence reads through the log. Treat a read as a special log entry, append a read marker, wait until it's delivered, then perform the read. The marker's position is the read's linearization point. This is similar to patterns used by quorum read systems like ECT. Second, query the log's latest position and wait until your replica has applied entries up to that index. If the log can report positions in a linearizable way, you can sync to that point as Zookeeper's sync follows this idea. Third, read from a replica that is updated synchronously for writes. Reading from that replica yields up-to-date state and thus linearizable reads, as in a primary or a synchronously maintained tail of a chain. I'll draw a simple text flow to show the sequence. Start, client wants handle, client appends claim to replicated log replication orders claims, total order, log delivers entries to nodes, node inspects earliest claim for that handle if earliest is this client, append commit entry and acknowledge success else, report failure. This shows the chronological steps and where the deterministic decision is made. In summary, total order broadcast gives a single agreed timeline that you can use to implement linearizable write semantics by deterministically choosing winners among conflicts. To make reads linearizable too, you must make reads observe a defined point in that same timeline either by sequencing them, syncing to a log position, or reading from a synchronously updated replica. Each option trades off latency, complexity, and availability. Today we'll see how a single linearizable counter can give us a total ordering of messages across a distributed system. I'll show the simple construction, why it works, why building the counter is hard, and how this ties directly to consensus. Total order broadcast means every participant delivers the same set of messages in the same global order. That order must be consistent across processes. If one process delivers a before B, every process must deliver a before B. This primitive is crucial when multiple nodes must agree on a single serialized sequence of events. The primitive we assume is a linearizable integer register that supports an atomic increment and get, or compare and set. Linearizability means each increment appears to happen at a single instant, and increments produce successive integers with no gaps in the global sequence of successful operations. When a process wants to broadcast a message, it first performs an atomic increment and get on the counter. The returned value is used as the message's sequence number. The sender attaches that sequence number to the payload and then reliably transmits the message to all participants, retransmitting if needed. On the receiving side, nodes buffer incoming messages and deliver them to the application in increasing sequence number order. If a node receives sequence 6 while it has delivered only up to 4, it must wait for 5 before delivering 6. This waiting guarantees the same delivery order everywhere. The construction relies on the counter producing a single contiguous sequence of integers. Every successful increment yields the next integer in one global sequence. That property makes it deterministic which message must exist when a later sequence number arrives. Logical clocks like Lamport timestamps capture causality, not a single linear index. They can be identical across different, concurrent events or leave gaps. They don't give a contiguous global sequence. Therefore, timestamps alone cannot implement total order delivery in the gap-free way we described. In a failure-free environment, you could keep the counter on one machine, but real systems have crashes, partitions, and message loss. Restoring the exact counter value after failures and coordinating concurrent increments across crashes requires replication and agreement. Ensuring the counter remains linearizable under these conditions is a hard problem. This is not accidental. A linearizable compare and set or increment and get register, a total order broadcast service, and consensus are interreducible. If you can build any one of these reliably, you can transform it into the others. In other words, the ability to generate a globally consistent sequence, to order messages the same everywhere, or to choose a single agreed value or equivalent capabilities in distributed systems. Practically, you might stamp every order with a globally increasing rank using a cloud-managed strong counter to serialize order processing across regions. That looks simple and attractive. But in production, operating that counter under failures requires consensus-like coordination behind the scenes in the managed service. Let's step through the flow. Sender, increment counter dash receive sequence number dash attach seek to message dash reliably send to all. Receiver, receive message dash place in buffer keyed by seek dash if next expected seek present then deliver in order, otherwise wait for missing sequence. This simple pipeline is what yields total order delivery when the counter is linearizable. Key takeaway, providing a global ordering boils down to global agreement, and that is the same core difficulty as consensus. With this perspective, the next step is to study consensus algorithms directly. The following chapters will develop consensus protocols and show how they implement the primitives we've been assuming. Today we explore consensus, a central but surprisingly tricky problem in distributed systems. At its core, it asks a simple question: can a set of independent nodes agree on a single value? Despite that apparent simplicity, practical and theoretical challenges make consensus one of the hardest problems we design for and reason about. The immediate statement of consensus sounds trivial: get nodes to choose the same value. But that simplicity hides many traps. Systems that looked correct at first have failed in production because subtle timing, failure, and ordering issues were overlooked. Consensus is subtle because distributed systems run in unpredictable environments. Messages may be delayed or lost, processes may crash and recover, and clocks are not perfectly synchronized. Reasoning about all these interactions requires careful models and assumptions, otherwise, corner cases lead to incorrect behavior. Before diving into consensus, you need a toolkit: how replication propagates state, how transactions coordinate state changes, what assumptions a system model encodes, the meaning of linearizability for correctness, and how total order broadcast enforces a common sequence of events. These concepts let us state guarantees and trade-offs precisely. One common use of consensus is electing a leader. For distributed databases or control planes, agreeing on a single primary simplifies coordination and prevents split-brain scenarios where two nodes both assume leadership and cause conflicting rights. Consensus underpins commit protocols that must ensure a transaction either commits on all required replicas or is aborted everywhere. Without agreement, different nodes might take incompatible actions leading to data corruption. When a cluster must apply the same sequence of updates in the same order, configuration changes, membership updates, or applying commands, consensus guarantees that every replica sees and executes the identical ordered log of operations. Blockchains use consensus to decide which chain is canonical. Agreement prevents double spending and ensures every honest node arrives at the same ledger state. Different blockchain designs make different trade-offs between speed, finality, and adversary tolerance. When configuration or security policy changes must take effect cluster-wide and consistently, consensus ensures all services observe the change coherently. This avoids inconsistent behavior across microservices or regions. Services often need exclusive access to a resource. Consensus-based locks or leader leases coordinate who holds exclusivity, preventing race conditions in the presence of failures and network partitions. Consensus operates in an adversarial environment, nodes crash, messages get delayed or dropped, and networks partition. Fault models capture attacker or failure capabilities, simple crash faults, omission faults where messages are lost, and Byzantine faults where components behave arbitrarily or maliciously. Stronger fault models require more complex protocols and more resources. A key theoretical result is the FLP impossibility theorem. In a fully asynchronous system, if even one process can crash, no deterministic algorithm can guarantee both safety and liveness. In practice, systems avoid the deadlock of this theorem by making timing assumptions, using failure detectors, or using randomization to break symmetry. Consensus systems make explicit trade-offs. Some prioritize safety, never making a wrong decision even if that means becoming unavailable under extreme conditions. Others favor availability at the cost of weaker consistency. Understanding which properties you must preserve under which failures is essential when choosing or designing a protocol. Architecturally, many consensus protocols concentrate coordination in a leader for simplicity and performance. Paxos and Raft are prime examples. Other designs are leaderless or quorum-based to improve availability or avoid a single coordinator. For Byzantine faults, protocols like PBFT or Tendermint add cryptography and extra rounds to tolerate malicious behavior. A common operational flow looks like this. A client proposes a command to a leader. The leader forwards the proposal to replicas. If a quorum of replicas accepts, the command is committed and applied. If not, the system retries or triggers a leader election. This simple flow hides many edge cases, timeouts, message reordering, and recovery after crashes. Before committing to consensus, ask whether you truly need it. Often eventual consistency, CRDTs, or other pragmatic compromises are simpler and adequate. Use consensus when you require a single authoritative decision, transaction commit, primary election, or a canonical log, and be explicit about your assumptions and failure model. In summary, consensus is essential but hard. It requires careful assumptions and a solid background in replication, transactions, system models, linearizability, and ordering. If you decide consensus is necessary, study the impossibility results and the practical algorithms that implement agreement under realistic assumptions. In the following chapters, we will dig into those guarantees, impossibility proofs, and resilient algorithms used in real systems. Today we'll explore why single-leader replication needs consensus, what can go wrong when nodes disagree, and how real systems prevent that dangerous split-brain outcome. In single-leader replication, the cluster assigns one node to accept all writes. The other nodes act as replicas that copy that leader's updates. This clear division keeps write ordering and simplifies correctness so long as everyone agrees on who the leader is. For the system to behave correctly, every node needs to agree about which machine currently holds leadership. If some nodes think A is leader while others think B is, clients routed to different nodes will see different behaviors and the cluster won't be consistent. Networks aren't perfect. Partitions, cloud region outages, or intermittent link failures can break communication between nodes. Those kinds of failures make it hard for nodes to exchange heartbeats or election messages, and leadership can become contested. If nodes can't reach a common decision, two or more nodes may each assume they are the leader. We call this situation split brain, multiple authorities simultaneously accepting rights as if they were the sole leader. When two leaders accept rights concurrently, each leader updates its own set of replicas. The histories diverge, some clients' rights go to one leader, others go to the other. After connectivity is restored, merging those divergent histories is error-prone and may require discarding data or manual conflict resolution, leading to inconsistency and potential data loss. Think of it like bank tellers in different branches. Only the teller with the authenticated token and confirmation from enough colleagues should process withdrawals. If two tellers both approve the same withdrawal without coordination, accounts can be overdrafted and ledgers won't match. Consensus protocols are the coordination that prevents that from happening. Modern production systems enforce consensus rules so a leader is only valid when it holds a quorum or an explicit lease. Elections are governed by robust protocols like Raft or Paxos, which ensure only one leader emerges and that leadership changes are safe even under failures. Practical safeguards include quorum voting, requiring a majority to elect or validate a leader, fencing tokens or monotonic epochs to prevent stale leaders from accepting rights, lease expirations so leadership times out if not renewed, and tie-breaking mechanisms for geo-distributed setups such as odd numbers of voters or an external arbiter. Let's walk a simple flow. Node suspects leader is down dash node requests votes dash if node gets quorum of votes, it becomes leader dash new leader obtains a lease or increases epoch slash fencing token dash replicas accept rights only if lease slash token is valid dash if network partition occurs, nodes without quorum reject leadership claims. Each step ensures conflicting leaders can't both be active. To summarize, single-leader replication depends on cluster-wide agreement about who leads. Network failures can create split-brain, which causes divergent histories and data loss. Consensus protocols like Raft or Paxos, plus practical measures such as quorum rules, fencing tokens, and leases, prevent split-brain by ensuring only a properly authorized leader can accept rights. Design systems with these protections so your data remains consistent even when parts of the network fail. Today we're studying the atomic commit problem. When a single transaction touches data spread over multiple nodes or partitions, a new failure mode appears. Some participants may successfully apply the transaction while others do not. To preserve acid atomicity, the guarantee that a transaction either fully happens or not at all, every node involved must reach the same final decision, commit or abort. That coordination challenge, ensuring a unanimous all-or-nothing outcome across participants, is called the atomic commit problem. What I want you to picture is the partial commit problem. If one node makes a change and another fails, the system can drift into inconsistency. Atomicity demands there be no half-done transactions left in the system. So we need a way to make sure every participant either applies the change or rolls it back. Nobody can be left uncertain. Here's a concrete example. An online checkout touches multiple services, inventory on one shard, payment on a payment service, and a shipment record on another node. If inventory is decrement but payment processing fails, you can end up with reserved stock and no payment, a broken business invariant. The system must avoid that split outcome. Another example is a bank transfer. If the sender's shard successfully debits the account but the receiver's shard fails to credit, balances become inconsistent. That can lead to financial loss, legal exposure, and a loss of trust. Atomic commit prevents that by ensuring both sides agree to commit or both abort. Why this matters: broken invariants cause real harm. Inventory errors create shipping mistakes, partial money moves cause reconciliation headaches and potential regulatory issues, users see incorrect balances or duplicate orders. Ensuring atomic outcomes protects correctness and business rules. At its heart, the atomic commit problem is a distributed consensus problem. Every participant must agree on a single outcome for the transaction, commit or abort. Achieving that agreement requires coordination despite failures and network uncertainty, so no participant is left in an ambiguous state. Practical systems solve this with commit protocols and careful recovery logic. A common protocol is two-phase commit. A coordinator asks participants to prepare. Participants vote yes/no. The coordinator decides and tells everyone to commit or abort. Timeouts and recovery procedures handle failures. For example, a participant that crashes can consult a coordinator or a log during recovery. Note that protocols must be designed to tolerate message loss, crashes, and to avoid leaving participants permanently blocked when possible. Architects face trade-offs. Strong distributed atomicity adds complexity and latency and can reduce availability under failure. That's why teams sometimes prefer alternatives: avoid distributed transactions, use eventual consistency, design compensating transactions, or rely on idempotent operations and careful retries. The choice depends on how critical strict atomicity is for the application's invariance. Walk through this simple flow. The client asks a coordinator to start a distributed transaction. The coordinator asks all participants to prepare. Each participant responds with a vote: yes, they can commit, or no, they cannot. If all vote yes, the coordinator decides to commit and instructs everyone to commit. If any vote no, it instructs everyone to abort. Participants then apply the decision. If failures occur at any step, timeouts, logs, and recovery procedures, for example replaying logs or electing a new coordinator, are used to reach a final decision and avoid indefinite uncertainty. Today we explore a famous theoretical result and how real systems work around it. We'll start with the FLP impossibility theorem, then see practical techniques like timeouts, failure detectors, and randomized choices that let real distributed systems reach agreement despite faults. The FLP theorem, named after Fisher, Lynch, and Patterson, shows a fundamental limit. In a completely asynchronous network, any deterministic algorithm cannot guarantee consensus if even one node can crash. That sounds alarming, so let's carefully unpack what the theorem assumes. FLP's conclusions follow from a very strict model. It assumes full asynchrony, meaning there are no timing guarantees, and that the algorithm is deterministic and cannot use clocks or timeouts. An adversary controlling message delivery times can keep the system in indecision forever by making a slow node indistinguishable from a crashed one. At first glance, FLP looks like doom for distributed agreement. If you must assume a crash might have happened and you cannot tell, how can you ever make a safe decision? The important point is that FLP applies to the idealized model I just described, not to every possible real-world scenario. Real systems get around FLP by stepping outside its strict assumptions. Typical relaxations include using timeouts and leader election, employing practical failure detectors, assuming partial synchrony, or introducing randomization. Each of these removes the adversary's power to force perpetual indecision. Timeouts let a node suspect that another is failed rather than merely slow. Combined with leader election, the system can replace an unresponsive coordinator and make progress. This is the basic mechanism underlying many practical consensus protocols. Chandra and Tug formalized failure detectors, abstractions that may make mistakes but, if their accuracy and completeness properties are sufficient, can be used to solve consensus. The idea is you don't need perfect information, practical, imperfect detectors are enough. Randomized algorithms avoid certain deterministic deadlocks by having processes make random choices. With high probability, these choices let the system progress and eventually agree. Randomness can be a powerful tool when determinism is stuck. A concrete, commonly seen protocol is two-phase commit. The coordinator asks participants to prepare, each votes yes or no. If everyone votes yes, the coordinator decides to commit and tells everyone to commit, otherwise it aborts. This is simple and widely used for atomic commits across services. Think of an e-commerce checkout. Inventory, payment, and shipping services must all agree to commit the transaction. If one fails to commit while another charges the card, you can end up with inconsistent or bad customer experiences. 2PC enforces the all-or-nothing property. Two-phase commit has important drawbacks. It's blocking. If the coordinator crashes after participants vote yes but before sending the final commit, participants hold locks and cannot proceed until the coordinator recovers. 2PC relies on one coordinator, so it lacks robust, fault-tolerant decision recovery. Modern consensus protocols like Paxos, Raft, and Zookeeper's Zav address 2PC's weaknesses. They treat the decision logic as a replicated state machine. Multiple nodes keep copies of the log of decisions, a leader coordinates, and progress requires only a quorum or majority. This replication removes the single point of failure problem. Raft was engineered to be easier to understand and implement than Paxos while providing the same guarantees. A stable leader handles client requests and replicates log entries to followers. Election timeouts and majority quorums ensure the system remains safe and can make progress in realistic failure scenarios. Here's a simple flow you can picture. A client sends a request to the leader. The leader appends the request to its log and replicates it to followers. Once a majority acknowledge, the leader commits and responds to the client. If the leader fails, followers use timeouts to start an election. A follower becomes a candidate, requests votes, and if it gets a majority, becomes the new leader. To summarize, FLP gives a crucial theoretical limit, but it applies to an idealized adversarial model. Real systems step outside that model by using time, imperfect detectors, partial synchrony, or randomness, and thus can achieve reliable consensus. Two-phase commit is a common atomic commit tool but has blocking behavior. For robust fault tolerance, replicated state machine protocols like Paxos and Raft are the preferred approach. Today we're talking about transaction atomicity, the all-or-nothing guarantee that helps programs stay correct when multiple related changes must happen together. I'll explain what atomicity means, why it matters, and how systems preserve or approximate it. Atomicity means that a transaction behaves as a single indivisible unit, either every change inside it is applied and made durable on commit, or none of those changes survive if it aborts. This removes the possibility of partial updates that leave the system in an inconsistent state. Why is this important? Because partial updates can violate important invariants or constraints in your data model. Atomicity prevents those half-finished states so you can reason more simply about correctness, even in the presence of failures. Imagine a bank transfer. You debit Alice's account and credit Bob's account. If the system debits Alice but crashes before crediting Bob, money is effectively lost and balances are wrong. With an atomic transaction, either both updates are persisted on commit, or if something goes wrong, the system reverts to the state as if the transfer never happened. Modern applications often maintain a primary record plus auxiliary data structures like secondary indexes or materialized views. For example, an e-commerce checkout must create an order record, decrement inventory for SKUs, and update a search index or recommendation view. If the order is created but the index update fails, search and analytics become inconsistent with the real data. When primary data and secondary structures fall out of sync, users see missing search results, stale recommendations, and incorrect inventory reports. Atomicity ensures those structures move together. Commit makes both durable, while an abort leaves everything unchanged. Many distributed systems provide atomicity only within a single shard or object by default. When updates span shards or multiple objects, preserving atomicity across them requires coordination protocols such as two-phase commit or consensus. Those protocols add latency, complexity, and operational cost. If full cross-shard atomicity is unavailable or too expensive, engineers use alternatives, idempotent operations to safely retry, compensating actions that undo earlier steps, or saga-style workflows that orchestrate a sequence of local transactions and compensations. These approaches work, but they make the application responsible for correctness and are more complex to reason about than true atomic transactions. Here's a simple flow to understand the commit versus abort decision. First, the transaction applies writes to both primary data and any secondary structures. Next, we check, did all updates succeed? If yes, we commit and make the changes durable. If any update failed, we abort and undo the changes so the system returns to the pre-transaction state. That guarantee, either commit or abort, protects us from inconsistent partial updates. To summarize, atomicity is a cornerstone of predictable, reliable systems. It prevents half-finished updates from polluting your data, keeps primary and secondary structures synchronized, and matters especially when updates span multiple objects or shards. When atomicity is absent or costly, there are engineering workarounds, but they shift complexity into application code and require careful design. Today we'll look at why committing a transaction is simple on one node but becomes difficult across many nodes. We'll compare the single-node durability model with the coordination needed for multi-node atomicity, and explain the key failure modes and rules that systems must follow. On a single database node, the storage engine is in charge of durability. When a client asks to commit, the node ensures the transaction's data changes are made durable, typically by writing them into a write-ahead log. Because the storage device is the single authority, it can enforce a strict order of durable writes, and recovery can use the log to determine whether a transaction was committed or not. That ordering, first persist the data changes, then persist a commit record, is crucial. The decisive instant is when the commit record has actually been flushed to persistent storage. If the system crashes before that flush, recovery treats the transaction as abortable. If the flush completed, recovery treats it as irrevocably committed. On one node, the disk or storage subsystem effectively enforces this rule. The picture changes when a logical transaction touches multiple nodes, shards, replicas, or separate services. If each participant independently applies and persists the transaction, some participants might commit while others abort, and that breaks the all-or-nothing guarantee that a transaction promises. There are several reasons partial commits happen. One participant might detect a constraint violation and decide to abort, while others have already applied changes. Network problems can drop or delay commit messages, so some nodes never receive them. And a node might crash while writing its commit record, rolling back on recovery, while other nodes that succeeded remain committed. If some nodes commit and others abort, the cluster ends up inconsistent. And it's worse because once a node reports data as committed and exposes it, other transactions can observe and act on that data. You cannot retroactively revoke that commit without undoing later dependent actions, which would cause cascading rollbacks across the system. For correctness, a participant must never unilaterally make a transaction visible unless it is certain every other participant will also commit. A commit must be irrevocable from the database's perspective. After the commit point is reached, the system treats the transaction as durable and visible to other transactions. This property underlies isolation levels like read committed. If you later need to reverse the effect of a committed transaction, you can issue a compensating transaction, an explicit undo like a refund or cancellation. But that compensating action is itself an ordinary new transaction managed by the application. It does not change the requirement that the original commit is treated as irrevocable by the database. Here is a simple text flow to contrast the two cases. On a single node, the node writes the data durably, then writes a commit record, and the change becomes visible. Across multiple nodes, we need a coordination sequence. Participants prepare and durably record the intent, a coordinator collects their answers and decides, and only if everyone agrees do we instruct all participants to commit. This coordination prevents unilateral, conflicting commits. In short, single-node atomicity relies on ordered durable writes controlled by one storage device. Multi-node atomicity requires coordination so that no participant commits unless it is certain all will. Any later reversal must be implemented as a new, separate transaction at the application level. That difference is why distributed commits are fundamentally harder. Today we'll study two-phase commit, or 2PC, a classic protocol that provides an atomic commit across multiple independently managed nodes. The key guarantee is simple: either every participant commits, or every participant aborts. It's widely used in distributed databases and older transaction frameworks when strict consistency is required. Start with the goal, coordinate several separate systems so they reach the same final outcome for a transaction. The outcome is binary: all participants commit or all abort, which keeps the data globally consistent. Two PC splits the process into two sequential phases. In phase 1, the coordinator asks each participant, "Can you commit?" In phase 2, the coordinator issues a single global decision: commit if everyone agreed, otherwise abort. When a participant receives the prepare request, it does several things. It verifies it can do the work, records its intent to commit durably so it won't lose the decision if it crashes, and locks the affected resources to avoid conflicting changes. Then it votes yes or no. The coordinator collects votes. If every participant votes yes, the coordinator broadcasts a commit, otherwise it broadcasts an abort. Upon receiving the coordinator's decision, participants either finalize the commit or roll back and free any locks they held. Imagine a checkout that updates inventory, charges a card, and reserves a shipping slot, each as a separate service. The checkout coordinator asks each service to prepare. If all prepare successfully, the coordinator tells everyone to commit. If any service cannot prepare, the coordinator instructs everyone to roll back so the system stays consistent. Visualize the flow. The coordinator sends a prepare to all participants. Each participant replies with a yes or a no vote. The coordinator evaluates the votes and issues a single global commit if all are yes, otherwise global abort. Finally, participants act on that decision and release locks. Key properties: 2PC enforces atomicity across participants. But it also has drawbacks. Participants that voted yes must hold locks while waiting, which can block progress. Also, the coordinator is a critical role, its availability and durable state are essential for proper operation. To survive crashes, participants persist their prepared state to durable storage so they can honor the final decision later. Recovery mechanisms such as replaying logs, electing a new coordinator, or administrative intervention are needed to resolve uncertain states after failures. Use 2PC when you truly need strict synchronous consistency, for example, when multiple legacy databases must be updated atomically for legal or financial correctness. Avoid 2PC when availability and responsiveness are more important, or in loosely coupled microservice architectures. Alternatives include Saga's sequences of local transactions with compensating actions for rollback idempotent retry patterns, or event-driven designs that accept eventual consistency. For replicated state, consensus algorithms like Raft or Paxos are a better fit than distributed 2PC. Historically, XA and JTA provided 2PC semantics to applications, and WS atomic transaction was used in SOAP-era systems. In modern cloud-native architectures, teams often prefer lighter-weight coordination or alternative patterns due to 2PC's complexity and blocking behavior. If you do use 2PC, follow these best practices. Keep the prepare window short to reduce lock contention, ensure prepare and decision records are durably logged, have a dependable recovery path for coordinator failures, and critically assess whether your business needs justify the operational cost of 2PC. Before adopting 2PC, answer 3 questions. Do you truly need strict atomicity across resources? Can you tolerate the blocking and extra operational burden? And do you have durable logging and a recovery plan? If any answer is no, consider alternative designs. Today we'll study two-phase commit, or 2PC, a protocol used to make sure a distributed transaction either fully succeeds everywhere or fully fails everywhere. I'll describe what it does, how it works step by step, and why it's different from other protocols with similar names. First, avoid confusing 2PC with 2PL. They sound similar but serve different purposes. Two-phase commit makes a commit decision that is atomic across multiple participants. Every node commits or everyone rolls back. Two-phase locking, on the other hand, is a concurrency control technique that enforces serializable isolation among concurrent transactions. Treat them as separate concepts. Two-PC uses a coordinator, often called a transaction manager, which orchestrates the commit across participants. In real systems, the coordinator may run inside the application process as a library, for example inside a Java EE container, or it can run as a separate service. Common transaction managers include Narayana, Atomicos, Bytronix, and Microsoft's Distributed Transaction Coordinator. Step 1 is the normal application work. The application reads and writes data on multiple database nodes, which we call participants. The application performs its usual operations across these participants before deciding to commit. Phase 1 is the prepare phase. When the application decides to commit, the coordinator sends a prepare request to each participant, effectively asking, "Can you commit this transaction?" Each participant examines its local state, ensures any required locks or durable information are in place, and then returns a yes if it can commit or no if it cannot. In Phase 2, the coordinator collects all responses. If every participant answered yes, the coordinator issues a commit command to everyone, and each participant completes the commit locally, making changes permanent. If any participant replied no, the coordinator issues an abort and each participant rolls back the local changes. The outcome is all or nothing. Here's the flow in sequence. The application does work on the participants. When ready to commit, it tells the coordinator, which sends prepare requests to all participants. Each participant replies yes or no. If the coordinator sees only yes replies, it sends commit commands and participants persist the changes. If any participant says no, the coordinator sends abort commands and participants roll back. This ensures the atomic result across the distributed system. Think of 2PC like booking a multi-vendor trip, flights, hotel, car. Before finalizing, the system asks each vendor, "Can you reserve this?" Only if all vendors confirm does the system finalize. If any vendor declines, the system cancels the tentative reservations so the traveler isn't left with a partial trip. That captures the all-or-nothing nature of 2PC. The key takeaway, two-phase commit is about atomicity across distributed participants. It uses a coordinator and a two-step prepare/commit sequence to guarantee an all-or-nothing outcome. It does not provide isolation or concurrency control. Protocols like two-phase locking handle that. To summarize, remember the two phases: prepare and commit or abort, remember the coordinator's role in common transaction managers, and always keep clear the difference between 2PC, which solves distributed atomic commit, and 2PL, which enforces isolation and concurrency control. Today we'll study why two-phase commit, or 2PC, can guarantee atomic commits across multiple nodes while a naive single-phase commit cannot. The core idea is that 2PC turns uncertainty into durable promises. Participants promise they can commit, and the coordinator records a single, durable decision. We'll walk the protocol step by step, highlight the two irreversible events that secure atomicity, show a simple text flowchart, and touch on operational trade-offs. At a high level, 2PC separates the process into two distinct phases: a prepare phase where participants make a durable promise, and a commit phase where the coordinator makes and persists the final decision. Those two durable rights are what prevent split outcomes across nodes. First, the coordinator issues a globally unique transaction ID. This ID tags every local action so all participants and the coordinator are talking about the same distributed transaction. Without a shared ID, messages and logs can't be correlated reliably after failures. Each participant runs its local reads and writes inside a local transaction annotated with the global ID. If a participant crashes during local work, it or the coordinator can decide to abort that global transaction. Importantly, local changes are prepared but not yet made visible globally until commit. When the application asks to commit, the coordinator sends a prepare request, including the global ID, to every participant. If any prepare fails or times out, the coordinator broadcasts abort. The prepare is effectively a request: "Can you guarantee you'll be able to commit later?" On receiving prepare, a participant must ensure it can unconditionally commit later. Practically, that means persisting enough state writing to durable storage so a crash won't prevent a later commit, and validating constraints or conflict checks. If it replies yes, that reply is an irrevocable promise: the participant has surrendered the right to abort unilaterally later. Once the coordinator has all votes, it decides: commit only if every participant voted yes, otherwise abort. Crucially, the coordinator writes that decision to its durable transaction log, the commit point. That right makes the outcome authoritative and recoverable even if the coordinator crashes immediately after. After persisting its decision, the coordinator sends the final commit or abort to all participants and retries delivery until each participant acknowledges. If a participant had voted yes but crashed before receiving the final command, on recovery it must consult its durable state in the coordinator, or logs, and honor the eventual decision. The combination of durable promises and indefinite retries ensures everyone converges on the same outcome. These two events are the heart of 2PC's safety. A participant's yes vote means it gave up the ability to abort, it already made local changes durable enough to commit later. The coordinator's persisted decision is the single source of truth. Once written, that outcome must be enforced. Together they prevent split-brain outcomes where some nodes commit and others abort. In a single-phase approach you collapse the prepare and decision into one local commit right per node. Across multiple nodes this creates races. Some nodes may persist to commit while others crash or time out before seeing the instruction, producing non-atomic, inconsistent states. Without the distinct prepare promise plus a single persisted decision, there's no durable coordination point to force agreement after failures. Let's walk this simple text flow. The coordinator issues a global ID, participants do local work under that ID, then the coordinator asks prepare. Participants that can commit persist the prepare and reply yes. If the coordinator gets all yes votes it persists the final decision, then tells everyone to commit. If delivery fails, the coordinator retries, and participants recovering from crashes consult their persisted promise and the coordinator to determine the outcome. This chain is how 2PC enforces a single outcome. Two practical trade-offs follow from 2PC. First, it can block. Participants that voted yes cannot unilaterally progress until the coordinator's decision is known, so a failed coordinator can leave them waiting. Second, the protocol depends on durable rights. Both participants and coordinator must persist state reliably, otherwise promises and the commit point aren't trustworthy. Imagine rolling out a breaking schema change across multiple microservices. During prepare, each service ensures it can apply the migration and persists backups or plans. By saying yes, each service promises it'll finish. The coordinator proceeds only if all are ready, records its decision, and then instructs everyone to apply or roll back. Because the readiness promises and the final decision are durable, the rollout is atomic, either every service moves forward, or none do. To summarize, 2PC doesn't eliminate message loss or crashes, but it transforms uncertainty into two durable, irrevocable promises: the participant's yes and the coordinator's persisted decision, and it uses retries to disseminate the final outcome. Those two promises are the mechanism that makes atomic commits across distributed nodes achievable, at the cost of blocking and strict durability requirements. Today we'll study a classic failure mode in distributed transactions: how two-phase commit can leave participants stuck when the coordinator fails. I'll use a checkout example to make this concrete and then walk you through exactly when and why the protocol becomes brittle. Imagine a modern microservices checkout. One service charges the customer's card, another reserves inventory, and a coordinator tries to make those actions appear as one atomic transaction across databases in different regions. That coordinator runs two-phase commit to coordinate the databases. Two-phase commit has two simple steps. In phase 1, the coordinator sends prepare requests and each participant does whatever local work is needed and replies yes or no. If everyone says yes, the coordinator decides to commit and sends commit messages in phase 2. If anyone says no, it aborts. The tricky part is failures. What happens depends entirely on when the coordinator crashes relative to these phases. Sometimes they're safe for participants to abort, other times they're stuck waiting. Once a participant votes yes, it has made a local promise, it has prepared the change and cannot undo it alone. That participant becomes uncertain, it cannot commit or abort safely without knowing the coordinator's decision, because either unilateral action could break global consistency. Here's a concrete failure sequence. Both databases receive prepare and vote yes. The coordinator decides to commit, sends commit to DB2, and then crashes before telling DB1. DB2 commits, but DB1 is left in the prepared state and must wait. If DB1 unilaterally aborts, the system diverges. If it commits without confirmation, it might be wrong if some participant had voted no. That is the blocking problem of two-phase commit. To reduce ambiguity, 2PC requires the coordinator to write its decision to stable storage before sending that decision to participants. That durable log is the single point where the global decision becomes fixed. If the coordinator recovers and sees a commit record, it can finish committing. If it sees no commit record for that transaction, it treats it as aborted. The main takeaways are these. Two-phase commit can block participants when the coordinator fails, so coordinator availability and durable logging are central to correctness. If you cannot tolerate blocking, you must consider other designs. Three-phase commit relaxes some blocking. Consensus protocols like Paxos or Raft distribute the decision, or you can redesign to use weaker consistency models with compensating actions. Each alternative has its own trade-offs. To finish, consider these questions. Could participants exchange votes and reach a decision without the coordinator, and what would that cost? What are the practical trade-offs of using consensus instead of 2PC for distributed commit? And in which real systems might it be acceptable to relax atomicity and use compensating transactions instead? Discussing these will help you decide the right approach for different availability and consistency requirements. Today we'll examine why two-phase commit can block, why ideas like three-phase commit don't fully solve the problem in real systems, and what engineers do instead. We'll step through the protocol, a blocking example, the role of timing assumptions, and common practical workarounds. Two-phase commit works in two steps. First, the coordinator asks every participant if it can commit the transaction. Each participant replies yes or no. If every participant says yes, the coordinator then broadcasts a commit. If any say no, the coordinator aborts. Those two steps are why it's called two-phase. A classic blocking scenario is when the coordinator crashes at a critical point, for example, after it has collected affirmative votes but before it broadcasts the final commit. Participants that voted yes are now in a prepared state. They cannot safely commit or abort on their own, and so they must wait, which is the blocking behavior. Participants can't just decide for themselves because that could break atomicity. If one participant commits while others later abort, the system becomes inconsistent. To be safe, a participant needs the coordinator's final decision or some reliable way to learn the global outcome. Walk the sequence. The client starts the transaction with the coordinator. The coordinator asks participants to prepare. Participants reply with a vote. The coordinator then decides and tells everyone to commit or abort. If the coordinator disappears between the vote and the final broadcast, the participants that voted yes are stuck waiting in the prepared state. Three-phase commit adds a middle pre-commit stage intended to give participants enough information to finish without the coordinator. The idea is to create a state that is safe to commit so participants can proceed if the coordinator disappears at that point. The catch is that 3PC's safety depends on strong timing assumptions. It needs bounded network delays and predictable timeouts so participants can reliably infer the coordinator's failure. In real-world environments, public clouds, garbage-collected runtimes, overloaded nodes, or network partitions, those timing guarantees don't hold, and the protocol's reasoning breaks down. A truly non-blocking atomic commit would require a perfect failure detector, an oracle that instantly and correctly says whether a node has crashed. In networks with unbounded latency, such a detector is impossible. A delayed message might mean the node crashed, or it might simply be slow. Timeouts cannot reliably distinguish the two, so protocols that depend on such detectors risk unsafe decisions. Because you can't get the perfect detector, systems adopt practical mitigations. Replicating the coordinator or using durable logs helps recovery. Using consensus, Paxos, or Raft to drive the commit decision replaces the single coordinator with a replicated decision mechanism that tolerates failures. Alternatively, some applications avoid strict atomic commit and use Saga's sequences of operations with compensating actions to achieve eventual consistency. Each mitigation has trade-offs. Replication and consensus give stronger availability and fault tolerance but at higher complexity and latency. Durable logs help, but they require storage and recovery logic. Sagas avoid blocking but push complexity into application-level compensation. The right choice depends on which guarantees your system needs most. To summarize, two-phase commit is simple but can block when the coordinator fails. Three-phase commit tries to remove blocking but requires timing guarantees that are unrealistic in many environments. Because you can't reliably detect failures under unbounded latency, designs adopt practical mitigations, replication, consensus algorithms, durable logging, or compensating workflows, and accept trade-offs between safety, liveness, performance, and complexity. Today we'll rethink distributed transactions and the role of two-phase commit, or 2PC. We'll compare the two common patterns that people lump together, explain why 2PC often hurts latency in operations, and give practical guidance for when to use it and when to choose alternatives. At the heart of distributed transactions is a promise: atomic, all-or-nothing updates across multiple resources. That promise simplifies correctness. If you need transfers or inventory reservations to be exact, atomicity can make your application logic much simpler. But those guarantees come at a cost. People often blame distributed transactions for brittle failures and big slowdowns. Cloud services sometimes avoid offering full distributed transactions because of these latency and operational costs. Before rejecting distributed transactions entirely, you should separate two distinct flavors that are commonly conflated. Treating them as the same leads to poor architectural choices. I'll describe each and why their costs differ. First, the classic cross-resource 2PC. An external coordinator orchestrates autonomous resource managers, for example a payment gateway, an inventory database, and an order ledger running on separate systems. Each participant must persist a prepare state durable enough to recover after crashes. That durability often means extra disk syncs, which add latency, and the coordinator must exchange extra messages with each participant. Think about a payment, an inventory decrement, and an order write. The coordinator asks each system to prepare. Each one writes a prepared record to disk so that if it crashes, it can complete the transaction later. Those extra forced writes and network round trips are what make cross-resource 2PC expensive. The predictable overheads are extra FSANCS because each participant must persist prepare state, additional network messages for prepare and commit phases, and locks that are held during the prepare phase which can block other transactions. When failures occur, transactions can become in doubt and require manual or out-of-band intervention, increasing operational burden. By contrast, many modern distributed databases implement transactions across nodes but optimize the internal steps. Because the database controls both the commit protocol and the storage layer, it can reduce FSANCS, combine messages, and use techniques like leader locality, group commit, or consensus to make distributed transactions cheaper than stitching together separate systems with 2PC. When the database owns replication and partitioning, it can do clever things: batch commits together, avoid redundant disk syncs, and run consensus algorithms that are optimized for its topology. That means native distributed transactions often have much lower overhead than external 2PC across autonomous systems. Summarizing why naive 2PC deployments are slow: each participant must persist a prepared state, extra FSANCS. There are extra network round trips for prepare and commit, and locks during prepare block concurrency. These combine to produce measurable, sometimes order of magnitude, slowdowns compared with local commits. Here's a simple flow to visualize 2PC. The client asks the coordinator to run the transaction. The coordinator sends prepare requests to each participant. Each participant durably records a prepared state, causing an FSINC, and replies yes or no. If every participant says yes, the coordinator sends commit and participants durably record commit and release locks. If any say no, the coordinator sends abort. The painful cases or failures in between: if a participant crashes after prepare, its locks and prepared state can cause in-doubt transactions needing human intervention. If the coordinator crashes, participants must wait for recovery to learn commit or abort. Now some practical guidance you can apply when designing systems: weigh correctness needs, prefer native solutions where possible, avoid cross-partition writes on hot paths, use alternative patterns for long workflows, and prepare operational tooling when you must use 2PC. Don't reflexively ban them. When correctness and atomicity across independent systems are essential, for example in financial transfers or strict inventory reservations, distributed transactions can simplify application logic and prevent subtle bugs. The key is to weigh those correctness benefits against performance and operational costs. Prefer native distributed transactions inside a single, well-designed database if that database provides the transactional guarantees you need. Those systems can often deliver lower latency and fewer operational pitfalls than coordinating separate systems with XA or 2PC. Many latency problems are solved by data modeling. Co-locate frequently updated entities, denormalize where appropriate, and design microservices to minimize multi-node commits. Reduce the need for distributed commits on your hot paths. For long-running or multi-service workflows, prefer sagas with compensating actions, idempotent operations, or asynchronous eventual consistency. These patterns remove the need for synchronous distributed commits while still allowing you to maintain business invariance in a more operationally friendly way. If you must use cross-resource 2PC, prepare for the operational burden. Implement robust monitoring for in-doubt transactions, build automated recovery paths where possible, and maintain clear runbooks for handling coordinator or participant failures. Automation reduces the human toil when things go wrong. In short, distributed transactions are a trade-off, not an outright mistake. Distinguish external multi-resource 2PC from internally optimized distributed transactions in a single database. Use 2PC when atomicity across independent systems is essential, and prefer alternatives or native solutions when latency, scale, and operational simplicity matter more. Today we'll explore how a single database cluster can make multi-node updates behave like one atomic, ACID transaction even when data and processing are spread across many machines. Internal transactions are the database's built-in way to run transactions that touch multiple servers inside the same cluster. Every participating server runs the same engine and understands the cluster's transaction protocol, so the cluster itself coordinates the update, not an external manager. The goal is to provide ACID semantics across nodes. Atomicity ensures the whole multi-node change is all or nothing. Consistency preserves constraints and invariance. Isolation prevents interference between concurrent transactions, and durability makes sure committed updates survive failures. At a high level, when the application issues a transaction that touches multiple shards, the database identifies which nodes participate, assigns a coordinator role, and runs a distributed commit protocol among the participants. The outcome is either commit everywhere or abort everywhere. Databases use several techniques to implement these transactions. They try to route work so few nodes are involved, sometimes use synchronous replication so changes are durable immediately, use consensus algorithms for reliable leadership and durability, or run two-phase commit style protocols to guarantee atomicity across participants. Imagine a checkout that must update inventory in Frankfurt, create an order in the US, and log a fraud event in Singapore. This architecture simplifies application code because it removes the need for external transaction managers or manual compensation. It also gives stronger consistency for a single cluster and can perform better than stitching different systems together. There are trade-offs. Cross-node coordination can increase latency, particularly for transactions that span distant shards. The database engine becomes more complex, and architects must balance routing, replication, and consensus choices against latency and throughput needs. It's important to distinguish internal transactions inside a homogeneous cluster from distributed transactions that span different systems. When you cross product boundaries or include external services, you usually need standardized interfaces like XA, an external two-phase commit, or application-level compensation patterns because the systems don't share a single transaction protocol. Use internal transactions when you need correctness and simpler application logic within a single cluster. If your workload repeatedly touches many shards and needs very low latency, the coordination overhead may be prohibitive. Always weigh the cost of internal coordination against the benefit of stronger guarantees. A common commit pattern looks like this. The coordinator asks participants to prepare and collect votes. If every participant responds yes, the coordinator tells them to commit, otherwise it tells them to abort. In practice, databases optimize and combine these steps with replication and consensus to improve durability and performance. In summary, internal transactions allow a single database cluster to give you ACID across nodes by coordinating updates internally. That simplifies application logic and improves consistency, but introduces coordination costs and internal complexity that architects must consider. Today we explore atomicity when a single operation must span different systems. We'll look at what makes cross-technology transactions unique, why they're harder than single database transactions, practical failure modes, and common patterns engineers use instead of a universal two-phase commit. A heterogeneous transaction spans participants built on different technologies. Examples include two different relational databases, a relational database and a NoSQL store, a message broker and a payment gateway, or any mix of systems with different protocols and consistency guarantees. The key requirement is atomicity. The overall operation should appear to either fully commit across every participant or not commit at all. When all work stays inside one database, that system controls both protocol and storage. It can optimize locking, logging, and commit strategies to maximize throughput and reduce latency. Because the database implements the coordination mechanisms end-to-end, these transactions are predictable, efficient, and easier to reason about. There isn't a universally adopted, low-friction protocol every system implements in the same way. Different systems may not support the same two-phase commit protocols, may handle failures differently, and may expose different durability and ordering semantics. For example, coordinating an atomic commit between PostgreSQL, MongoDB, and a Kafka topic is much harder than coordinating across 3 PostgreSQL instances. Heterogeneous transactions increase operational complexity and the risk of inconsistent state. Network partitions, partial crashes, or mismatched retry semantics can leave some systems committed while others are not. This can lead to lost messages, duplicated work, or inventory/payment mismatches in real applications. Because classic distributed two-phase commit isn't always available or desirable, teams often use alternative strategies. 1. Use distributed two-phase commit only when all participants support it. 2. Compensating transactions or sagas for undoing work. 3. Idempotent operations so retries are safe. 4. Event-driven choreography to let services react and reconcile. 5. An external coordinator that manages retries and cleanup. 6. Transactional outbox pattern to reliably forward messages to systems like Kafka. Imagine a checkout that must deduct inventory from a SQL database, store session info in a NoSQL store, and enqueue a fulfillment message to Kafka. Achieving a single atomic commit across all three is difficult. Kafka doesn't participate in XA-style transactions with databases. So engineers pick patterns that trade strict atomicity for practical reliability. The transactional outbox pattern solves the Kafka problem by writing both the domain change and an outgoing message into the same database transaction. A separate forwarder reads the outbox table and publishes messages to Kafka, with idempotent publishes and retries. This provides strong guarantees that changes and messages won't be lost even if the broker can't join a distributed commit. A saga breaks a multi-step operation into a sequence of local transactions, each with a compensating action to undo it if a later step fails. Sagas may be orchestrated by a coordinator or implemented with choreography where services react to events. They provide eventual consistency and explicit recovery logic rather than a single atomic commit. Single technology transactions benefit from tight integration and efficient optimizations. Cross-technology transactions must bridge mismatched protocols and guarantees, making true atomicity harder to achieve. In practice, engineers choose patterns, transactional outbox, sagas, idempotency, choreography, or an external coordinator based on which trade-offs fit their system's reliability, latency, and operational complexity requirements. Today we're looking at how multiple independent systems can be treated as one atomic unit of work. Imagine several different products, a message broker and a database, for example, acting together so that either all changes happen or none do. That mechanism is called an atomic commit across heterogeneous systems. A distributed transaction spans more than one system or technology. Instead of updating only one component, a single logical operation includes multiple participants. The goal is to keep the whole operation atomic, commit everywhere, or abort everywhere. A common example is message processing. A consumer reads a message from a queue, updates a database, and then acknowledges the message so it won't be redelivered. Those three steps look simple, but when they involve separate systems, we need a way to make them behave as one. With heterogeneous distributed transactions, the message acknowledgement and the database commit can be made atomic. Even if the message broker and the database are different products on different machines, we can arrange for both the acknowledgement and the database writes to either both happen or both not happen. When the ACK and the DB writes are committed together, failure modes become deterministic. If either side fails, the entire transaction is aborted. The broker keeps the message for redelivery and any partial database changes are rolled back. This removes unpredictable partial states. This behavior supports what people often call effectively exactly once processing. The system may retry processing several times, but after a successful commit, the visible outcome is as if the message were processed only once. Any partial effects from failed attempts are discarded when the transaction aborts. The guarantee depends on every participant supporting a common atomic commit protocol. In practice, this means the systems involved must be able to participate in the same coordinated protocol, for example, a two-phase commit, so they can agree to commit or abort together. If a side effect cannot join that protocol, it can break atomicity. For example, if processing triggers a third-party notification API that doesn't support coordinated commits, that API might already have delivered the notification even if the transaction later aborts. That leads to duplicates or other visible inconsistent effects. There are two common design choices for reliable message processing. One is to ensure critical side effects can participate in a coordinated commit. The other is to design external interactions so they are idempotent or otherwise tolerant of duplicates. Each approach has trade-offs in complexity, performance, and reliability. Let's walk a simple textual flowchart step by step. Step 1. Read message from queue. Step 2. Start a distributed transaction that covers both the broker and the database. Step 3a. Prepare the database changes. Step 3b. Prepare the broker acknowledgement. Step 4. If all participants report ready, commit on all participants. Step 5. Acknowledge the message and persist database changes. If any participant cannot commit, abort, roll back database changes and keep the message in the broker for redelivery. The crucial concept to take away is the atomic commit protocol. It's the mechanism that lets heterogeneous systems either all commit or all abort together. When everyone can participate, you get deterministic failure handling and effectively exactly once outcomes. When someone can't participate, you must handle duplicates or find other patterns to preserve correctness. Today we'll study XA, the long-standing standard that lets different transactional resources participate together in a single distributed transaction. We'll focus on what XA is, how participants cooperate, how the two-phase commit works, and what happens when failures occur. XA, short for Extended Architecture, is a standard dating back to 1991. Its purpose is to enable two-phase commit across different kinds of transactional resources like databases and message brokers so they can behave as a single atomic transaction even though they're independent systems. An important point, XA is not a new network protocol. It's an API contract, originally a C API, that transaction coordinators and resource managers implement. Languages provide bindings. For example, Java applications use the Java Transaction API, JTA, which implements XA semantics and lets JDBC and JMS drivers hook into XA coordinated transactions. Here's how drivers and resource managers cooperate. When your application uses an XA-capable client library or driver, the driver asks whether an operation should be enlisted in the current distributed transaction. If yes, the driver passes an XA context to the resource manager and registers that resource with the transaction coordinator. From that point, the coordinator controls the lifecycle for that participant. Where does the coordinator live? XA specifies the interface but not deployment. Practically, the coordinator is commonly a library loaded into the same process as the application, for example, a transaction manager in an application server or a framework component in a microservice. That local coordinator tracks enlisted participants and writes the transaction outcome to a local on-disk log so it can finish recovery reliably. The core of XA is two-phase commit. In phase 1, the coordinator asks each participant to prepare. They do everything needed and record their ability to commit, but do not make the change visible yet. In phase 2, based on the prepare responses and coordinator decision, the coordinator instructs participants to commit or to roll back. Imagine this flow. The application uses a coordinator which has enlisted participant A, say a database, and participant B, for example a message broker. In phase 1 the coordinator sends prepare to each participant, each marks its changes as prepared. In phase 2 the coordinator sends commit or rollback to finalize the transaction across all participants. Now consider failures. Because the coordinator often runs in the same process as the application, it shares that failure domain. If the process crashes after participants have been asked to prepare but before the coordinator sends the final commit or rollback, those participants will remain in a prepared but uncommitted state. We call this the in-out problem. Resources are blocked, holding locks or prepared changes, until they hear the final decision. Recovery requires the coordinator process to come back up. On restart, the coordinator reads its local on-disk transaction log, determines the correct outcome for in-out transactions, and then calls back into the drivers to tell each participant to commit or abort. Note that resource managers cannot unilaterally resolve the decision. Resolution goes through the client library that implements XA callbacks. A concrete example, a Spring Boot microservice using JTA coordinates a transaction that writes or wrote a PostgreSQL and publishes an event to ActiveMQ. During prepare both PostgreSQL and ActiveMQ mark their changes as prepared. If the microservice crashes at that point, both resources are left waiting. When the microservice restarts, its embedded transaction manager reads the on-disk log and completes the transaction by instructing both resources to commit or abort through their XA drivers. To summarize, XA defines an API for two-phase commit across heterogeneous resources and is widely supported by databases and enterprise brokers. A common deployment pattern is an in-process coordinator that keeps a local log, This works well for coordinating transactions but creates a recovery dependency. When the coordinator's host fails while participants are prepared, those participants remain in doubt until the coordinator is brought back and completes recovery. Today we're going to look at why an in-out distributed transaction can do more than clutter logs. It can actually immobilize parts of your system by holding locks for too long. An in-out transaction is one that is neither committed nor aborted because the transaction coordinator and participants are still negotiating the final result. Databases acquire locks to prevent concurrent corruption, to stop two transactions from making conflicting changes at the same time, ensuring consistency. When a transaction modifies rows, most databases take exclusive row-level locks. These exclusive locks prevent dirty writes and must remain until the transaction commits or aborts. Under serializable isolation with two-phase locking, the database also keeps shared locks on rows it reads. Those read locks cannot be released while the transaction is still active. In a two-phase commit, locks are retained for the entire time the transaction is in doubt, that is, while the coordinator and participants decide whether to commit or abort, because releasing them would break correctness. Imagine a ticketing checkout that spans multiple services in a distributed transaction. The seat rows touched by that transaction become locked, preventing others from changing them until the transaction resolves. If the transaction coordinator crashes or is unreachable, those locks remain held until the coordinator recovers or an administrator intervenes. If recovery is slow, say 20 minutes, locks block activity for that whole time. If the coordinator's log is lost, locks can remain effectively forever. While locks are held, other transactions that need to update the same rows are blocked. Depending on the DB and isolation level, even reads may be blocked. As a result, unrelated user requests queue up or fail. The practical consequence is that large portions of your application may become unavailable despite most of the system being otherwise healthy. An in-out transaction becomes a choke point that propagates latency and outages. Let me walk you through a simple text flow. Start begin distributed transaction acquire locks, read/write, prepare phase, participants vote, coordinator waits for votes if coordinator is reachable, commit or abort release locks. Now the failure path, if coordinator crashes after prepare transaction becomes in-out locks remain held other transactions blocked admin recovery or coordinator restart needed to resolve and release locks. In-out transactions are not just delayed work, they are operational hazards. They can silently block traffic, require human intervention, and cause outages that are hard to diagnose because most services appear healthy. To mitigate, detect in-out transactions quickly, restore or failover coordinators fast, provide admin tools to resolve stuck participants, avoid long-lived distributed transactions when possible, and consider alternative patterns like eventual consistency and compensating actions. Today we'll examine a practical problem in distributed transactions, when two-phase commit gets stuck and leaves in-doubt transactions. I'll explain what causes them, why they're dangerous, how administrators resolve them, and what design choices reduce their likelihood. Start with the basics. Two-phase commit uses a coordinator that asks participants if they're ready and then records a global decision in a durable log. That log lets the coordinator recover after a crash and finish any pending work. The promise is strong atomicity across distributed resources. An in-doubt transaction is one where the coordinator, for some reason, can no longer determine whether to commit or abort. The system is left uncertain about the transaction's final state, and that uncertainty creates practical problems. These situations arise for various reasons. The coordinator's log may be lost or corrupted, a software bug might prevent proper recovery, or the coordinator may be partitioned from some participants. Any of these can make the coordinator forget or be unable to learn the global decision. A critical point: the database preserves the locks held by an in-doubt transaction, even across restarts. This is intentional. If the system released those locks automatically, another transaction could proceed and later conflict with the original transaction if it eventually commits, breaking atomicity. Because locks are preserved, the in-doubt transaction sits frozen and blocks resources. It can prevent other operations from making progress and degrade availability, sometimes severely, until someone intervenes. Restarting servers or services often won't help. A correct 2PC implementation will maintain lock state across restarts to preserve correctness. That means automatic recovery may be impossible, manual intervention is often the only escape. Resolving an in-doubt transaction requires an administrator to make an explicit global decision: commit or abort. They must inspect each participant to see whether any already applied or aborted locally, then choose a consistent action and apply it everywhere. This detective work can be time-consuming and stressful, especially during outages. Here's a simple flow you can picture. If the coordinator crashes, we first ask whether its log is intact. If yes, automatic recovery proceeds and the coordinator finishes 2PC. If no, the transaction becomes in doubt and locks are preserved. From there, an administrator must inspect participants and choose to commit or abort, then apply that decision consistently across all participants. Some XA-style transaction managers offer heuristics. A participant can unilaterally decide to commit or abort an in-doubt transaction. This breaks atomicity guarantees but can free resources and restore service in extreme cases. Heuristics are a last resort for emergency recovery, not for routine use. To reduce the chance and impact of in-doubt transactions, prefer designs that avoid heavyweight distributed locking. Keep distributed transactions short, make operations idempotent, use compensating transactions or sagas for long-running work, and ensure transaction logs in coordinator state are highly durable and replicated. Finally, prepare for the worst, maintain clear runbooks for manual resolution, train operators to inspect participants safely, and limit the use of true 2PC to cases that truly require it. When a coordinator does get stuck, manual resolution or a carefully considered heuristic is often the only way out. Today we'll examine why XA, two-phase commit, though powerful, brings operational costs and architectural pitfalls. XA keeps multiple, heterogeneous data systems consistent in a single transaction, but that very power hides serious runtime and design risks. Let's unpack them step by step. Start with the core promise. XA coordinates a single transaction across different databases or systems so they appear consistent. That sounds ideal for heterogeneous environments where you need atomicity across multiple stores. A crucial and often missed fact is that the transaction coordinator is itself a stateful data store. It writes durable logs recording prepare and commit decisions. That makes the coordinator as important to protect as any primary database. If the coordinator runs on a single machine without robust replication, it becomes a single point of failure. When it crashes, client servers can block waiting for outcomes of in-doubt transactions. Some XA implementations trade simplicity for resilience and ship with little or no high availability features. Modern cloud-native apps are typically stateless. Persistent state lives in databases so instances can be added or removed freely. Embedding an XA coordinator inside an application server breaks that assumption. The coordinator's logs are durable system state. Once those logs are required for recovery, those servers are no longer safely disposable and need replication and backups. XA is intentionally conservative to work across diverse systems. It relies on the lowest common denominator of participant capabilities. That design imposes limits. XA cannot, for example, perform cross-system deadlock detection because disparate systems have no shared lock-weight protocol. Two concrete limitations: XA can't do cross-system deadlock detection, and it's incompatible with serializable snapshot isolation, SSI. SSI needs mechanisms to identify transactional conflicts across systems, which XA does not provide. If all participants share a common internal protocol, as inside a single database cluster, you can implement richer distributed transaction protocols, even distributed SSI. That shared implementation lets you do things XA cannot when participants are heterogeneous. Here's the two-phase commit flow in simple terms. The coordinator tells participants to prepare. Participants vote yes or no. Only if everyone votes yes does the coordinator send commit. The problem arises if anyone is down during this protocol. The transaction becomes in doubt. Other services that need that outcome may block waiting for resolution, so a small outage can halt wider progress. Because two-phase commit requires every participant to respond, a failure in one participant where the coordinator can block commits system-wide. In effect, distributed transactions amplify the blast radius of partial outages and work against resilient, fault-tolerant design goals. Abandoning consistency entirely isn't necessary. There are practical patterns that trade synchronous strong guarantees for better operability, sagas and compensating actions, designing idempotent operations with exactly once semantics where feasible, and relying on consensus or replicated state for critical coordination. Each option has trade-offs. They relax atomic cross-system commit in favor of availability and simpler failure modes. If you must use XA, treat the coordinator like any primary data store, deploy it with HA, replication, and backups, avoid embedding it in ephemeral stateless app instances unless you also provide durable, replicated storage for its logs, monitor for and remediate in-out transactions quickly, and consider limiting XA to environments where participants are homogeneous or under your control. In summary, XA solves cross-system consistency but creates operational and architectural burdens because the coordinator is stateful and two-phase commit requires all participants to be available. These properties make distributed transactions fragile in heterogeneous, cloud-native environments. We'll study practical alternatives like sagas, compensating actions, and replicated coordination in chapters 11 and 12. Today we will explore consensus, how distributed systems reliably choose a single outcome when many independent processes make competing proposals. I'll walk you through what consensus is, the properties a correct algorithm must satisfy, common failure models, and the trade-offs designers face. Start with a simple idea. Consensus is the mechanism that lets multiple, independent processes agree on a single outcome. Think of competing requests or proposals that need a single, consistent decision. To make this concrete, imagine several users trying to buy the last concert ticket, bots racing to register the same username, or microservices proposing which replica should host a shard. Each scenario produces conflicting proposals that a consensus protocol must resolve. Conceptually, nodes propose values, the consensus protocol runs, and the system reaches a single decision. For example, front-end servers propose customer IDs for that last ticket, consensus picks one ID and the system behaves consistently. A correct consensus algorithm satisfies four core properties: uniform agreement, integrity, validity, and termination. We'll define each precisely and explain why they matter. Uniform agreement is about consistency. No two nodes should ever decide on different values. If two nodes decide differently, the system is inconsistent and application-level correctness breaks. Integrity means decisions are final for each node. A node must decide at most once. You cannot have a node flip its decision later. That would undermine trust in the system's state. Validity ensures the protocol doesn't invent values. Any decided value must have come from a real proposal by some node. This prevents trivial or meaningless outcomes. Termination is the liveness guarantee. Every node that hasn't crashed should eventually reach a decision. Without termination, the system might stall and never make progress. The first three properties, agreement, integrity, and validity, are safety properties. They prevent bad outcomes. Termination is a liveness property. It guarantees the system keeps moving forward. Both kinds of guarantees are important but address different risks. Agreement and integrity alone don't stop trivial protocols. For example, a protocol that always decides null would be consistent and final, but useless. Validity forces the protocol to pick something meaningful from the actual proposals. If you ignore fault tolerance, one easy way to get agreement is to designate a single authoritative node to decide every time. This solves agreement immediately, but it creates a single point of failure. If that node dies, the whole system stalls. Two-phase commit, 2PC, illustrates the problem. The coordinator decides and drives participants. If the coordinator crashes, participants may be left waiting forever, violating termination in a crash-stop model. Most consensus theory assumes a crash-stop failure model. When a node crashes, it simply disappears and never comes back. Any algorithm that needs the node to recover cannot guarantee termination in this model. To guarantee termination, you need a majority of nodes to be up and able to communicate. That majority forms a quorum and can make progress even while some nodes are down. In practice, consensus protocols are designed so safety, agreement, integrity, and validity holds under almost any condition, even if many nodes fail or the network is chaotic. A severe outage may halt progress, breaking termination, but it should never let the system make inconsistent or invalid decisions. The common model assumes non-Byzantine faults. Nodes either follow the protocol or crash. If nodes can act arbitrarily or maliciously, sending conflicting messages to different peers, they can break safety. There are consensus algorithms that tolerate Byzantine faults, but they require stronger assumptions and more nodes. A classic result says you can tolerate Byzantine faults only if fewer than 1/3 of the nodes are Byzantine. These protocols are powerful but more complex and costly. Designers choose protocol trade-offs based on expected faults and system goals. Crash-stop protocols are simpler and cheaper. Byzantine-tolerant protocols add complexity for adversarial environments. Performance and implementation complexity also influence choices. In summary, consensus is about reliably choosing one proposal among many. Achieving it means satisfying safety properties, agreement, integrity, validity, and a liveness property, termination, under a chosen failure model. Practical protocols balance these guarantees against performance, complexity, and the types of faults the system expects. Today we'll explore how consensus protocols like view-stamped replication, Paxos, Raft, and Zab are used not just to decide a single value, but to build a durable, totally ordered log that all replicas share. These algorithms aim to keep replicas consistent despite crashes and network faults, and the key idea tying them together is agreement on a sequence of actions so every node applies operations in the same order. Start with the big names: VSR, Paxos, Raft, and Zab. They share high-level goals: safety under crashes and partitions, but they differ in protocol details, design trade-offs, and developer ergonomics. You don't need to memorize every message in each protocol. Focus on the shared concept of ordering operations. In theory, consensus often means deciding one value while ensuring agreement, integrity, validity, and termination. Real systems almost always need many decisions over time, a stream of values. So we move from single-shot consensus to deciding a sequence, a log of commands that every replica applies in the same order. Total order broadcast, also called atomic broadcast or log replication, is the mechanism we build from consensus. It guarantees that all participants receive the same messages in the same order, and typically exactly once. This is the abstraction that replicated state machines rely on to maintain consistent state. Think of a group chat, a multiplayer game, or a replicated database. Users issue commands, send messages, move characters, commit transactions. If replicas or players see different orders of those commands, states diverge and behavior becomes incorrect. Enforcing a shared order prevents such divergence. Map the classic consensus properties to total order broadcast. Agreement means all replicas deliver the same messages in the same order. Integrity ensures no messages delivered more than once and only messages that were actually sent are delivered. Validity means delivered messages originated from a real sender, not fabricated. And termination means broadcasts eventually get delivered if the system isn't too faulty. Practical protocols often use a replicated log driven by a leader. A leader accepts client commands, appends them to its log, and coordinates replication to followers. Once entries are safely replicated and committed, followers apply them in order. Raft, VSR, and Zab are designed this way. Paxos can be used similarly in the multi-Paxos optimization. Multi-Paxos is Paxos tuned for sequences. A stable leader avoids repeating the expensive leader election phase for every entry. Instead, the leader keeps proposing new log entries, amortizing the setup cost across many decisions. This is why production use of Paxos usually looks like a leader-driven log protocol. Building consensus from scratch is subtle and error-prone. Prefer battle-tested implementations, for example, ET's Raft, Zookeeper's Zab, or established Paxos libraries unless you are researching new protocols. Choose an algorithm based on engineering trade-offs: Raft for clarity and ease of implementation, Paxos for historical rigor and some optimizations, and VSR or Zab for their particular design goals. Let's walk through a simple leader-based replication flow. Client sends command to leader. The leader appends the command as a new log entry. The leader sends the entry to followers to replicate. Followers write the entry to their logs and send acknowledgements. When the leader sees enough acknowledgements, a quorum, it marks the entry committed. The leader then tells followers to apply committed entries. They update their state machines and the leader responds to the client. This ensures the same entry is applied in the same order everywhere. To close, single-value consensus is a useful theoretical tool, but real distributed services need a continuous, totally ordered log of decisions. Modern consensus systems focus on replicating a sequenced log so every node sees the same ordered stream of actions. That design is both more efficient and directly matches the needs of replicated state machines and distributed applications. Today we'll unpack how distributed systems elect a leader without already having one. We'll see the apparent paradox: you need a leader to pick a leader, and then break down the practical recipe modern algorithms use to bootstrap leadership reliably and safely. Begin by noticing a simple likeness. In single leader replication, one node orders all writes, and followers apply them in that same order. That is exactly what total order broadcast guarantees: a single ordered stream of updates applied consistently by everyone. This similarity raises a crucial question we often gloss over: who chooses that leader? If we handpick the leader manually, the system behaves like a dictator, correct while the leader lives, but stuck if it dies. That violates the termination requirement. The system must make progress even when nodes fail. If humans assign the leader, only that node can accept writes and decide order. That design can be safe, it preserves consistency, but it isn't autonomous. When the leader crashes, the cluster stalls until an operator reconfigures a new leader. In other words, safe, but no automatic liveness. To recover automatically, followers can try to become leader after a failure. That gives resilience, but introduces a classic hazard: split brain. If two nodes believe their leader at the same time, they can accept conflicting rights and corrupt the replicated state. Preventing that requires the nodes to agree on exactly one leader. This creates an apparent paradox: single leader replication needs a leader, consensus needs leader election, but leader election looks like it needs consensus. How do we escape this circularity? The answer is in the disciplined rules these algorithms use to let any node propose leadership while preserving safety. Modern consensus algorithms combine three key ideas. Together they let the cluster elect a leader without a pre-existing dictator: 1. Quorum voting, 2. Ordered/numbered proposals, and 3. Mechanisms to avoid livelock and make progress under realistic timing assumptions. First, quorum voting. Any node can start an election and ask a majority of nodes to vote for it. Because any two majorities overlap, two different nodes cannot both get a majority at the same time unless at least one node breaks its promise. This overlapping quorum property guarantees that at most one leader can be elected for a given term, preserving uniqueness. Second, numbered proposals or terms. Elections and proposals carry increasing identifiers, terms, epochs, or proposal numbers. Nodes promise to only accept votes or proposals with higher numbers than they've already seen. That prevents old, delayed messages from re-establishing stale leaders and helps drive the system toward a single, current leader. Third, mechanisms to avoid livelock. Theoretical results show that purely asynchronous systems can get stuck in endless contention. Practical systems add assumptions or randomness to break ties. For instance, Raft uses randomized election timeouts so candidates rarely collide. Paxos uses a prepare/accept two-phase dance with numbered proposals so a quorum accepted value can't be contradicted later. These tactics help guarantee progress when the network behaves reasonably. Here's a short, text-based flow of a typical election, and I'll walk you through it step by step. Candidate starts increments term/proposal number sends request vote to quorum. If majority granted? Yes, becomes leader, starts sending heartbeats/accepts rights. If majority not reached, wait, randomized timeout, try again with higher term. Also, followers reject lower term requests and accept only highest numbered election scene. This sequence shows how any node can propose, solicit votes, and become leader if it wins a majority, while term numbers and voting rules keep old or conflicting candidates from taking over. Now some concrete algorithms. RAFT, nodes increment term, request votes, and win leadership after a majority. Randomized election timeouts reduce collisions and make leader election likely to succeed. Paxos and multi-Paxos, proposers use increasing proposal numbers and a prepare/accept protocol so that a value accepted by a quorum is preserved. Multi-Paxos optimizes repeated decisions under a stable leader. Zookeeper's ZAB combines leader election and total order broadcast guarantees with quorum-based voting to choose a primary and ensure durable replication. Why all this careful machinery? Safety, no two leaders for the same term and no lost committed entries, is preserved through quorum intersection and monotonically increasing terms. Liveness, eventual progress, however, requires additional timing assumptions. FLP tells us we can't have both guaranteed safety and guaranteed termination in a completely asynchronous system with crashes. So practical systems accept assumptions like eventual synchrony, timeouts, or randomized backoff to make progress in real networks. In summary, we break the need a leader to elect a leader loop by changing the rules. Every node may propose leadership, but votes, term numbers, and timeout/randomization rules constrain outcomes so the cluster converges on a single leader. Safety is enforced by quorum intersection and monotonic terms. Progress requires reasonable timing assumptions. This is the pragmatic compromise that underlies RAFT, Paxos, ZAB, and production distributed systems like ETD and Zookeeper. Today we will unpack how leader-based distributed consensus stays safe. We'll look at epochs, also called ballots, views, or terms, how elections work, why quorums matter, and how these pieces prevent conflicting decisions even when nodes fail. First, an epoch is simply a number attached to an election round. Different protocols call it different names, but the idea is the same. Epochs are totally ordered and they strictly increase whenever nodes start a new election. That ordering is what lets the system know which leader is more recent. When nodes think the current leader is down or unreachable, they start an election and increment the epoch number. That bump is a signal to everyone that we are trying to pick a new leader for a newer epoch. Because epoch numbers always rise, a leader elected in a higher epoch overrides any leader from a lower epoch. However, a node that believes it's the leader cannot just start making decisions. It first needs to ensure that no other node was elected in an even higher epoch in the meantime, otherwise conflicting decisions could occur. To be safe, a prospective leader solicits votes from a quorum of nodes, typically a majority, such as 3 out of 5. Each node grants its vote only if it doesn't already know about a higher numbered epoch. By collecting a quorum of votes, the candidate gains confidence that enough of the cluster recognizes its authority. There are effectively 2 voting rounds. The first elects the leader for a specific epoch. The second is used to approve a concrete proposal, for example, a log entry or value, that the leader wants to choose. Both rounds use quorums. The crucial safety property is quorum overlap. Any two quorums in the system must share at least one node. That guarantees that some node that took part in the leader's election will also take part in the proposal approval. That shared node carries knowledge forward and prevents contradictory decisions. Here's a concrete example. In a 5-node cluster A through E, suppose A is elected at epoch 10 when nodes A, B, and D vote for it. Later, A proposes a value and receives affirmative replies from A, B, and C. The election quorum, A, B, D, and the proposal quorum, A, B, C, overlap on A and B. Because none of the replying nodes report a higher epoch, A can safely conclude no newer leader was chosen and commit the decision. Think of the process like a flowchart. First, when the leader appears to have failed, nodes bump the epoch. A candidate then asks for votes and waits for a quorum. If it gets a quorum, it becomes leader for that epoch. Next, it proposes a value and waits for a proposal quorum. If those replies show no higher epoch, the leader commits the decision. Each step checks epochs to avoid conflicting leadership. This two-stage voting might look like two-phase commit at first, but there are important differences. In 2PC, the coordinator is fixed and progress requires every participant to respond yes. There's no majority quorum concept. Consensus protocols, by contrast, tolerate failures because only a majority is needed, and leadership is obtained through an election. Another key distinction is that consensus algorithms include explicit recovery and log merge procedures. After a new leader is chosen, nodes exchange their logs and reconcile any differences so that the chosen decisions are preserved and no conflicting state survives. These recovery steps, combined with monotonic epochs and quorum overlap, make leader-based consensus safe and fault-tolerant. To summarize, epochs give us a strict ordering of leadership attempts, quorum voting prevents split decisions by requiring broad support, quorum overlap links election results to proposal approvals so knowledge carries forward, and recovery plus log merge guarantee the system stays safe over time. Together, these mechanisms let leader-based consensus tolerate failures while avoiding conflicting decisions. Today we'll study consensus in distributed systems, what guarantees it gives, at what cost, and where it tends to be fragile. We'll keep this practical, focusing on the trade-offs engineers face when choosing consensus. Consensus gives three core, provable safety guarantees. Agreement means all non-faulty nodes decide the same value. Integrity means votes can't be forged or counted twice, each decision reflects legitimate votes. Validity means the decided value comes from a valid proposal. These guarantees hold even when some machines or links fail. Because consensus provides total order broadcast, we can implement linearizable operations on top of it. That means the system behaves as if operations ran atomically in a single global order, despite concurrency and failures, a very strong correctness property for distributed services. The decision process in consensus is like synchronous replication. Nodes exchange votes and wait for a quorum before committing a proposal. That waiting is necessary for the safety guarantees, but it creates latency and limits throughput compared to asynchronous replication modes where a replica can accept writes immediately. Many systems accept the trade-off. They sacrifice some write latency and throughput to get strong durability and linearizability. Others choose weaker durability to optimize for low latency writes. It's a conscious design choice based on application needs. A fundamental constraint: to tolerate F crash failures, you need at least n equals 2F plus 1 voting nodes. For example, to tolerate one failure, you need 3 nodes, to tolerate 2 failures, you need 5 nodes. This majority requirement is central to most consensus protocols. When the network partitions, only the side with a majority of voters can continue to make progress. Minority partitions are blocked. This reflects the cost of strong consistency. In the presence of partitions, availability can be sacrificed to preserve safety. Classical consensus assumes a fixed set of voters. Dynamic membership, adding or removing nodes, is possible but more complex and error-prone. Production systems often use careful procedures or joint consensus transitions to change membership without violating safety. Implementations rely heavily on timeouts to detect failures and drive leader elections. In environments with variable latency, transient delays can make a healthy leader look failed. These false suspicions don't break safety, but they hurt liveness. Frequent elections waste resources and slow progress. Some protocols show pathological behavior under certain network patterns. For instance, raft clusters have been observed to oscillate leadership or repeatedly step down when a single link is flaky. Even with a mostly healthy network, a few unreliable links or uneven latencies can severely degrade throughput and availability. Engineers pick consensus for scenarios where its guarantees are essential: coordination and state stores for orchestration, like ECT for Kubernetes, distributed SQL databases needing strong consistency, CockroachDB, FoundationDB, and systems for service discovery or distributed locking, Consul. When eventual consistency and higher performance suffice, designers often avoid consensus. Before choosing consensus, ask: do you need linearizability? Can you tolerate higher write latency? Are you prepared for operational complexity, timeouts, leader elections, membership changes? Is the network environment stable and low latency enough? These questions help decide whether consensus is worth the cost. Here's a simple decision flow. First, do you need strong linearizability? If not, pick weaker consistency for better performance. If yes, next ask whether you can accept higher write latency and operational complexity. If you can, use consensus but provision at least TUF plus 1 nodes and plan careful membership changes. If you cannot accept the costs, explore alternatives like asynchronous replication or conflict resolution models. Finally, if your deployment is geo-distributed, factor in higher latency and more frequent leader instability that might push you away from consensus. To summarize, consensus gives powerful, provable safety and enables linearizable systems, but the price is visible: higher latency and throughput costs, operational complexity around membership and leader election, and fragility to variable network conditions. Use consensus where correctness demands it, and choose simpler models where performance and availability are more important. Today we'll explore why systems like Zookeeper and ECT exist. At first glance they look like tiny key-value stores, but their real role is to coordinate distributed systems. We'll break down what they do, how they differ from ordinary databases, the coordination primitives they expose, and why implementing consensus is essential for that job. At first glance Zookeeper and ECT look like lightweight databases. They give you a key-value API, let you read and write, and let you traverse keys like a file system. That similarity can be misleading, because their design goals are quite different from a general-purpose database. The short answer to why they implement consensus is that they are coordination substrates. They store a small, highly consistent, durable view of system metadata, the tiny authoritative facts that many distributed processes must agree on to cooperate reliably. Think of them as the brains coordinating cluster-wide decisions like leader election, membership, locks, and service discovery. Application developers rarely use Zookeeper or ECT as a primary database. Instead, these systems run as shared infrastructure for higher-level projects. Examples include HBase, Hadoop YRN, OpenStack Nova, and Kafka using Zookeeper historically, and Kubernetes using ECT to store cluster state. These projects need a small, strongly consistent source of truth that they can rely on even during failures. What sets these systems apart from conventional databases? First, they're optimized for a small in-memory working set, so reads and writes are very fast. Second, they use ordered replication, a total order broadcast implemented via a consensus protocol, so every replica applies updates in the same global order. Third, they focus on coordination primitives, not bulk storage features. Total order broadcast is the backbone of strong consistency here. Consensus ensures all updates are seen in the same sequence by every replica. Zookeeper uses ZAB and ECT uses Raft. That single agreed order is why you can rely on these systems for coordination instead of getting conflicting views that lead to split brain. These systems organize keys hierarchically, for example /services/web/instances, which makes it easy to group related keys and follow conventions like per-service registration. The file system like layout is simple and intuitive for representing structured metadata. Ephemeral nodes or leases let a client create entries that vanish automatically if the client disconnects or its lease expires. This is ideal for representing liveness. If a service registers itself and then crashes, the ephemeral entry disappears and other components detect the failure quickly. Sequential nodes are keys created with monotonically increasing suffixes, like /lock/lock 0000001. Combined with ephemeral nodes, sequential nodes enable leader election and fair locking. The node with the lowest sequence number becomes leader, and when it dies, the next one takes over. Watches or change notifications let clients subscribe to keys or directories and receive updates when data changes. This is much more efficient than polling. Controllers and services can react instantly to configuration changes or membership updates. Modern systems offer leases and TTLs for transient state and lock timeouts. They also support transactions and conditional updates, compare and swap, which let clients perform atomic multi-key operations or checks like only take this lock if it's free. Those primitives make coordination logic safe and predictable. Access control ACLs or role-based permissions and authentication reduce the risk of accidental or malicious changes to critical metadata. Since these systems hold the authoritative state for coordination, guarding who can modify that state is important. Concrete uses include leader election for controllers, for example, Kubernetes controllers using leases so only one reconciler is active. Here's a simple leader election flow. Candidates create ephemeral sequential nodes under a shared path like /election. Each participant checks the directory. Whoever has the lowest sequence number is the leader. If that leader dies, its ephemeral node disappears and the others see the change via a watch. They re-evaluate and the next lowest node becomes leader automatically. This combination of ephemeral and sequential nodes plus watches makes leader election simple and robust. Consensus adds complexity and latency compared to eventually consistent approaches, but it guarantees a single, ordered truth. For coordination metadata, divergent views can cause split brain, lost updates, or simultaneous exclusive actions. Strong consistency prevents those failure modes and makes it safe for distributed processes to rely on the shared state. In short, Zookeeper and ECT are intentionally narrow tools. They trade general-purpose storage capacity for a small, predictable, strongly consistent coordination substrate. Implementing consensus gives them the single-ordered truth that distributed systems need to make coordinated decisions safely and quickly. Today we'll learn how to build reliable distributed locks by combining an atomic compare and set operation with a consensus protocol and expressing locks as time-bounded leases. I'll first give a high-level picture, then we'll drill into each piece and practical considerations. Start with compare and set, or CAS. CAS is an atomic operation that says, if the current value equals X, set it to Y, otherwise fail. When many nodes try the same CAS at once, CAS ensures only one succeeds. That single winner property prevents two services from both thinking they hold a lock or both making conflicting updates. CAS on a single machine is atomic, but in a distributed system we need that atomicity to hold even when machines crash or messages are delayed. If the CAS state isn't agreed on by a quorum of replicas, different nodes could see different outcomes after failures. So we must make CAS operations durable and agreed upon across nodes. To make CAS reliable across crashes and network hiccups, we use a consensus algorithm such as Raft or Paxos. Consensus ensures linearizability. Every completed operation appears to take effect at a single, well-defined point in time. In practice, that means the CAS decision is replicated and ordered so all nodes agree which attempt won. In practice, distributed locks are implemented as leases. A lease grants ownership for a fixed time window. When the window ends, the lease expires automatically. This prevents permanent resource loss. If a client crashes or gets paused, the lock will eventually be available to others without manual intervention. There are three operational knobs you must tune. First, choose a lease duration long enough to tolerate transient pauses but short enough to limit the risk if the holder fails. Second, support renewals so a healthy holder can extend before expiry, but ensure buggy clients can't extend forever. Third, use fencing tokens or monotonically increasing ownership identifiers so delayed or partitioned clients cannot disrupt a new owner after a failover. Here's a step-by-step flow to visualize the lifecycle. The client proposes a CAS to acquire the lock. Consensus replicates the proposal and decides which proposal wins. If the client wins, it receives a lease containing a token and an expiry time. The client uses the resource and either renews before the expiry or lets the lease expire, at which point the next contender can attempt the same process. Now consider failures. If a holder crashes, the lease eventually expires and others can acquire it. That's why bounded leases are important. If messages from a previously valid holder arrive late, fencing tokens ensure those late operations are rejected by the current owner. And because CAS is decided under consensus, split-brain scenarios where two nodes both think they hold the lock are avoided. Consensus chooses a single outcome. This pattern is widely used, electing a leader among microservice instances, ensuring only one replica runs a scheduled job, coordinating safe schema migrations, or managing cache invalidation across replicas. In each case, the combination of CAS, consensus, and leases gives strong safety and predictable failover behavior. Before we finish, a quick checklist you can use in real systems. 1. Ensure CAS is backed by consensus so lock decisions are linearizable. 2. Implement leases with a sensible duration and support timely renewal. 3. Add fencing tokens or monotonically increasing IDs to avoid late arriving clients interfering. And 4. Monitor lease expirations and renewal failures so you can detect and respond to problems. In short, use CAS to pick a single winner among concurrent attempts, rely on consensus to make that outcome atomic and visible consistently across failures, and implement the lock as a time-bounded lease so ownership is automatically relinquished if the holder fails or is paused. This combination gives robust, predictable distributed locking. Today we'll study fencing tokens, a simple but powerful technique to prevent stale leaders from corrupting shared resources in distributed systems. We'll see the problem, the solution, how systems like Zookeeper help, and some practical rules to follow. A plain lock or lease tells you who should act, but it doesn't handle time. If a process holding a lock pauses, for example due to a stop-the-world garbage collection or a network hiccup, another process may acquire the same lock. When the paused process resumes, it may still behave as if it owns the resource. That can produce overlapping, conflicting operations and serious data corruption. Imagine a replicated cache with a primary that writes to a backing database. If the primary pauses and a new leader is elected, the database must refuse any late writes from the old primary. If it doesn't, you can get split brain updates where two different leaders both modify the same data concurrently. A fencing token is a number, or monotonic ID, handed out every time a lock is acquired. Each new acquisition gets a larger token than any previously issued. The essential requirement is that the resource itself uses the token to decide whether to accept a request, not just the client's. The resource enforces a simple compare. It accepts only requests whose token is greater than or equal to the token it considers current. If a paused, stale client later sends a request with an older token, the resource rejects it. That prevents resumed old holders from undoing safety after failover. Zookeeper gives us exactly the building blocks we need. It totally orders state changes and assigns monotonically increasing transaction IDs called ZIDs. It also keeps per node counters, like version for child changes. When a client creates an ephemeral sequential node or performs an acquire operation, the resulting ZXID or sequence-derived number increases globally and can be used as a fencing token. When acquiring a lease, write the fencing token into the protected resource's metadata or include it with all subsequent requests. Make the resource store the newest token and check incoming requests tokens. That way the resource can tell a current leader's write from a stale leader's write and reject the stale one. For practical rules, first, always enforce fencing in the resource itself. Client-side checks are insufficient. Second, use a monotonic, globally visible counter as the token. Zookeeper's ZXID is ideal. Third, make token checks and updates atomic in the resource. Update the stored token and grant permission in a single atomic step where possible. Fourth, embed the token in request metadata, headers, object fields, or version fields so the resource can validate requests independently. Let's walk the flow. A process acquires the lock or lease and the system issues a monotonic token. That token is recorded in the resource's metadata. Every write or operation from the leader includes the token. On each request, the resource compares the request token with the stored token and accepts only if the request token is current. If an old holder tries to act later, its token will be smaller and the resource will reject the operation. Lock's answer who is allowed to act, fencing token's answer when that actor is still valid. Use globally ordered, monotonic identifiers and make the resource enforce token checks atomically. Properly implemented fencing prevents paused or crashed processes from causing split brain or corrupted state after failover. Today we'll study how Zookeeper uses heartbeats to keep sessions alive and how ephemeral nodes implement ephemeral locks and leader indicators. We'll cover heartbeats, session timeouts, what happens when a session expires, examples like locks and leader election, how to tune timeouts, and practical best practices. Zookeeper clients and servers exchange simple periodic messages called heartbeats. These regular messages let each side know the other is still reachable and functioning. They are the fundamental mechanism for keeping a session alive. Important detail: Zookeeper separates the network connection from the session itself. That means a brief network blip or a short server outage won't immediately destroy the session. As long as heartbeats continue within the configured time window, the session remains valid. The session timeout is the critical threshold. If heartbeats stop for longer than this timeout, Zookeeper treats the session as expired. When a session expires, the cluster automatically cleans up any state tied to that session's liveness. A common state that depends on session liveness is an ephemeral node. Ephemeral nodes exist only while the creating session is alive. If the session goes away, Zookeeper deletes those nodes automatically. This is what makes them useful for coordination. For a distributed lock, a service creates an ephemeral node to indicate it holds the lock. If that service crashes or becomes unreachable and its session expires, Zookeeper deletes the ephemeral node and the lock is released so another instance can acquire it. In leader election, processes create ephemeral, often sequential, nodes to declare candidacy. If the leader's session expires, its ephemeral node disappears. Other participants notice this removal and can elect a new leader automatically. Choosing a session timeout is a trade-off. Shorter timeouts let the system detect failures and recover faster, useful for quick lock failover and leader replacement. Longer timeouts make the system more resilient to temporary network hiccups and client pauses. Pick a value that balances your network stability and your application's need for rapid failure detection. In practice, rely on ephemeral nodes for transient coordination states such as locks, leases, and leader indicators. Reserve persistence nodes for durable configuration or metadata. And always tune the session timeout to your environment. Too short causes false failovers, too long delays recovery. Let's walk through a simple lifecycle. The client connects and starts sending heartbeats regularly. If heartbeats continue within the configured timeout, the session stays active and ephemeral nodes remain. If heartbeats stop long enough to exceed the timeout, the session expires. The cluster then deletes ephemeral nodes created by that session, and other clients detect those deletions and take recovery actions such as acquiring a released lock or electing a new leader. Today we explore how Zookeeper provides reactive coordination for distributed systems by combining shared state, ephemeral nodes, watches, and consensus. We'll break each idea down, show examples, and end with practical design tips. At its core, Zookeeper offers a small set of complementary primitives. There are ordinary nodes that hold shared state, ephemeral nodes that follow client sessions, and watches that let clients subscribe to changes. These few features compose into powerful coordination patterns. Nodes form a simple hierarchical namespace, much like a file system. Each node can hold small metadata. Clients read and write these nodes to share information such as configurations, lock ownership, or service registration. Ephemeral nodes exist only while the creating client session is alive. When the session expires, Zookeeper automatically removes those nodes. That automatic cleanup makes ephemeral nodes excellent for representing liveness, leases, and temporary registrations. A watch is a lightweight, server-driven event. You register it on a node or its children and get a one-time notification the next time the watched state changes. Because watches are one-shot, production code typically re-registers them after they fire or uses a helper library to emulate persistent subscriptions. Imagine a payment service fleet. Each instance creates an ephemeral node under /services/payment with its address When a new instance appears, the watch on the parent directory fires. Consumers receive the event and update their routing tables or load balancers. This push-based model avoids polling and reduces discovery latency. If an instance crashes or loses connectivity and its session expires, Zookeeper removes its ephemeral node. Watchers on that directory are notified and can stop routing traffic to the failed instance immediately. Leader election commonly uses ephemeral sequential nodes. Each contender creates an ephemeral node with a monotonically increasing suffix. The contender with the lowest suffix becomes leader. If it fails, its ephemeral node disappears and the next contender learns it is now leader via a watch. Remember that watches fire only once. After a watch event, you should re-establish the watch if you need ongoing notifications. Also designed for missed events, network blips and session expiries can drop events, so reconcile by reading the current state after reconnecting. Not every Zookeeper operation requires global consensus. But operations that need a strict, globally agreed order, like creating sequential nodes or multi-operation transactions, are consensus-backed. This ensures atomicity and a single authoritative ordering for coordination primitives. Simple reads and passive observations can often be served without the full cost of consensus. That lets systems remain efficient for common read-heavy workloads while still providing linearizable updates when correctness demands it. When designing with Zookeeper, prefer event-driven architectures that react to watch events. Use ephemeral nodes to represent liveness. Always re-register watches or use helpers to provide persistent semantics. And minimize consensus-heavy operations, reserving them for tasks that require strict ordering. Zookeeper and similar systems are commonly used for service discovery, leader election, distributed locks, propagating configuration, and orchestrating one-off critical tasks like rolling upgrades or migrations. Their primitives fit these coordination needs well. Walkthrough: an instance starts and creates an ephemeral node under the service directory. Consumers who watch that directory get an event when the child list changes and update their routing tables. If the instance fails and its session expires, Zookeeper deletes the ephemeral node, the watch fires again, and consumers remove the instance from routing. For leader election, each candidate creates an ephemeral sequential node. The candidate holding the lowest numbered node is leader. If that node disappears because the leader's session expired, the next candidate notices via a watch and assumes leadership. Final checklist: model liveness with ephemeral nodes, always reconcile state after session expiry, re-register watches or use libraries that provide stable subscriptions, avoid unnecessary consensus operations, and thoroughly test failure in partition scenarios so your system behaves predictably. Today we'll explore how a small, stable coordination service like Zookeeper helps distributed systems perform two common tasks reliably: electing a single leader and assigning ownership of partitions. We'll see the simple primitives it exposes, why the ensemble stays small, and when to choose Zookeeper versus a different storage system. Distributed systems often need straightforward coordination: pick one leader, decide who owns each partition of work, and react quickly when nodes join or fail. These are the basic building blocks for many resilient architectures. Leader election is a canonical example. Imagine many stateless service instances where only one should run a scheduled task, coordinate writes, or act as the primary. When that primary fails, some other instance must take over promptly and safely. Zookeeper makes election robust by using ephemeral and sequential nodes. Candidates create ephemeral sequentials nodes, the lowest sequence number wins. Because this node is ephemeral, it vanishes if the process dies or loses connectivity, and the next candidate becomes leader automatically. Picture a fleet of stateless microservices where one instance must run maintenance or act as a primary. Each instance attempts to create the ephemeral sequential node, the winner becomes the leader. If the leader crashes, its ephemeral node disappears and a new leader is chosen without manual intervention. Partition assignment is the other common pattern. Systems that split work into partitions, stream processors, or distributed caches must move partitions when nodes join or leave so workload stays balanced and ownership is consistent. Using Zookeeper's atomic updates and change notifications, you can store assignment tables and trigger orderly transitions. Clients watch relevance nodes and react when assignments change, so ownership handoff is clear and observable to all parties. Here's a simple flow you can picture. Candidates create ephemeral sequential nodes. The one with the lowest sequence number is the leader. If that leader fails, its ephemeral node disappears and the next in line becomes leader automatically. For partition rebalancing, when a node joins, a coordinator updates the assignment table in an atomic operation. Watches notify the nodes involved, so they can acquire ownership and begin processing. The atomic update plus notifications ensures a predictable handover. practical mechanics reduced to three simple primitives: atomic ops for consistent updates, ephemeral nodes for membership and liveness, and watches so clients react to changes. These primitives are compact but powerful when combined correctly. Libraries like Apache Curator provide battle-tested recipes, leader elector, shared locks, persistent watches that save you from reinventing boilerplate. They help, but you still must think about failure modes and edge cases in your design. Zookeeper deliberately keeps the consensus layer small. Typical ensembles run 3 or 5 servers and make decisions by majority vote. Thousands of application clients can connect. This avoids the complexity of running quorum across every application node. Use Zookeeper for slow-changing metadata, who is leader for a partition, configuration, or topology that changes over minutes or hours. It's not meant for highly dynamic runtime state that changes thousands or millions of times per second. For that, choose purpose-built replicated storage or logback systems. In short, Zookeeper gives concise, reliable building blocks for leader election and partitioning. By centralizing coordination in a tiny, well-managed ensemble, you get automated recovery and orderly rebalancing without having to reinvent consensus. Today we'll compare two common needs in distributed systems: finding services and agreeing on a leader. By the end you should know when strong consensus is required and when cached, fast name resolution is enough. Clouds and container platforms create and destroy instances constantly. IP addresses and endpoints are ephemeral, so systems usually register endpoints in a central registry at startup so others can discover them. This is the basic problem service discovery solves. Service discovery is commonly done with registries such as Zookeeper, ETCT, or Console, or the long-standing DNS system. These systems let services publish where they are and let clients look them up when needed. DNS achieves availability and speed by layering caches. That means different clients can get slightly different answers, or a lookup might be briefly stale. For most service discovery use cases, this eventual consistency is acceptable because what matters is reachability and resilience, not perfect freshness. Leader election is a different class of problem. When components must agree on a single leader, the primary database node, a cluster controller, or a lock holder, everyone needs a consistent, unambiguous view. If nodes disagree, you risk split brain and conflicting actions, so strong consensus and linearizability are required. As a rule of thumb, prefer DNS-like mechanisms for locating stateless services and frontends where temporary staleness is fine. Use consensus-backed systems for decisions that must be unique and authoritative, such as electing a controller or granting a distributed lock. many systems combine both approaches. A small set of voting nodes runs consensus to make safe authoritative decisions. Read-only or observer replicas follow the ordered log asynchronously and can serve fast, highly available reads that may be slightly stale. This balances performance and safety. Let's walk a small decision flow. Start. Do you need a single authoritative decision right now? If yes, use consensus, voting cluster. If no, do you need fast, resilient name resolution and can tolerate some staleness? If yes, use DNS or cached registry reads. If you need both strict decisions and fast reads, combine a consensus core with read-only replicas. Here are concrete mappings. Stateless microservices and frontends are fine with DNS or cached registries. Critical control plane decisions, cluster controllers, locks, primary shards need consensus. When you need consistent decisions but also low latency reads, use a consensus core with observers to serve reads. To summarize, don't overuse consensus where eventual consistency suffices, it's heavier. But don't underprovide consistency for leader election and other single authority tasks. When both fast reads and strict safety are required, architect a hybrid, a voting consensus core plus read-only replicas. Today we're going to explore consensus membership, how distributed systems decide who is in the group. This topic links decades of research to practical systems like Zookeeper, ECT, Consul, and the control planes that power Kubernetes and distributed databases. A membership service answers a deceptively simple question: who is currently part of the group? It keeps the roster of nodes that are actively participating, and it tells higher-level components which peers they can rely on for coordination. Think of the roster as the cluster's attendance sheet. Each entry indicates whether a node is considered active. This sheet is crucial because many coordination algorithms, like leader election and quorum decisions, depend on everyone using the same roster. In real networks, delays are unpredictable and can be arbitrarily long. That means a node that stops responding might have crashed, or it might simply be slow, overloaded, or partitioned. Because of that uncertainty, perfect failure detection is impossible in asynchronous networks. The pragmatic solution is to use imperfect failure detectors to propose suspicions, and then use a consensus protocol to agree on membership changes. The detector says, "I suspect node X," and consensus decides whether to accept that suspicion and change the roster. By recording membership changes through consensus, the entire cluster converges on a single authoritative view. Even if detectors are noisy or produce transient false suspicions, consensus makes the membership decision global and consistent. If different nodes have different membership lists, you can get multiple leaders or no leader at all. For example, a rule like pick the lowest numbered member only works when everyone agrees on the list. Using consensus to set membership first prevents split brain and ensures deterministic leader selection. In practice, systems combine several techniques. Heartbeats or gossip spread suspicion information. Leases or ephemeral registrations automatically expire stale memberships so old information doesn't persist forever. A consensus layer, often implemented with Paxos or Raft, makes membership changes authoritative. Layering these components gives resilience despite network uncertainty. This design isn't foolproof. Consensus can make a wrong decision permanent in the short term, for example, declaring a slow but healthy node dead. Systems mitigate this with short leases, conservative timeouts, monitoring, and sometimes operational intervention to recover nodes that were incorrectly evicted. Here's a simple flow to keep in mind. Heartbeats or gossip produce suspicion signals. The failure detector aggregates those signals and proposes suspect nodes. The consensus protocol then decides whether to change the membership. Once the membership is updated, higher-level processes such as leader election or quorum-based operations use that single agreed roster. To summarize, we can't perfectly detect failures in real networks, so we combine imperfect detectors with consensus to craft a reliable roster. Consensus gives us a single truth that other protocols depend on, and layering heartbeats, leases, and consensus keeps the system practical and resilient. Today we examine why causality is not always enough in distributed systems, and why consensus becomes necessary. We'll trace a path from the simple single-copy mental model to the hard realities of making a single, irreversible decision across many nodes. Start with linearizability. Think of a cluster of replicas behaving exactly like one single copy of the data. Every operation looks as if it took effect at one instant between when it was called and when it returned. That makes reasoning simple. It matches your mental model of a single-threaded variable. But to guarantee a single global order across geographically separated nodes, systems must coordinate a lot. That coordination increases latency, especially in high-delay networks. Now contrast that with causal consistency. Causality captures happen before relations. If event A could have influenced event B, the system preserves that order. Unlike linearizability's single total order, causal consistency permits independent events to be seen in different orders on different nodes. The version history can branch and merge. This weaker model reduces coordination overhead and is more tolerant of network delays and partitions. Causality doesn't solve every coordination problem. Imagine two edge servers handling signups for a popular app. Two users simultaneously try to claim the same unique handle on different edges. Vector clocks or Lamport timestamps can tell us whether one action causally preceded the other, but when there's no causal relationship, the two nodes can independently accept the same handle. Timestamps can order events, but they cannot enforce a single, irrevocable decision in the face of true concurrency. This is where consensus comes in. Consensus is the mechanism by which a distributed system ensures all correct nodes agree on a single value, and once decided, the decision is final. A consensus decision must be durable and visible to all participants. Consensus is the primitive that gives you a single, irreversible verdict across the cluster. Many practical distributed problems are essentially the same core challenge as consensus. These include agreeing on a single value, delivering messages in the same total order, replicating a state machine so every replica applies the same commands, electing a single leader, performing an atomic commit across participants, or implementing a distributed lock. A strong solution for one of these problems often yields solutions to the others. Here's a simple decision flow. A client sends a request. A replica proposes a value. The replicas run a consensus protocol to coordinate proposals. If agreement is reached, the change is applied and the result is made durable. If agreement is not reached, because of concurrency or partitioning, the system must retry or perform more coordination until it achieves a single decision. The practical takeaway: choose the weakest consistency model that satisfies your application's needs. Use causal consistency when you value availability and low latency and can tolerate divergent histories. But when you need a single, irreversible decision, unique identifiers, coordinated configuration changes, serializing critical state updates, you must pay the cost of consensus. Today we're studying compare and set, often called CAS. It's the simple atomic decision that powers many lock-free algorithms. If the current value equals this expected value, replace it with this new one all at once. We'll unpack how it works, common variants, examples, and practical pitfalls. At its core, CAS does four things in one atomic step. First, it reads the current value. Second, it compares that value to the expected value you provide. Third, if they match, it writes the desired new value, otherwise it leaves the value unchanged. Finally, it reports whether the swap happened, usually by returning a success flag or the observed value. Here is compact pseudocode you can hold in your head. The whole if check and assignment are atomic, no other thread can sneak in between the read and the conditional write. Either the change occurs, or it doesn't, and you learn the outcome. Implementations vary in what they return. A Boolean CAS simply says success or failure. A value returning CAS returns the previous value, letting the caller inspect what was seen and choose a retry strategy. Also be aware of strong versus weak CAS. Weak CAS can fail spuriously and must be used inside a retry loop, while strong CAS promises not to fail when the value actually matches. CAS shows up everywhere. For an optimistic web update, you fetch a version token, change locally, and send an update that only applies if the token still matches. That's CAS. To push onto a lock-free stack, you read the head, set node. Next to that head, then CAS the head pointer to your node. If someone else changed head, you retry. In an order book, you update a quote only if the quote ID is still the one you read. Here's the typical flow. You read the current state, compute your intended update, then attempt CAS. If CAS succeeds, you're done. If it fails, that indicates someone else changed the value, so you read again and retry. This simple loop, often with a short backoff, is the basis of optimistic concurrency. This is the canonical retry pattern. You optimistically assume the value won't change, try the CAS, and only on failure do you reread and retry. Backoff reduces contention and can prevent livelock under high concurrency. CAS is supported directly by hardware and exposed by modern languages. On x86 you have CMPXCHG instructions. On ARM there are LDREX/STREX primitives used to build CAS. In C11 and C++11 the STD atomic API gives you compare_exchange_strong and compare_exchange_weak. Rust offers compare_exchange and compare_exchange_weak on atomic types as well. CAS interacts with memory ordering. If a successful CAS grants visibility for later reads, use acquire semantics. If CAS's publishing state that other threads must see, use release semantics. And although sequentially consistent ordering is the safest, it is heavier, prefer acquire/release to balance correctness and performance. There are several pitfalls. The ABA problem occurs when a location goes from A to B and back to a CAS that only checks for A will wrongly succeed despite an intervening change. Weak CAS can fail spuriously, so always code it inside a loop. And heavy contention can cause starvation or unfairness. Back-off strategies help here. To mitigate ABA, attach a small version counter to the pointer or value, so the tag changes on every update. If hardware supports double-width CAS, you can update pointer plus tag atomically. For safe memory reuse, use hazard pointers or other reclamation schemes. Finally, use exponential backoff to ease contention. In summary, compare and set gives you a small but powerful atomic decision. If it's what I expect, replace it. With it, you can build lock-free data structures and optimistic concurrency patterns. But be mindful of memory ordering, the ABA issue, spurious failures, and contention. With those safeguards, CAS becomes a practical and scalable synchronization primitive. Today we'll explore how distributed systems decide whether multiple participants should all apply a change or none of them should. We'll look at the classic two-phase commit protocol, common failure scenarios, how systems recover, and modern alternatives and best practices. The core objective is atomicity across nodes. A distributed transaction must complete everywhere or not at all. That prevents partial updates that could leave the system in an inconsistent state. Two-phase commit, or 2PC, is the canonical protocol. A coordinator drives the decision and multiple participants follow. Together they reach a binary outcome, commit or abort. In the first phase, the coordinator asks each participant if it can commit. Participants do the local preparation work, for example acquiring locks and writing a durable prepared record, and then vote yes if they can commit or no if they must abort. Participants that vote yes persist that vote so they can finish even after a crash. In the second phase, the coordinator collects votes. If every participant voted yes, the coordinator writes a global commit to durable storage and instructs all participants to finalize. If any participant voted no, the coordinator writes abort and tells everyone to roll back. Think of an e-commerce checkout involving orders, payments, and inventory services. The coordinator asks each service if it can reserve the needed resource. Only when all three say yes does the coordinator instruct them to finalize. If any say no, the coordinator instructs each to release their reservations. Here's a simple step-by-step flow. The coordinator sends prepare to all participants. Participants reply yes or no. The coordinator decides if all replies are yes, then commit, otherwise abort, and broadcasts that decision. Participants then apply the commit or roll back the work they prepared. There are several tricky failure scenarios. If the coordinator crashes before making a decision, participants who voted yes remain in a prepared state and can block progress. If the coordinator crashes after recording the decision, participants can recover by reading the coordinator's durable log. A participant crash forces that participant on recovery to consult the coordinator for the final outcome, and network partitions or lost messages introduce uncertainty and reliance on durable logs and timeouts. Durability helps recovery. Both coordinator and participants persist critical states like prepare and commit records. After a crash, participants typically query the coordinator for the final decision. If the coordinator is unreachable, they remain prepared to preserve correctness. Systems may use timeouts and operator interventions to resolve long block transactions, but such heuristics risk violating atomicity. two-phase commit is correct but has drawbacks. It can block. Participants may remain prepared until the coordinator recovers. Performance suffers due to blocking network round trips and mandatory durable writes. And the single coordinator is a potential point of liveness failure. There are several ways to mitigate two PC limits. Three-phase commit adds a step to reduce blocking but requires strong timing assumptions. Consensus-based approaches like Paxos or Raft replicate the commit decision across a fault-tolerant group, removing the single coordinator liveness bottleneck. Optimistic techniques proceed assuming few conflicts and resolve them later. The saga pattern replaces a single atomic commit with a sequence of local transactions paired with compensating actions. Systems like Spanner use tightly synchronized time plus consensus to achieve external consistency for distributed commits. In practice, prefer small, short-lived distributed transactions to reduce locking and blocking. Whenever possible, collocate related data or use a single transactional resource to avoid cross-service commits. For critical decisions, rely on consensus replication rather than a single coordinator. When full ACID across services is infeasible, use sagas with well-designed compensating actions and ensure operations are idempotent and retry-safe. Finally, monitor for long-prepared transactions and provide operators with safe resolution tools. To summarize, deciding commit or abort in a distributed system is fundamentally a coordination problem under uncertainty. Two-phase commit guarantees correctness but can hurt availability and latency. Modern systems balance these trade-offs using consensus replication, compensating workflows like sagas, careful design, and durable logging. Choose the right tools based on your application's consistency, availability, and performance requirements. Welcome. Today we explore how messaging systems decide the order in which messages are delivered, why that choice matters for correctness and scale, and practical ways to design reliable message-driven applications. every messaging system must pick a delivery order. That choice, how strict ordering is, how it is enforced, and who is responsible affects correctness, latency, throughput, and how easy the system is to reason about. We'll cover common ordering models, implementation techniques, trade-offs, and pragmatic recommendations. Before we dig into models, let's look at real problems that arise when ordering is wrong: inconsistent UI, incorrect financial state, broken game logic, and downstream service errors. These motivate why we must pick the right ordering for each case. Imagine Alice edits a document and Bob later sees an earlier version. Or a chat shows a reply before the original message. The user experience breaks because perceived causality is violated. If a debit is processed before its corresponding deposit arrives, transactions may be rejected or accounts show false overdrafts. Ordering errors here can cause monetary loss and compliance issues. Player movement and attack events delivered out of order lead to inconsistent game state across clients, unfair advantages, or nonsensical behavior that ruins gameplay. One service may emit create order, then pay order. If consumers see pay first, they may try to apply payment to a non-existent order, causing failures or complex compensations. Now we'll walk through the common ordering models, from weakest to strongest guarantees, and what they mean for application behavior and system design. No ordering is promised, messages can arrive in any sequence. Use this when operations are independent or when your application tolerates reordering and can resolve it at a higher layer. FIFO ensures messages from the same producer arrive in send order. It's common and relatively cheap to implement using per-producer sequence numbers or counters. Messages are ordered inside a partition or message group but not across partitions. This lets systems scale by parallelizing across partitions while preserving order for a key. Kafka and SQS FIFO with groups are examples. Causal ordering guarantees that if A could have influenced B, all recipients see A before B. It preserves causality without forcing a single global sequence, but requires metadata like logical or vector clocks. Total ordering gives every recipient the same global sequence. It simplifies reasoning but is the most expensive, typically implemented via consensus, Raft, Paxos, or a centralized sequencer. Let's look at practical mechanisms systems use to encode and enforce those ordering models. Producers tag messages with monotonic counters. Consumers can detect gaps in buffer or request missing messages. This is the simplest way to get FIFO per producer guarantees. Sharding by key routes related messages to the same partition. Order is preserved per partition, enabling scalable, parallel processing while keeping per key ordering. Lamport timestamps or vector clocks attach causal metadata. Lamport clocks order events but don't capture concurrency precisely. Vector clocks capture causality across multiple producers but grow in size. Algorithms like Raft or Paxos produce a single agreed sequence across replicas. Useful for replicated state machines where every replica must apply the identical order of updates. Consumers can buffer out-of-order messages and apply them when gaps are filled or a timeout/watermark triggers. This is a pragmatic way to cope with transient reordering without global coordination. Ordering interacts with delivery guarantees, at most once, at least once, and exactly once. For example, at least once plus FIFO can produce duplicates, so consumers must be idempotent or deduplicate. Retries can produce duplicate messages in the same order. Applications must detect duplicates or ensure idempotent processing using unique message IDs or state checks. Exactly once semantics with ordering is expensive, it may require distributed transactions, careful state management, or idempotent, transactional sinks. Often expensive and complex in large systems. Stronger ordering simplifies reasoning but costs throughput and increases latency because of centralized sequencing or consensus. Weaker guarantees improve performance and availability but push complexity to applications. Practical choices reduce risk. Pick the weakest ordering that satisfies correctness, partition by key for parallelism, and make consumers resilient to duplicates and reordering. Ask whether you need per user, per account, or global ordering. Avoid global order unless absolutely required, it's costly. Include unique message IDs and keep a short-lived dedup cache. Idempotent consumers tolerate retries and duplicates without corrupting state. Route all messages for the same entity to the same partition or group to preserve order while scaling across keys. Attach monotonic counters at the producer and have consumers detect gaps. Decide whether to wait, request retries, or apply compensating actions for missing messages. Match requirements to middleware. Kafka for per-key partitioned ordering, Raft/Paxos for total order in replicated state machines, SQS FIFO for ordered queues with message groups. For collaborative apps, causal delivery or conflict-free replicated data types, CRDTs, reduce coordination while preserving user intent. Here's a simple decision flow to guide your choice. Start with correctness and variance, then consider scale and failure modes. Read the decision flow as steps. First, identify your correctness and variance. If you need ordering per entity, partition by key and rely on per partition FIFO. If you need causal relationships across actors, use causal delivery or logical clocks. If reordering is tolerable, accept unordered messaging for throughput. Only if nothing else suffices should you use consensus for a global sequence. Before building a pipeline, run through these concrete steps to ensure your design meets needs and survives failures. Explicitly list which event orders must be preserved for correctness per user, per account, per resource, or global. Choose the minimal guarantee that preserves correctness. Weakest model that works is usually best for scale. Pick technologies that implement your chosen model efficiently, partition queues for per key order, consensus for total order, etc. Enrich messages with monotonic counters, unique IDs, and timestamps to enable detection of gaps, duplicates, and causality. Make consumers resilient to duplicates and out-of-order deliveries using idempotent handlers and short-lived dedup caches. Decide how to act when sequence holes appear, buffer and wait, request retries, or apply compensating transactions. Simulate restarts, network partitions, and message loss to verify ordering assumptions hold under stress. Ordering is a spectrum. Strong guarantees simplify reasoning but cost scale. Aim for the simplest ordering model that preserves correctness, pair it with idempotent processing, and document the semantics your system provides. That balance delivers reliability without unnecessary coordination overhead. Today we're looking at a simple but powerful idea in distributed systems. When multiple clients try to take the same resource, the lock or lease mechanism is the arbiter. We'll see how that decision is made and what clients should do whether they win or lose. Imagine a single restroom key on a hook outside a door. If several people reach for it at once, only one person can take the key and use the restroom. That person has exclusive access. Everyone else either waits or goes away and tries later. This physical picture maps directly to software locks and leases. One winner, everyone else is blocked or retries. Mutual exclusion means that only the client that holds the lock can perform the protected action. Other clients must either wait, be blocked, or retry later. This guarantee is crucial to prevent concurrent operations from corrupting shared state. The lock implementation makes the acquisition decision atomically. Clients might attempt to get the lock at the same time, but the lock system decides a single winner in one atomic step. Clients don't try to negotiate among themselves, the lock resolves the race. Some lock APIs block the caller until the lock becomes available. Others provide a non-blocking try-acquire that returns immediately with success or failure. Both are useful. Blocking is simpler when you can wait. Non-blocking is useful for time-sensitive tasks that need to proceed if they can't get exclusive access. A lease is a lock with an expiration time, TTL. If the holder fails to renew the lease because it crashed or lost connectivity, the lease expires and others can take over. Leases prevent permanent lockout from crashed clients, but they require careful renewal and clock/timeout handling. Redis offers a common pattern, set key value NXPXTTL. NX ensures the set only happens if the key doesn't exist, so only one client wins, and PX sets a TTL so the lock auto expires. Clients that lose the set can retry with exponential backoff. This pattern is commonly used for leader election in microservices. Kubernetes uses a lease object for leader election among controllers or pods. Competing pods try to update the same lease record. Kubernetes ensures only one pod's update succeeds at a time. The lease has a renewal period so leadership can transfer if a pod fails to renew. Zookeeper clients create ephemeral sequential nodes. The client with the lowest sequence number becomes the leader. If that client disconnects, Zookeeper automatically deletes its ephemeral node and the next lowest client takes over. This gives a clear, automatic failover behavior. Many databases and operating systems provide advisory locks or file locks. When two processes request the same advisory lock, the lock manager decides who gets exclusive access. These primitives are used for coordination when you don't want to build a separate distributed locking service. Different lock implementations handle fairness differently. Some try to serve waiters in FIFO order, others are unfair for performance, which can cause starvation. Choose a lock primitive based on whether fairness and starvation avoidance matter for your workload. To handle failures, prefer leases or heartbeats so a crashed holder eventually loses ownership. Avoid designs that allow indefinite blocking without timeouts, otherwise a crashed client could deadlock your system. Always design a recovery path for lost or stalled owners. When many clients contend for the same lock, they can create a thundering herd. Use exponential backoff with jitter on retries to spread attempts over time and reduce collision probability. This simple practice greatly improves throughput under contention. Here's a step-by-step flow to keep in mind. Clients attempt acquisition, the lock checks and makes an atomic decision, the winner performs work while holding the lock, the winner releases the lock or its lease expires, losers either wait, retry with backoff, or yield. If the holder fails, a lease expiry or heartbeat timeout allows others to take over. In summary, competition for locks is expected. The lock or lease enforces correctness by choosing a single owner. Design clients to handle winning, perform work, release/renew, and losing, retry, backoff, or yield. Rely on lock guarantees and use leases, timeouts, and backoff strategies to handle failures and reduce contention. Today we'll cover how systems decide a machine or service is dead. This is a practical topic. Most systems use timeouts to infer liveness, but choosing and responding to those timeouts correctly is the hard part. I'll walk you through what happens, the common pitfalls, useful techniques, and concrete examples. First, the basic mechanism. Nodes either send periodic heartbeats or respond to probes. If a node fails to reply before a configured timeout, the detector treats its session as expired and may mark it unreachable. That simple looped send, wait, timeout is the foundation of most failure detectors. A node session begins when it last responded or successfully registered, and continues until the detector decides the session has timed out. Different systems attach different meanings to a timed out session. Some immediately evict the node, others mark it suspected and wait for more evidence. It's important to remember timeouts are not proofs. Networks can delay packets, processes can pause for garbage collection, and partitions can be transient. A timeout is a probabilistic judgment, not a fact. It trades certainty for timeliness. There are two critical error types to understand. A false positive is when we suspect a node that is actually alive. This can cause unnecessary failovers or duplicate work. A false negative is when a failed node isn't suspected quickly enough that delays recovery. Good detection balances these errors. To balance false positives and negatives, you must know your environment. Measure round-trip times, packet loss, GC pauses, and scheduling delays. Timeouts tuned to observed behavior reduce both kinds of mistakes. When setting timeouts, avoid fixed guesses. Base them on measured RTT plus a safety margin. Better yet, use statistical estimators like EWMA for revolving conditions or percentile-based windows to cover typical tail latency. Adaptive detectors such as the Fiacrol algorithm compute a suspicion score from inter-arrival statistics instead of a single threshold. This lets the system dynamically become more or less sensitive as network conditions change, improving accuracy without manual retuning. To lower overhead, piggyback heartbeat information on regular messages rather than sending separate heartbeat packets. This preserves liveness visibility while reducing network and processing cost. A practical safety measure is multi-step suspicion. First mark a node as suspected, then perform extra checks or waits before taking irreversible actions such as removing it from membership or electing a new leader. This limits disruption from transient blips. For safety-critical decisions, rely on redundancy and quorums. Making decisions based on multiple independent observations reduces the impact of a single mistaken suspect and preserves consistency across the system. Here's a simple flow you can draw and follow. Start with periodic heartbeats or probes. If a reply is missed and the timeout expires, mark the node as suspected. Then try to confirm the suspicion with extra checks or retries. Only after confirmation do you take irreversible actions like reconfiguring quorum or starting a failover. In practice, Raft uses election timeouts too short and you get churn, too long and failover is slow. Cassandra has used FiAccrual to adapt suspicion sensitivity. Kubernetes liveness/readiness probes must account for cold starts and GC pauses. And multiplayer games must avoid kicking players for brief mobile blips. A short checklist for robust systems. 1. Observe and measure real latency and pause characteristics. 2. Make timeouts configurable with sensible defaults for different environments. 3. Prefer suspect then confirm for membership or destructive changes. 4. Combine timeout detectors with application-level signals like health pings or metrics to reduce false positives. To conclude, timeouts are a practical and widely used way to infer liveness, but they are inherently heuristic. The recipe for robustness is simple in concept: measure your environment, use adaptive detection when helpful, and design your reactions so the system tolerates occasional misclassifications without sacrificing safety or availability. Today we'll explore how distributed databases make decisions when multiple transactions touch the same key, what happens when the central decision maker is unreachable, and practical strategies to design resilient systems. We'll cover leader-based models, failure modes, 3 ways to handle leader unavailability, outsourced consensus tools, leaderless alternatives, and why studying distributed systems theory matters. When several concurrent transactions try to create or update records using the same key, the system must decide which one wins and which one fails with a constraint violation. On a single node, this decision is easy because there's one authority handling requests. In multi-node systems, things get more complicated because multiple replicas or coordinators may see conflicting operations at the same time. A common solution is a leader-based database. One node is the leader and it makes decisions about conflicts. Leader-based designs let systems provide linearizable operations, guarantee unique keys, and maintain a totally ordered replication log. The leader centralizes decision-making, which simplifies reasoning and the implementation of correctness properties. That centralization is also a liability. If the leader crashes or becomes isolated by a network partition, no other node may have authority to decide conflicting updates. The result can be a stalled system, writes and some transactions block because the authority to commit or reject them is missing. There are three practical ways systems handle an unreachable leader: wait for the original leader to return, use manual failover where humans promote a new leader, or run an automatic election using a consensus algorithm. Each approach has trade-offs in availability, simplicity, and operational complexity. Some systems and transaction coordinators accept temporary blocking and rely on the original leader to recover. This is simple and keeps the original ordering intact, but it violates termination guarantees. If the leader never recovers, the system stays blocked indefinitely. In production environments, that uncertainty is often unacceptable. A common pattern in traditional deployments is manual failover. Operators detect the failure, choose a new leader, and reconfigure the cluster. Manual promotion works, but it's slow and error-prone because it depends on humans and external procedures that are often outside the system's control loop. The most robust option is automatic failover driven by a consensus protocol. Algorithms such as Raft and Paxos let a cluster detect failures and elect a new leader without human intervention. Production implementations at Consul, Zookeeper are battle-tested and designed to handle unreliable networks and crashed nodes. Here's a simple decision flow you can visualize. Start: is the leader reachable? If yes, continue routing rights to leader. If no, choose wait for original leader, blocks, or initiate failover. For failover, you can manual failover, human promotes node, slow/error prone, or automatic election, consensus, uses Raft/Paxos and elects new leader. This flow shows trade-offs between availability, speed, and operational complexity. Even if your database routes all writes through a single leader, so most writes do not run full consensus, you still need consensus for leader election and cluster membership. In other words, introducing a leader only shifts where consensus is required. The good news is you don't need to invent algorithms, use proven implementations instead of ad hoc solutions. Tools like Zookeeper, ETT, and Consul provide outsourced consensus, failure detection, and membership services. They are not trivial to use correctly, but they spare you from re-implementing subtle distributed algorithms and handling corner cases that appear under partitions, clock skew, and crash recovery. If your application needs a fault-tolerant primitive that reduces to consensus, prefer an existing library or service. Not every system should enforce global consensus. Leaderless or multi-leader replication designs avoid a single global authority and accept that concurrent writes can produce divergent histories across replicas. These architectures make conflicts an operational reality to be managed with conflict resolution policies, merge procedures, CRDTs, or vector clocks/version vectors. If strict linearizability isn't required, embracing eventual consistency can improve availability and reduce latency. Finally, study the theory of distributed systems. Despite dense proofs and simplified models, the literature explains what is possible, what is impossible, and where surprising failure modes occur. Foundational papers and protocols will help you avoid costly mistakes when designing or operating distributed systems. To summarize Part 2, we examined replication, partitioning, transactions, failure models, and consistency and consensus. With this theoretical foundation, Part 3 will shift to practical engineering, how to compose diverse building blocks into robust, scalable applications. Today we'll explore eventual consistency, what it promises, why systems use it, and how to make it practical. At its core, eventual consistency says that if you stop making updates to some data, all replicas will eventually agree on the same value. That simple promise lets distributed systems stay available and responsive across regions, but it also opens a complex design space. We'll unpack the problems, the common extensions people use, and practical design patterns you can apply. Let's start with the key promise and trade-offs. The promise is eventual convergence. Given no new updates, replicas will end up the same. The trade-off is clear. To tolerate partitions and keep services responsive, we give up immediate global agreement. That reduction in synchrony is what enables low-latency, geo-distributed services. Why does this matter in practice? Because latency and availability are often business critical. Synchronous replication with strong consistency can add hundreds of milliseconds to operations, and may become unavailable during network partitions. Eventual consistency allows systems to remain responsive and partition tolerant by permitting temporary divergence, but that divergence can be surprising unless we add constraints. Here are common user-facing scenarios where designers choose consistency models carefully. Social feeds often tolerate temporary ordering differences as long as posts appear quickly. Shopping carts, single-user carts can be session-scoped with read-your-rights guarantees, but cross-device or shared carts may need stronger coordination. Collaborative editing requires merging concurrent edits without data loss, which pushes toward specialized data types or coordination. Eventual consistency by itself is weak because it doesn't bound convergence time, doesn't choose a deterministic winner for concurrent updates, and doesn't provide ordering guarantees. That leads to three practical anomalies: lost updates, where concurrent writes overwrite each other; stale reads, where a client observes old state after its own write; and causality violations, where dependent actions are observed out of order and break application logic. One simple way to improve developer ergonomics without global synchronization is session guarantees. Read your writes ensures a client sees its own recent updates. Monotonic reads ensure a client never sees older versions after seeing newer ones. Monotonic writes serialize a client's writes in session order. These are cheap and often sufficient, for example when a mobile user edits offline and later expects their edits to be visible after reconnecting. Causal consistency ensures operations that are causally related are seen in the same order by all observers. It's useful for preserving intuitive dependencies, such as replies appearing after the posts they reference. Causal plus adds deterministic conflict resolution, usually via CRDTs, delivering both causal ordering and strong convergence without coordination. CRDTs are data types designed so that concurrent updates merge deterministically and replicas converge irrespective of update order. This yields strong eventual consistency. Simple examples: a G counter that only grows avoids lost increments, a PN counter supports increments and decrements. Sequence CRDTs support collaborative text editing by making character insertions commutative. CRDTs remove the need for coordination in many multi-writer scenarios. To detect concurrency and reason about causality, systems embed metadata. Vector clocks accurately capture causality, but their size grows with replicas. Hybrid logical clocks combine physical time and logical counters to produce compact, causality-preserving timestamps that are practical for geo-distributed stores. Choose the mechanism that fits your scale and conflict resolution needs. Convergence also requires propagation and repair. Anti-entropy protocols synchronize state between pairs of replicas. Gossip spreads updates probabilistically across a cluster. Combined with deterministic reconciliation rules or CRDTs, these mechanisms ensure replicas converge even under node churn and transient failures. Make sure your system runs regular repairs and monitors convergence. A common cheap heuristic is last writer wins, which uses timestamps to pick a single winner for concurrent updates. It's easy but can silently discard important updates, so use it only for metadata or truly obsolete values. For user-generated content, counters, or collaborative data, prefer CRDTs or application-aware merge logic that preserves intent. When choosing a model, use eventual consistency for latency-critical workloads where a single writer per key is common. For collaborative multi-writer workloads, use CRDTs or causal plus consistency to avoid lost updates. If global invariants or multi-key transactions are non-negotiable, use consensus protocols like Paxos or Raft or transaction layers. Often the best practical approach is hybrid. Keep local operations fast with eventual guarantees and add bounded or on-demand strong checks where correctness demands it. Some practical tips: limit the surface that needs stronger guarantees. Per object or per operation is often enough. Offer session guarantees to improve developer experience. Use CRDTs for commutative, mergeable data types. Run background anti-entropy and measure staleness, convergence time, and conflict frequency as first-class metrics. Finally, give clients a way to retry or escalate to stronger consistency when necessary. Recent trends include broader real-world adoption of CRDTs in collaborative and offline-first apps, practical causal plus systems that add a small amount of metadata for strong semantics, and hybrid frameworks that let you tune staleness or require causality only when needed. There's also growing work on formal verification and developer-facing libraries that encapsulate consistency semantics safely. Looking forward, priorities include building scalable causality tracking for thousands of replicas, better developer abstractions that hide complexity while exposing semantics, adaptive systems that pick consistency levels dynamically using predictive models, and formal tooling that verifies application invariance under the selected consistency model. These advances will make it easier to get correctness and performance together. In conclusion, eventual consistency is indispensable for global, highly available applications, but its basic guarantee is rarely enough. By layering session guarantees, causal semantics, CRDTs, and reconciliation protocols, you can build predictable and convergent systems without losing availability. The guiding principle is pragmatic: choose the weakest consistency model that still preserves your correctness requirements, and use the strongest possible model that keeps the user experience acceptable. For further study, read seminal CRDT papers and practical tutorials, follow up on causal consistency literature including systems like COPS, and examine modern databases that offer tunable consistency. Those resources will deepen your understanding of the trade-offs and implementation techniques we've covered today.